an Enigma machine is shown. The device has a keyboard above a complex plug board in which wires connect different lettered plugs. Beneath these and toward the front of the device are 3 mechanical rotors, each with 26 pins. Enigma machines like this one were used by government and military officials for enciphering and deciphering top-secret communications during World War II. By varying the combinations of the plug board and the settings of the rotors, encoders could add complex encryption to their messages. Notice that the 3 rotors each contain 26 pins, one for each letter of the alphabet. Later versions had 4 and 5 rotors. Credit: Modification of Enigma Machine by School of Mathematics, University of Manchester/Flickr. Chapter Outline: 7. Systems of linear equations, 2 variables. 7. 2 systems of linear equations, 3 variables. 7. 3 systems of nonlinear equations and inequalities, 2 variables. 7. 4 partial fractions. 7. 5 matrices and matrix operations. 7. 6 solving systems with Gaussian elimination. 7. 7 solving systems with inverses. 7. 8 solving systems with Cramer's rule. At the start of the Second World War, British military and intelligence officers recognized that defeating Nazi Germany would require the Allies to know what the enemy was planning. This task was complicated by the fact that the German military transmitted all of its communications through a presumably uncrackable code created by a machine called Enigma. The Germans had been encoding their messages with this machine since the early 1930s, and were so confident in its security that they used it for everyday military communications as well as highly important strategic messages. Concerned about the increasing military threat, other European nations began working to decipher the Enigma codes. Poland was the first country to make significant advances when it trained and recruited a new group of codebreakers, math students from Poznan University. With the help of intelligence obtained by French spies, Polish mathematicians, led by Marian Rejewski, were able to decipher initial codes and later to understand the wiring of the machines. Eventually, they create replicas. However, the German military eventually increased the complexity of the machines by adding additional rotors, requiring a new method of decryption. The machine attached letters on a keyboard to 3, 4, or 5 rotors, depending on the version, each with 26 starting positions that could be set prior to encoding. A decryption code, called a cipher key, essentially conveyed these settings to the message recipient and allowed people to interpret the message using another Enigma machine. Even with the simpler 3-rotor scrambler, there were 17,576 different combinations of starting positions, 26x, 26x, 26, plus the machine had numerous other methods of introducing variation. Not long after the war started, the British recruited a team of brilliant codebreakers to crack the Enigma code. The codebreakers, led by Alan Turing, used what they knew about the Enigma machine to build a mechanical computer that could crack the code. And that knowledge of what the Germans were planning proved to be a key part of the ultimate Allied victory of Nazi Germany in 1945. The Enigma is perhaps the most famous cryptographic device ever known. It stands as an example of the pivotal role cryptography has played in society. Now, technology has moved cryptanalysis to the digital world. Many ciphers are designed using invertible matrices as the method of message transference, as finding the inverse of a matrix is generally part of the process of decoding. In addition to knowing the matrix and its inverse, the receiver must also know the key that, when used with the matrix inverse, will allow the message to be read. In this chapter, we will investigate matrices and their inverses and various ways to use matrices to solve systems of equations. First, however, we will study systems of equations on their own, linear and nonlinear, and then partial fractions. We will not be breaking any secret codes here, but we will lay the foundation for future courses. Learning objectives. In this section, you will solve systems of equations by graphing, solve systems of equations by substitution, solve systems of equations by addition, identify inconsistent systems of equations containing 2 variables, express the solution of a system of dependent equations containing 2 variables. Figure 1, credit. Thomas Sorns, a skateboard manufacturer, introduces a new line of boards. The manufacturer tracks its costs, which is the amount it spends to produce the boards, and its revenue, which is the amount it earns through sales of its boards. How can the company determine if it is making a profit with its new line? How many skateboards must be produced and sold before a profit is possible? In this section, we will consider linear equations with two variables to answer these and similar questions. Introduction to systems of equations. In order to investigate situations, such as that of the skateboard manufacturer, we need to recognize that we are dealing with more than one variable and likely more than one equation. A system of linear equations consists of two or more linear equations made up of two or more variables, such that all equations in the system are considered simultaneously. To find the unique solution to a system of linear equations, we must find a numerical value for each variable in the system that will satisfy all equations in the system at the same time. Some linear systems may not have a solution, and others may have an infinite number of solutions. In order for a linear system to have a unique solution, there must be at least as many equations as there are variables. Even so, this does not guarantee a unique solution. In this section, we will look at systems of linear equations in two variables, which consist of two equations that contain two different variables. For example, consider the following system of linear equations in two variables. 2 letter 1d465 plus letter 1d466 equals 153 letter 1d465 letter 1d466 equals 5. The solution to a system of linear equations in two variables is any ordered pair that satisfies each equation independently. In this example, the ordered pair 4, 7 is the solution to the system of linear equations. We can verify the solution by substituting the values into each equation to see if the ordered pair satisfies both equations. Shortly, we will investigate methods of finding such a solution if it exists. 2, 4 plus 7 equals 15 true 3, 4 minus 7 equals 5 true. In addition to considering the number of equations and variables, we can categorize systems of linear equations by the number of solutions. A consistent system of equations has at least one solution. A consistent system is considered to be an independent system if it has a single solution, such as the example we just explored. The two lines have different slopes and intersect at one point in the plane. A consistent system is considered to be a dependent system if the equations have the same slope and the same y-intercepts. In other words, the lines coincide, so the equations represent the same line. Every point on the line represents a coordinate pair that satisfies the system. Thus, there are an infinite number of solutions. Another type of system of linear equations is an inconsistent system, which is one in which the equations represent two parallel lines. The lines have the same slope and different y-intercepts. There are no points common to both lines. Hence, there is no solution to the system. Types of linear systems. There are three types of systems of linear equations in two variables and three types of solutions. An independent system has exactly one solution pair, xy. The point where the two lines intersect is the only solution. An inconsistent system has no solution. Notice that the two lines are parallel and will never intersect. A dependent system has infinitely many solutions. The lines are coincident. They are the same line, so every coordinate pair on the line is a solution to both equations. Figure 2 compares graphical representations of each type of system. Figure 2. How to, given a system of linear equations and an ordered pair, determine whether the ordered pair is a solution. Substitute the ordered pair into each equation in the system. Determine whether true statements result from the substitution in both equations. If so, the ordered pair is a solution. Example 1. Determining whether an ordered pair is a solution to a system of equations. Determine whether the ordered pair, 51, is a solution to the given system of equations. Letter 1d465 plus 3 letter 1d466 equals 82 letter 1d465 minus 9 equals letter 1d466. Solution. Substitute the ordered pair, 51, into both equations. 5 plus 3, 1 equals 88 equals 82, 5 minus 9 equals 1, 1 equals 1 true true. The ordered pair, 51, satisfies both equations, so it is the solution to the system. Analysis. We can see the solution clearly by plotting the graph of each equation. Since the solution is an ordered pair that satisfies both equations, it is a point on both of the lines and thus the point of intersection of the two lines. See Figure 3. Figure 3. Try it 1. Determine whether the ordered pair, 85, is a solution to the following system. 5 letter 1 D465 minus 4 letter 1 D466 equals 202 letter 1 D465 plus 1 equals 3 letter 1 D466. Solving systems of equations by graphing. There are multiple methods of solving systems of linear equations. For a system of linear equations in two variables, we can determine both the type of system and the solution by graphing the system of equations on the same set of axes. Example 2. Solving a system of equations in two variables by graphing. Solve the following system of equations by graphing. Identify the type of system. 2 letter 1 D465 plus letter 1 D466 equals minus 8 letter 1 D465 minus letter 1 D466 equals minus 1. Solution. Solve the first equation for y. 2 letter 1 D465 plus letter 1 D466 equals minus 8 letter 1 D466 equals minus 2 letter 1 D465 minus 8. Solve the second equation for y. Letter 1 D465 minus letter 1 D466 equals minus 1 letter 1 D466 equals letter 1 D465 plus 1. Graph both equations on the same set of axes as in Figure 4. Figure 4. The lines appear to intersect at the point minus 3, minus 2. We can check to make sure that this is the solution to the system by substituting the ordered pair into both equations. 2 minus 3 plus minus 2 equals minus 8 equals minus 8, minus 3 minus 2 equals minus 1 equals minus 1 true. The solution to the system is the ordered pair, minus 3, minus 2. So the system is independent. Try it 2. Solve the following system of equations by graphing. 2 letter 1 D465 minus 5 letter 1 D466 equals minus 25 minus 4 letter 1 D465 plus 5 letter 1 D466 equals 35. Q&A. Can graphing be used if the system is inconsistent or dependent? Yes, in both cases we can still graph the system to determine the type of system and solution. If the two lines are parallel, the system has no solution and is inconsistent. If the two lines are identical, the system has infinite solutions and is a dependent system. Solving systems of equations by substitution. Solving a linear system in two variables by graphing works well when the solution consists of integer values. But if our solution contains decimals or fractions, it is not the most precise method. We will consider two more methods of solving a system of linear equations that are more precise than graphing. One such method is solving a system of equations by the substitution method, in which we solve one of the equations for one variable and then substitute the result into the second equation to solve for the second variable. Recall that we can solve for only one variable at a time, which is the reason the substitution method is both valuable and practical. How to? Given a system of two equations in two variables, solve using the substitution method. Solve one of the two equations for one of the variables in terms of the other. Substitute the expression for this variable into the second equation, then solve for the remaining variable. Substitute that solution into either of the original equations to find the value of the first variable. If possible, write the solution as an ordered pair. Check the solution in both equations. Example 3. Solving a system of equations in two variables by substitution. Solve the following system of equations by substitution. Minus letter 1 D465 plus letter 1 D466 equals minus 52 letter 1 D465 minus 5 letter 1 D466 equals 1. Solution. First, we will solve the first equation for y. Minus letter 1 D465 plus letter 1 D466 equals minus 5 letter 1 D466 equals letter 1 D465 minus 5. Now we can substitute the expression letter 1 D465 minus 5 for y in the second equation. 2 letter 1 D465 minus 5 letter 1 D466 equals 12 letter 1 D465 minus 5. Letter 1 D465 minus 5 equals 12 letter 1 D465 minus 5 letter 1 D465 plus 25 equals 1 minus 3, letter 1d465 equals minus 24, letter 1d465 equals 8. Now, we substitute letter 1d465 equals 8 into the first equation and solve for y. Minus 8 plus letter 1d466 equals minus 5, letter 1d466 equals 3. Our solution is 83. Check the solution by substituting 83 into both equations. Minus letter 1d465 plus letter 1d466 equals minus 5 minus 8 plus 3 equals minus 52, letter 1d465 minus 5, letter 1d466 equals 12, 8 minus 5, 3 equals 1, true. Try it 3. Solve the following system of equations by substitution. Letter 1d465 equals letter 1d466 plus 34 equals 3, letter 1d465 minus 2, letter 1d466. Q&A. Can the substitution method be used to solve any linear system in two variables? Yes, but the method works best if one of the equations contains a coefficient of 1 or 1 so that we do not have to deal with fractions. Solving systems of equations in two variables by the addition method. A third method of solving systems of linear equations is the addition method. In this method, we add two terms with the same variable but opposite coefficients so that the sum is 0. Of course, not all systems are set up with the two terms of one variable having opposite coefficients. Often, we must adjust one or both of the equations by multiplication so that one variable will be eliminated by addition. How to? Given a system of equations, solve using the addition method. Write both equations with x and y variables on the left side of the equal sign and constants on the right. Write one equation above the other, lining up corresponding variables. If one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation, add the equations together, eliminating one variable. If not, use multiplication by a non-zero number so that one of the variables in the top equation has the opposite coefficient of the same variable in the bottom equation. Then add the equations to eliminate the variable. Solve the resulting equation for the remaining variable. Substitute that value into one of the original equations and solve for the second variable. Check the solution by substituting the values into the other equation. Example 4. Solving a system by the addition method. Solve the given system of equations by addition. Letter 1d465 plus 2 letter 1d466 equals minus 1 minus letter 1d465 plus letter 1d466 equals 3. Solution. Both equations are already set equal to a constant. Notice that the coefficient of x in the second equation, 1, is the opposite of the coefficient of x in the first equation, 1. We can add the two equations to eliminate x without needing to multiply by a constant. Letter 1d465 plus 2 letter 1d466 equals minus 1 minus letter 1d465 plus letter 1d466 equals 33, letter 1d466 equals 2. Now that we have eliminated x, we can solve the resulting equation for y. 3 letter 1d466 equals 2 letter 1d466 equals 23. Then we substitute this value for y into one of the original equations and solve for x. Minus letter 1d465 plus letter 1d466 equals 3 minus letter 1d465 plus 23 equals 3 minus letter 1d465 equals 3 minus 23 minus letter 1d465 equals 73, letter 1d465 equals minus 73. The solution to this system is minus 73, 23. Check the solution in the first equation. Letter 1d465 plus 2 letter 1d466 equals minus 1 minus 73 plus 2, 23 equals minus 73 plus 43 equals minus 33 equals minus 1 equals minus 1, true. Analysis. We gain an important perspective on systems of equations by looking at the graphical representation. See Figure 5 to find that the equations intersect at the solution. We do not need to ask whether there may be a second solution, because observing the graph confirms that the system has exactly one solution. Figure 5. Example 5. Using the addition method, when multiplication of one equation is required, solve the given system of equations by the addition method. 3 letter 1d465 plus 5 letter 1d466 equals minus 11 letter 1d465 minus 2 letter 1d466 equals 11. Solution. Adding these equations as presented will not eliminate a variable. However, we see that the first equation has 3x in it and the second equation has x, so if we multiply the second equation by minus 3, the x terms will add to 0. Letter 1d465 minus 2 letter 1d466 equals 11 minus 3. Letter 1d465 minus 2 letter 1d466 equals minus 3, 11. Minus 3 letter 1d465 plus 6 letter 1d466 equals minus 33. Multiply both sides by minus 3. Use the distributive property. Now let's add them. 3 letter 1d465 plus 5 letter 1d466 equals minus 11 minus 3 letter 1d465 plus 6 letter 1d466 equals minus 33. 11 letter 1d466 equals minus 44 letter 1d466 equals minus 4. For the last step, we substitute letter 1d466 equals minus 4 into one of the original equations and solve for x. 3 letter 1d465 plus 5 letter 1d466 equals minus 113 letter 1d465 plus 5. Minus 4 equals minus 113 letter 1d465 minus 20 equals minus 113 letter 1d465 equals 9 letter 1d465 equals 3. Our solution is the ordered pair, 3 minus 4. See figure 6. Check the solution in the original second equation. Letter 1d465 minus 2 letter 1d466 equals 11, 3 minus 2 minus 4 equals 3 plus 811 equals 11 true. Figure 6. Try it 4. Solve the system of equations by addition. 2 letter 1d465 minus 7 letter 1d466 equals 23 letter 1d465 plus letter 1d466 equals minus 20. Example 6. Using the addition method, when multiplication of both equations is required, solve the given system of equations in two variables by addition. 2 letter 1d465 plus 3 letter 1d466 equals minus 165 letter 1d465 minus 10 letter 1d466 equals 30. Solution. One equation has 2 letter 1d465, and the other has 5 letter 1d465. The least common multiple is 10 letter 1d465, so we will have to multiply both equations by a constant in order to eliminate one variable. Let's eliminate letter 1d465 by multiplying the first equation by minus 5 and the second equation by 2. Minus 5 2 letter 1d465 plus 3 letter 1d466 equals minus 5, minus 16. Minus 10 letter 1d465 minus 15 letter 1d466 equals 82. 5 letter 1d465 minus 10 letter 1d466 equals 2, 30. 10 letter 1d465 minus 20 letter 1d466 equals 60. Then, we add the two equations together. Minus 10 letter 1d465 minus 15 letter 1d466 equals 80. 10 letter 1d465 minus 20 letter 1d466 equals 60 minus 35 letter 1d466 equals 140. Letter 1d466 equals minus 4. Substitute letter 1d466 equals minus 4 into the original first equation. 2 letter 1d465 plus 3 minus 4 equals minus 162 letter 1d465 minus 12 equals minus 162 letter 1d465 equals minus 4 letter 1d465 equals minus 2. The solution is minus 2 minus 4. Check it in the other equation. 5 letter 1d465 minus 10 letter 1d466 equals 305 minus 2 minus 10 minus 4 equals 30 minus 10 plus 40 equals 30. 30 equals 30. See figure 7. Figure 7. Example 7. Using the addition method in systems of equations containing fractions, solve the given system of equations in two variables by addition. Letter 1d465 3 plus letter 1d466 6 equals 3. Letter 1d465 2 minus letter 1d466 4 equals 1. Solution. First, clear each equation of fractions by multiplying both sides of the equation by the least common denominator. 6 letter 1d465 3 plus letter 1d466 6 equals 6. 3 2 letter 1d465 plus letter 1d466 equals 184. Letter 1d465 2 minus letter 1d466 4 equals 4. 1, 2 letter 1d465 minus letter 1d466 equals 4. Now multiply the second equation by minus 1, so that we can eliminate the x variable. Minus 1, 2 letter 1d465 minus letter 1d466 equals minus 1, 4 minus 2 letter 1d465 plus letter 1d466 equals minus 4. Add the two equations to eliminate the x variable and solve the resulting equation. 2 letter 1d465 plus letter 1d466 equals 18 minus 2 letter 1d465 plus letter 1d466 equals minus 4 2 letter 1d466 equals 14 letter 1d466 equals 7. Substitute letter 1d466 equals 7 into the first equation. 2 letter 1d465 plus 7 equals 18 2 letter 1d465 equals 11 letter 1d465 equals 112 equals 5. 5. The solution is 1127. Check it in the other equation. Letter 1d465 2 minus letter 1d466 4 equals 11,122 minus 74 equals 1,114 minus 74 equals 144 equals 1. Try it 5. Solve the system of equations by addition. 2 letter 1d465 plus 3 letter 1d466 3 letter 1d465 plus 5 letter 1d466 equals 810. Identifying inconsistent systems of equations containing two variables. Now that we have several methods for solving systems of equations, we can use the methods to identify inconsistent systems. Recall that an inconsistent system consists of parallel lines that have the same slope but different letter 1d466. Intercepts, they will never intersect. When searching for a solution to an inconsistent system, we will come up with a false statement such as 12 equals 0. Example 8. Solving an inconsistent system of equations. Solve the following system of equations. Letter 1d465 equals 9 minus 2 letter 1d466 letter 1d465 plus 2 letter 1d466 equals 13. Solution. We can approach this problem in two ways. Because one equation is already solved for letter 1d465, the most obvious step is to use substitution. Letter 1d465 plus 2 letter 1d466 equals 13. 9 minus 2 letter 1d466 plus 2 letter 1d466 equals 139 plus 0 letter 1d466 equals 139 equals 13. Clearly, this statement is a contradiction because 9 not equal to 13. Therefore, the system has no solution. The second approach would be to first manipulate the equations so that they are both in slope-intercept form. We manipulate the first equation as follows. Letter 1d465 equals 9 minus 2 letter 1d466 to letter 1d466 equals minus letter 1d465 plus 9 letter 1d466 equals minus 12 letter 1d465 plus 92. We then convert the second equation expressed to slope-intercept form. Letter 1d465 plus 2 letter 1d466 equals 132 letter 1d466 equals minus letter 1d465 plus 13 letter 1d466 equals minus 12 letter 1d465 plus 132. Comparing the equations, we see that they have the same slope but different y-intercepts. Therefore, the lines are parallel and do not intersect. Letter 1d466 equals minus 12 letter 1d465 plus 92 letter 1d466 equals minus 12 letter 1d465 plus 132. Analysis. Writing the equations in slope-intercept form confirms that the system is inconsistent because all lines will intersect eventually unless they are parallel. Parallel lines will never intersect. Thus, the two lines have no points in common. The graphs of the equations in this example are shown in Figure 8. Figure 8. Try it 6. Solve the following system of equations in two variables. 2 letter 1d466 minus 2 letter 1d465 equals 22 letter 1d466 minus 2 letter 1d465 equals 6. Expressing the solution of a system of dependent equations containing two variables. Recall that a dependent system of equations in two variables is a system in which the two equations represent the same line. Dependent systems have an infinite number of solutions because all of the points on one line are also on the other line. After using substitution or addition, the resulting equation will be an identity, such as Example 9. Finding a solution to a dependent system of linear equations. Find a solution to the system of equations using the addition method. Solution. With the addition method, we want to eliminate one of the variables by adding the equations. In this case, let's focus on eliminating letter 1d465. If we multiply both sides of the first equation by -3, then we will be able to eliminate the letter 1d465. Variable. Letter 1d465 plus 3 letter 1d466 equals 2 minus 3. Letter 1d465 plus 3 letter 1d466 equals -3. 2 minus 3 letter 1d465 minus 9 letter 1d466 equals -6. Now add the equations. -3 letter 1d465 minus 9 letter 1d466 plus 3 letter 1d465 plus 9 letter 1d466 equals -6 equals 60 equals 0. We can see that there will be an infinite number of solutions that satisfy both equations. Analysis. If we rewrote both equations in the slope-intercept form, we might know what the solution would look like before adding. Let's look at what happens when we convert the system to slope-intercept form. Letter 1d465 plus 3 letter 1d466 equals 2 3 letter 1d466 equals minus letter 1d465 plus 2 letter 1d466 equals -13 letter 1d465 plus 233 letter 1d465 plus 9 letter 1d466 equals 6 9 letter 1d466 equals -3 letter 1d465 plus 6 letter 1d466 equals -39 letter 1d465 plus 69 letter 1d466 equals -13 letter 1d465 plus 23. See Figure 9. Notice the results are the same. The general solution to the system is x minus 13 letter 1d465 plus 23. Figure 9. Try it 7. Solve the following system of equations in two variables. Letter 1d466 minus 2 letter 1d465 equals 5 minus 3 letter 1d466 plus 6 letter 1d465 equals -15. Using systems of equations to investigate profits. Using what we have learned about systems of equations, we can return to the skateboard manufacturing problem at the beginning of the section. The skateboard manufacturer's revenue function is the function used to calculate the amount of money that comes into the business. It can be represented by the equation letter 1d445 equals letter 1d465 letter 1d45d, where quantity and letter 1d45d equals price. The revenue function is shown in orange in Figure 10. The cost function is the function used to calculate the costs of doing business. It includes fixed costs, such as rent and salaries, and variable costs, such as utilities. The cost function is shown in blue in Figure 10. The letter 1d465 axis represents quantity in hundreds of units. The y-axis represents either cost or revenue in hundreds of dollars. Figure 10. The point at which the two lines intersect is called the break-even point. We can see from the graph that if 700 units are produced, the cost is $3,300 and the revenue is also $3,300. In other words, the company breaks even if they produce and sell 700 units. They neither make money nor lose money. The shaded region to the right of the break-even point represents quantities for which the company makes a profit. The shaded region to the left represents quantities for which the company suffers a loss. The profit function is the revenue function minus the cost function, written as letter 1d443, letter 1d465 equals letter 1d445, letter 1d465 minus letter 1d436, letter 1d465. Clearly, knowing the quantity for which the cost equals the revenue is of great importance to businesses. Example 10. Finding the break-even point and the profit function using substitution. Given the cost function letter 1d436, letter 1d465 equals 0, 85x plus 35000, and the revenue function letter 1d445, letter 1d465 equals 1, 55x. Find the break-even point and the profit function. Solution. Write the system of equations using letter 1d466 to replace function notation. Letter 1d466 equals 0. 85 letter 1d465 plus 35, 0, 0, 0 letter 1d466 equals 1. 55x. Substitute the expression 0. 85x plus 35000 from the first equation into the second equation and solve for letter 1d465. 0. 85 letter 1d465 plus 35, 0, 0, 0 equals 1. 55 letter 1d465 35, 0, 0, 0 equals 0. 7 letter 1d465 50, 0, 0, 0 equals letter 1d465. Then we substitute letter 1d465 equals 50, 0, 0, 0 into either the cost function or the revenue function. 1, 55, 50, 0, 0, 0 equals 77,500. The break-even point is 5,077,500. The profit function is found using the formula letter 1d443, letter 1d465 equals letter 1d445, letter 1d465 minus letter 1d436, letter 1d465. Letter 1d443, letter 1d465 equals 1. 55 letter 1d465 minus 0. 85x plus 35000 equals 0. 7 letter 1d465 minus 35, 0, 0, 0. The profit function is letter 1d443, letter 1d465 equals 0. 7 letter 1d465 minus 35, 0, 0, 0. Analysis. The cost to produce 50,000 units is $77,500, and the revenue from the sales of 50,000 units is also $77,500. To make a profit, the business must produce and sell more than 50,000 units. See Figure 11. Figure 11, we see from the graph in Figure 12 that the profit function has a negative value until letter 1d465 equals 50, 0, 0, 0. When the graph crosses the x-axis, then the graph emerges into positive y values and continues on this path as the profit function is a straight line. This illustrates that the break-even point for businesses occurs when the profit function is 0. The area to the left of the break-even point represents operating at a loss. Figure 12. Example 11. Writing and solving a system of equations in two variables. The cost of a ticket to the circus is $25 for children and $50 for adults. On a certain day, attendance at the circus is 2,000, and the total gate revenue is $70,000. How many children and how many adults bought tickets? Solution. Let C equals the number of children, and it equals the number of adults in attendance. The total number of people is 2,000. We can use this to write an equation for the number of people at the circus that day. Letter 1d450 plus letter 1d440 equals 2,000. The revenue from all children can be found by multiplying $25 by the number of children, 25 letter 1d450. The revenue from all adults can be found by multiplying $50 by the number of adults, 50 letter 1d440. The total revenue is $70,000. We can use this to write an equation for the revenue. 25 letter 1d450 plus 50 letter 1d440 equals 70,000. We now have a system of linear equations in two variables. Letter 1d450 plus letter 1d440 equals 2,00025 letter 1d450 plus 50 letter 1d440 equals 70,000. In the first equation, the coefficient of both variables is 1. We can quickly solve the first equation for either letter 1d450, or we will solve for letter 1d440. Letter 1d450 plus letter 1d440 equals 2,000 letter 1d440 equals 2,000 minus letter 1d450. Substitute the expression 2,000 minus letter 1d450 in the second equation for letter 1d440, and solve for letter 1d450. 25 letter 1d450 plus 50, 2,000 minus letter 1d450 equals 70, 25c plus 100. 0, minus 50, letter 1d450 equals 70. 0, 0, 0 minus 25 letter 1d450 equals minus 30. 0, 0, 0 letter 1d450 equals 1, 200. Substitute letter 1d450 equals 1, 200 into the first equation to solve for letter 1d44e. 1, 200 plus letter 1d44e equals 2. 0, 0, 0 letter 1d44e equals 800. We find that 1, 200 children and 800 adults bought tickets to the circus that day. Try at 8. Meal tickets at the circus cost $4 for children and $12 for adults. If 1,650 meal tickets were bought for a total of $14,200, how many children and how many adults bought meal tickets? Media. Access these online resources for additional instruction and practice with systems of linear equations. Solving systems of equations using substitution. Solving systems of equations using elimination. Applications of systems of equations. 7. One section exercises. Verbal. 1. Can a system of linear equations have exactly two solutions? Explain why or why not. 2. If you are performing a break-even analysis for a business and their cost and revenue equations are dependent, explain what this means for the company's profit margins. 3. If you are solving a break-even analysis and get a negative break-even point, explain what this signifies for the company. 4. If you are solving a break-even analysis and there is no break-even point, explain what this means for the company. How should they ensure there is a break-even point? 5. Given a system of equations, explain at least two different methods of solving that system. Algebraic. For the following exercises, determine whether the given ordered pair is a solution to the system of equations. 6. 5 letter 1d465 minus letter 1d466 equals 4 letter 1d465 plus 6 letter 1d466 equals 2. And 40. 7. Minus 3 letter 1d465 minus 5 letter 1d466 equals 13 minus letter 1d465 plus 4 letter 1d466 equals 10. And minus 6, 1. 8. 3 letter 1d465 plus 7 letter 1d466 equals 12 letter 1d465 plus 4 letter 1d466 equals 0. And 23. 9. Minus 2 letter 1d465 plus 5 letter 1d466 equals 72 letter 1d465 plus 9 letter 1d466 equals 7. And minus 1, 1. 10. Letter 1d465 plus 8 letter 1d466 equals 433 letter 1d465 minus 2 letter 1d466 equals minus 1. And 35. For the following exercises, solve each system by substitution. 11. Letter 1d465 plus 3 letter 1d466 equals 52 letter 1d465 plus 3 letter 1d466 equals 4. 12. 3 letter 1d465 minus 2 letter 1d466 equals 185 letter 1d465 plus 10 letter 1d466 equals minus 10. 13. 4 letter 1d465 plus 2 letter 1d466 equals minus 103 letter 1d465 plus 9 letter 1d466 equals 0. 14. 2 letter 1d465 plus 4 letter 1d466 equals minus 3. 89 letter 1d465 minus 5 letter 1d466 equals 1. 3. 15. Minus 2 letter 1d465 plus 3 letter 1d466 equals 1. 2 minus 3 letter 1d465 minus 6 letter 1d466 equals 1. 8. 16. Letter 1d465 minus 0. 2 letter 1d466 equals 1 minus 10 letter 1d465 plus 2 letter 1d466 equals 5. 17. 3 letter 1d465 plus 5 letter 1d466 equals 930 letter 1d465 plus 50 letter 1d466 equals minus 90. 18. Minus 3 letter 1d465 plus letter 1d466 equals 212 letter 1d465 minus 4 letter 1d466 equals minus 8. 19. 12 letter 1d465 plus 13 letter 1d466 equals 1616 letter 1d465 plus 14 letter 1d466 equals 9. 20. minus 14 letter 1d465, plus 32 letter 1d466 equals 11 minus 18 letter 1d465, plus 13 letter 1d466 equals 3. For the following exercises, solve each system by addition. 21. Minus 2 letter 1d465, plus 5 letter 1d466 equals minus 427 letter 1d465, plus 2 letter 1d466 equals 30. 22. 6 letter 1d465, minus 5 letter 1d466 equals minus 342 letter 1d465, plus 6 letter 1d466 equals 4. 23. 5 letter 1d465 minus letter 1d466 equals minus 2. 6 minus 4 letter 1d465 minus 6 letter 1d466 equals 1. 4. 24. 7 letter 1d465 minus 2 letter 1d466 equals 34 letter 1d465 plus 5 letter 1d466 equals 3. 25. 25. Minus x plus 2 letter 1d466 equals minus 15 letter 1d465 minus 10 letter 1d466 equals 6. 26. 7 letter 1d465 plus 6 letter 1d466 equals 2 minus 28 letter 1d465 minus 24 letter 1d466 equals minus 8. 27. 56 letter 1d465 plus 14 letter 1d466 equals 0. 18 letter 1d465 minus 12 letter 1d466 equals minus 43,120. 28. 13 letter 1d465 plus 19 letter 1d466 equals 29 minus 12 letter 1d465 plus 45 letter 1d466 equals minus 13. 29. Minus 0. 2x plus 0. 4 letter 1d466 equals 0. 6 letter 1d465 minus 2 letter 1d466 equals minus 3. 30 minus 0. 1x plus 0. 2 letter 1d466 equals 0. 65 letter 1d465 minus 10 letter 1d466 equals 1. For the following exercises, solve each system by any method. 31. 5 letter 1d465 plus 9 letter 1d466 equals 16 letter 1d465 plus 2 letter 1d466 equals 4. 32. 6 letter 1d465 minus 8 letter 1d466 equals minus 0. 63 letter 1d465 plus 2 letter 1d466 equals 0. 9. 33. 5 letter 1d465 minus 2 letter 1d466 equals 2. 257 letter 1d465 minus 4 letter 1d466 equals 3. 34. Letter 1d465 minus 512 letter 1d466 equals minus 5,512 minus 6 letter 1d465 plus 52 letter 1d466 equals 552. 35. 7 letter 1d465 minus 4 letter 1d466 equals 762 letter 1d465 plus 4 letter 1d466 equals 13. 36. 3 letter 1d465 plus 6 letter 1d466 equals 112 letter 1d465 plus 4 letter 1d466 equals 9. 37. 73 letter 1d465 minus 16 letter 1d466 equals 2 minus 216 letter 1d465 plus 312 letter 1d466 equals minus 3. 38. 12 letter 1d465 plus 13 letter 1d466 equals 1,332 letter 1d465 plus 14 letter 1d466 equals minus 18. 39. 2. 2x plus 1, 3 letter 1d466 equals minus 0. 14. 2x plus 4, 2 letter 1d466 equals 2. 1. 40. 0. 1x plus 0. 2 letter 1d466 equals 20. 35 letter 1d465 minus 0. 3 letter 1d466 equals 0. Graphic. For the following exercises, graph the system of equations and state whether the system is consistent, inconsistent, or dependent, and whether the system has one solution, no solution, or infinite solutions. 41. 3 letter 1d465 minus letter 1d466 equals 0. 6 letter 1d465 minus 2 letter 1d466 equals 1. 3. 42 minus letter 1d465 plus 2 letter 1d466 equals 42 letter 1d465 minus 4 letter 1d466 equals 1. 43. Letter 1d465 plus 2 letter 1d466 equals 72 letter 1d465 plus 6 letter 1d466 equals 12. 44. 3 letter 1d465 minus 5 letter 1d466 equals 7 letter 1d465 minus 2 letter 1d466 equals 3. 45. 3 letter 1d465 minus 2 letter 1d466 equals 5 minus 9 letter 1d465 plus 6 letter 1d466 equals minus 15. Technology. For the following exercises, use the intersect function on a graphing device to solve each system. Round all answers to the nearest hundredth. 46. 0, 1x plus 0. 2 letter 1d466 equals 0. 3 minus 0, 3x plus 0. 5 letter 1d466 equals 1. 47, minus 0, 1x plus 0. 12 letter 1d466 equals 0. 620. 15x plus 0. 20 letter 1d466 equals 0. 52. 48. 5x plus 0. 3 letter 1d466 equals 40. 25 letter 1d465 minus 0. 9 letter 1d466 equals 0. 46. 49. 15x plus 0. 27 letter 1d466 equals 0. 39 minus 0. 34x plus 0. 56 letter 1d466 equals 1. 8. 50 minus 0. 71x plus 0. 92 letter 1d466 equals 0. 130. 83x plus 0. 05 letter 1d466 equals 2. 1. Extensions. For the following exercises, solve each system in terms of letter 1d434, letter 1d435, letter 1d436, letter 1d437, letter 1d438, and letter 1d439, where letter 1d434, letter 1d439 are non-zero numbers. Note that letter 1d434 not equal to letter 1d435, and letter 1d434 letter 1d438 not equal to letter 1d435 letter 1d437. 51. Letter 1d465 plus letter 1d466 equals letter 1d434 letter 1d465 minus letter 1d466 equals letter 1d435. 52. 53. 54. Letter 1d434 letter 1d465 plus letter 1d435 letter 1d466 equals letter 1d436 letter 1d465 plus letter 1d466 equals 1. 55. Letter 1d434 letter 1d465 plus letter 1d435 letter 1d466 equals letter 1d436 letter 1d437 letter 1d465 plus letter 1d438 letter 1d466 equals letter 1d439. Real-world applications. For the following exercises, solve for the desired quantity. 56. A stuffed animal business has a total cost of production, and a revenue function, letter 1d445, equals 20 letter 1d465. Find the break-even point. 57. An Ethiopian restaurant has a cost of production, letter 1d436, letter 1d465, equals 11 letter 1d465 plus 120. And a revenue function, letter 1d445, letter 1d465, equals 5 letter 1d465. When does the company start to turn a profit? 58. A cell phone factory has a cost of production, and a revenue function, letter 1d445, letter 1d465, equals 200 letter 1d465. What is the break-even point? 59. A musician charges letter 1d436, letter 1d465, equals 64 letter 1d465 plus 20, 000, where letter 1d465 is the total number of attendees at the concert. The venue charges $80 per ticket. After how many people buy tickets does the venue break even, and what is the value of the total tickets sold at that point? 60. A guitar factory has a cost of production, letter 1d436, letter 1d465, equals 75 letter 1d465 plus 50, 000, If the company needs to break even after 150 units sold, at what price should they sell each guitar? Round up to the nearest dollar and write the revenue function. For the following exercises, use a system of linear equations with two variables and two equations to solve. 61. Find two numbers whose sum is 28 and difference is 13. 62. A number is 9 more than another number. Twice the sum of the two numbers is 10. Find the two numbers. 63. The startup cost for a restaurant is $120,000, and each meal costs $10 for the restaurant to make. If each meal is then sold for $15, after how many meals does the restaurant break even? 64. A moving company charges a flat rate of $150 and an additional $5 for each box. If a taxi service would charge $20 for each box, how many boxes would you need for it to be cheaper to use the moving company, and what would be the total cost? 65. A total of 1,595 first and second-year college students gathered at a pep rally. The number of first years exceeded the number of second years by 15. How many students from each year group were in attendance? 66. 276 students enrolled in an introductory chemistry class. By the end of the semester, 5 times the number of students passed as failed. Find the number of students who passed and the number of students who failed. 67. There were 130 faculty at a conference. If there were 18 more women than men attending, how many of each gender attended the conference? 68. A Jeep and a pickup truck enter a highway running east-west at the same exit heading in opposite directions. The Jeep entered the highway 30 minutes before the pickup did and traveled 7 mph slower than the pickup. After 2 hours from the time the pickup entered the highway, the cars were 306, 5 miles apart. Find the speed of each car, assuming they were driven on cruise control and retained the same speed. 69. If a scientist mixed 10% saline solution with 60% saline solution to get 25 gallons of 40% saline solution, how many gallons of 10% and 60% solutions were mixed? 70. An investor earned triple the profits of what they earned last year. If they made $500,000, $48 total for both years, how much did the investor earn in profits each year? 71. An investor invested $1 million into 2 land investments. On the first investment, Swan Peak, her return was a 110% increase on the money she invested. On the second investment, Riverside Community, she earned 50% over what she invested. If she earned $1 million in profits, how much did she invest in each of the land deals? 72. If an investor invests a total of $25,000 into 2 bonds, one that pays 3% simple interest, and the other that pays 278% interest, and the investor earns $737.50 annual interest, how much was invested in each account? 73. If an investor invests $23,000 into 2 bonds, one that pays 4% in simple interest, and the other paying 2% simple interest, and the investor earns $710. Annual interest, how much was invested in each account? 74. Blu-rays cost $5, $96 more than regular DVDs at All Bets Are Off Electronics. How much would 6 Blu-rays and 2 DVDs cost if 5 Blu-rays and 2 DVDs cost $127? $73? $75. A store clerk sold 60 pairs of sneakers. The high tops sold for $98. $99, and the low tops sold for $129. $99. If the receipts for the 2 types of sales totaled $6,404. 40. How many of each type of sneaker were sold? 76. A concert manager counted 350 ticket receipts the day after a concert. The price for a student ticket was $12.50, and the price for an adult ticket was $16. The register confirms that $5,075 was taken in. How many student tickets and adult tickets were sold? 77. Admission into an amusement park for 4 children and 2 adults is $116. $90. For 6 children and 3 adults, the admission is $175. $35. Assuming a different price for children and adults, what is the price of the child's ticket and the price of the adult ticket? Learning objectives. In this section, you will solve systems of 3 equations in 3 variables. Identify inconsistent systems of equations containing 3 variables. Express the solution of a system of dependent equations containing 3 variables. Figure 1, credit. Ellembus, Wikimedia Commons. Jordy received an inheritance of $12,000 that he divided into 3 parts and invested in 3 ways. In a money market fund, paying 3% annual interest. In municipal bonds, paying 4% annual interest. And in mutual funds, paying 7% annual interest. Jordy invested $4,000 more in mutual funds than in municipal bonds. He earned $670 in interest the first year. How much did Jordy invest in each type of fund? Understanding the correct approach to setting up problems, such as this one, makes finding a solution a matter of following a pattern. We will solve this and similar problems involving 3 equations and 3 variables in this section. Doing so uses similar techniques as those used to solve systems of 2 equations in 2 variables. However, finding solutions to systems of 3 equations requires a bit more organization and a touch of visualization. Solving systems of 3 equations in 3 variables. In order to solve systems of equations in 3 variables, known as 3x3 systems, the primary tool we will be using is called Gaussian elimination, named after the prolific German mathematician Carl Friedrich Gauss. While there is no definitive order in which operations are to be performed, there are specific guidelines as to what type of moves can be made. We may number the equations to keep track of the steps we apply. The goal is to eliminate one variable at a time to achieve upper triangular form, the ideal form for a 3x3 system, because it allows for straightforward back substitution to find a solution, xyz, which we call an ordered triple. A system in upper triangular form looks like the following. The third equation can be solved for z, and then we back substitute to find y and x. To write the system in upper triangular form, we can perform the following operations. Interchange the order of any 2 equations. Multiply both sides of an equation by a non-zero constant. Add a non-zero multiple of one equation to another equation. The solution set to a 3x3 system is an ordered triple, xyz. Graphically, the ordered triple defines the point that is the intersection of 3 planes in space. You can visualize such an intersection by imagining any corner in a rectangular room. A corner is defined by 3 planes, 2 adjoining walls and the floor or ceiling. Any point where 2 walls and the floor meet represents the intersection of 3 planes. Number of possible solutions. Figure 2 and Figure 3 illustrate possible solution scenarios for 3x3 systems. Systems that have a single solution are those which, after elimination, result in a solution set consisting of an ordered triple, xyz. Graphically, the ordered triple defines a point that is the intersection of 3 planes in space. Systems that have an infinite number of solutions are those which, after elimination, result in an expression that is always true, such as. Graphically, an infinite number of solutions represents a line or coincident plane that serves as the intersection of 3 planes in space. Systems that have no solution are those that, after elimination, result in a statement that is a contradiction, such as 3 equals 0. Graphically, a system with no solution is represented by 3 planes with no point in common. Figure 2, A, 3 planes intersect at a single point, representing a 3x3 system with a single solution. B, 3 planes intersect in a line, representing a 3x3 system with infinite solutions. Figure 3, all 3 figures represent 3x3 systems with no solution. A, the 3 planes intersect with each other, but not at a common point. B, 2 of the planes are parallel and intersect with the third plane, but not with each other. C, all 3 planes are parallel, so there is no point of intersection. Example 1. Determining whether an ordered triple is a solution to a system. Determine whether the ordered triple 3, minus 2, 1 is a solution to the system. Letter 1D465 plus letter 1D466 plus letter 1D467 equals 26 letter 1D465 minus 4 letter 1D466 plus 5 letter 1D467 equals 315 letter 1D465 plus 2 letter 1D466 plus 2 letter 1D467 equals 13. How to Given a linear system of 3 equations, solve for 3 unknowns. Pick any pair of equations and solve for one variable. Pick another pair of equations and solve for the same variable. You have created a system of 2 equations in 2 unknowns. Solve the resulting 2x2 system. Back-substitute known variables into any one of the original equations and solve for the missing variable. Example 2. Solving a system of 3 equations in 3 variables by elimination. Find a solution to the following system. Letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 9 minus letter 1d465 plus 3 letter 1d466 minus letter 1d467 equals minus 62 letter 1d465 minus 5 letter 1d466 plus 5 letter 1d467 equals 17. 1, 2, 3. Solution. There will always be several choices as to where to begin, but the most obvious first step here is to eliminate x by adding equations 1 and 2. Letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 9 minus letter 1d465 plus 3 letter 1d466 minus letter 1d467 equals minus 6. 1, 2 letter 1d466 plus 2 letter 1d467 equals 3, 4. The second step is multiplying equation 1 by minus 2 and adding the result to equation 3. These two steps will eliminate the variable x. Minus 2 letter 1d465 plus 4 letter 1d466 minus 6 letter 1d467 equals minus 182 letter 1d465 minus 5 letter 1d466 plus 5 letter 1d467 equals 17. 1. Multiplied by minus 2, 3. Minus letter 1d466 minus letter 1d467 equals minus 1, 5. In equations 4 and 5, we have created a new 2x2 system. We can solve for z by adding the two equations. Letter 1d466 plus 2 letter 1d467 equals 3, 4 minus letter 1d466 minus letter 1d467 equals minus 1, 5 letter 1d467 equals 2, 6. Choosing one equation from each new system, we obtain the upper triangular form. Letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 9 letter 1d466 plus 2 letter 1d467 equals 3 letter 1d467 equals 2, 1, 4, 6. Next, we back substitute letter 1d467 equals 2 into equation 4 and solve for y. Letter 1d466 plus 2, 2 equals 3 letter 1d466 plus 4 equals 3 letter 1d466 equals minus 1. Finally, we can back substitute letter 1d467 equals 2 and letter 1d466 equals minus 1 into equation 1. This will yield the solution for x letter 1d465 minus 2. Minus 1 plus 3, 2 equals 9 letter 1d465 plus 2 plus 6 equals 9 letter 1d465 equals 1. The solution is the ordered triple, 1 minus 1, 2. See Figure 4, Figure 4. Example 3. Solving a real-world problem using a system of 3 equations in 3 variables. In the problem posed at the beginning of the section, Jordy invested his inheritance of $12,000 in 3 different funds. Part in a money market fund paying 3% interest annually, part in municipal bonds paying 4% annually, and the rest in mutual funds paying 7% annually. Jordy invested $4,000 more in mutual funds than he invested in municipal bonds. The total interest earned in 1 year was $670. How much did he invest in each type of fund? Try it 1. Solve the system of equations in 3 variables. 2 letter 1d465 plus letter 1d466 minus 2 letter 1d467 equals minus 13 letter 1d465 minus 3 letter 1d466 minus letter 1d467 equals 5 letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 6. Identifying inconsistent systems of equations containing 3 variables. Just as with systems of equations in 2 variables, we may come across an inconsistent system of equations in 3 variables, which means that it does not have a solution that satisfies all 3 equations. The equations could represent 3 parallel planes, 2 parallel planes and 1 intersecting plane, or 3 planes that intersect the other 2 but not at the same location. The process of elimination will result in a false statement, such as 3 equals 7, or some other contradiction. Example 4. Solving an inconsistent system of 3 equations in 3 variables. Solve the following system. Letter 1 D465 minus 3 letter 1 D466 plus letter 1 D467 equals 4 minus letter 1 D465 plus 2 letter 1 D466 minus 5 letter 1 D467 equals 35 letter 1 D465 minus 13 letter 1 D466 plus 13 letter 1 D467 equals 8. 1, 2, 3. Solution. Looking at the coefficients of x, we can see that we can eliminate x by adding equation 1 to equation 2. Letter 1 D465 minus 3 letter 1 D466 plus letter 1 D467 equals 4. 1 minus letter 1 D465 plus 2 letter 1 D466 minus 5 letter 1 D467 equals 3. 2 minus letter 1 D466 minus 4 letter 1 D467 equals 7, 4. Next, we multiply equation 1 by minus 5 and add it to equation 3. Minus 5 letter 1 D465 plus 15 letter 1 D466 minus 5 letter 1 D467 equals minus 200, 5 letter 1 D465 minus 13 letter 1 D466 plus 13 letter 1 D467 equals 8. 1. Multiplied by minus 5, 3 2 letter 1 D466 plus 8 letter 1 D467 equals minus 12, 5. Then, we multiply equation 4 by 2 and add it to equation 5. Multiplied by the final equation is a contradiction, so we conclude that the system of equations is inconsistent and therefore has no solution. Analysis. In this system, each plane intersects the other two, but not at the same location. Therefore, the system is inconsistent. Try it too. Solve the system of 3 equations in 3 variables. Letter 1 D465 plus letter 1 D466 plus letter 1 D467 equals 2 letter 1 D466 minus 3 letter 1 D467 equals 12 letter 1 D465 plus letter 1 D466 plus 5 letter 1 D467 equals 0. Expressing the solution of a system of dependent equations containing 3 variables. We know from working with systems of equations in 2 variables that a dependent system of equations has an infinite number of solutions. The same is true for dependent systems of equations in 3 variables. An infinite number of solutions can result from several situations. The 3 planes could be the same, so that a solution to one equation will be the solution to the other 2 equations. All 3 equations could be different, but they intersect on a line, which has infinite solutions. Or 2 of the equations could be the same and intersect the third on a line. Example 5. Finding the solution to a dependent system of equations. Find the solution to the given system of 3 equations in 3 variables. 2 letter 1 D465 plus letter 1 D466 minus 3 letter 1 D467 equals 0, 4 letter 1 D465 plus 2 letter 1 D466 minus 6 letter 1 D467 equals 0 letter 1 D465 minus letter 1 D466 plus letter 1 D467 equals 0. 1, 2, 3. Analysis as shown in figure 5, 2 of the planes are the same and they intersect the third plane on a line. The solution set is infinite, as all points along the intersection line will satisfy all 3 equations. Figure 5Q and A, does the generic solution to a dependent system always have to be written in terms of x? No, you can write the generic solution in terms of any of the variables, but it is common to write it in terms of x, and if needed x and y. Try it. 3. Solve the following system. Letter 1 D465 plus letter 1 D466 plus letter 1 D467 equals 73 letter 1 D465 minus 2 letter 1 D466 minus letter 1 D467 equals 4 letter 1 D465 plus 6 letter 1 D466 plus 5 letter 1 D467 equals 24. Media access. These online resources for additional instruction and practice with systems of equations in 3 variables. x1. System of 3 equations with 3 unknowns using elimination, x2. System of 3 equations with 3 unknowns using elimination, 7-2 section, exercises verbal 1. Can a linear system of 3 equations have exactly 2 solutions? Explain why or why not 2. If a given ordered triple solves the system of equations, is that solution unique? If so, explain why. If not, give an example where it is not unique. 3. If a given ordered triple does not solve the system of equations, is there no solution? If so, explain why. If not, give an example. 4. Using the method of addition, is there only one way to solve the system? 5. Can you explain whether there can be only one method to solve a linear system of equations? If yes, give an example of such a system of equations. If not, explain why not. Algebraic for the following exercises, determine whether the ordered triple given is the solution to the system of equations. 6. 2 letter 1d465 minus 6 letter 1d466 plus 6 letter 1d467 equals minus 12 letter 1d465 plus 4 letter 1d466 plus 5 letter 1d467 equals minus 1 minus letter 1d465 plus 2 letter 1d466 plus 3 letter 1d467 equals minus 1 and 0. 1 minus 1, 7. 6 letter 1d465 minus letter 1d466 plus 3 letter 1d467 equals 63 letter 1d465 plus 5 letter 1d466 plus 2 letter 1d467 equals 0 letter 1d465 plus letter 1d466 equals 0 and 3. Minus 3 minus 5, 8. 6 letter 1d465 minus 7 letter 1d466 plus letter 1d467 equals 2 minus letter 1d465 minus letter 1d466 plus 3 letter 1d467 equals 42 letter 1d465 plus letter 1d466 minus letter 1d467 equals 1 and 4, 2 minus 6, 9. Letter 1d465 minus letter 1d466 equals 0 letter 1d465 minus letter 1d467 equals 5 letter 1d465 minus letter 1d466 plus letter 1d467 equals minus 1 and 4, 4 minus 1, 10. Minus letter 1d465 minus letter 1d466 plus 2 letter 1d467 equals 35 letter 1d465 plus 8 letter 1d466 minus 3 letter 1d467 equals 4 minus letter 1d465 plus 3 letter 1d466 minus 5 letter 1d467 equals minus 5 and 4. 1 minus 7. For the following exercises, solve each system by elimination. 11. 3 letter 1d465 minus 4 letter 1d466 plus 2 letter 1d467 equals minus 152 letter 1d465 plus 4 letter 1d466 plus letter 1d467 equals 162 letter 1d465 plus 3 letter 1d466 plus 5 letter 1d467 equals 2012. 5 letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 202 letter 1d465 minus 4 letter 1d466 minus 3 letter 1d467 equals minus 9 letter 1d465 plus 6 letter 1d466 minus 8 letter 1d467 equals 2113. 5 letter 1d465 plus 2 letter 1d466 plus 4 letter 1d467 equals 9 minus 3 letter 1d465 plus 2 letter 1d466 plus letter 1d467 equals 104 letter 1d465 minus 3 letter 1d466 plus 5 letter 1d467 equals minus 314. 4 letter 1d465 minus 3 letter 1d466 plus 5 letter 1d467 equals 31 minus letter 1d465 plus 2 letter 1d466 plus 4 letter 1d467 equals 20 letter 1d465 plus 5 letter 1d466 minus 2 letter 1d467 equals minus 2915. 5 letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 4 minus 4 letter 1d465 plus 6 letter 1d466 minus 7 letter 1d467 equals minus 13 letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 416. 4 letter 1d465 plus 6 letter 1d466 plus 9 letter 1d467 equals 0 minus 5 letter 1d465 plus 2 letter 1d466 minus 6 letter 1d467 equals 37 letter 1d465 minus 4 letter 1d466 plus 3 letter 1d467 equals minus 3 for the following exercises. Solve each system by Gaussian elimination. 17. 2 letter 1d465 minus letter 1d466 plus 3 letter 1d467 equals 17 minus 5 letter 1d465 plus 4 letter 1d466 minus 2 letter 1d467 equals minus 462 letter 1d466 plus 5 letter 1d467 equals minus 718. 5 letter 1d465 minus 6 letter 1d466 plus 3 letter 1d467 equals 50 minus letter 1d465 plus 4 letter 1d466 equals 102 letter 1d465 minus letter 1d467 equals 1019. 2 letter 1d465 plus 3 letter 1d466 minus 6 letter 1d467 equals 1 minus 4 letter 1d465 minus 6 letter 1d466 plus 12 letter 1d467 equals minus 2 letter 1d465 plus 2 letter 1d466 plus 5 letter 1d467 equals 1020. 4 letter 1d465 plus 6 letter 1d466 minus 2 letter 1d467 equals 86 letter 1d465 plus 9 letter 1d466 minus 3 letter 1d467 equals 12 minus 2 letter 1d465 minus 3 letter 1d466 plus letter 1d467 equals minus 421. 2 letter 1d465 plus 3 letter 1d466 minus 4 letter 1d467 equals 5 minus 3 letter 1d465 plus 2 letter 1d466 plus letter 1d467 equals 11 minus letter 1d465 plus 5 letter 1d466 plus 3 letter 1d467 equals 422. 10 letter 1d465 plus 2 letter 1d466 minus 14 letter 1d467 equals 8 minus x minus 2 letter 1d466 minus 4 letter 1d467 equals minus 1 minus 12 letter 1d465 minus 6 letter 1d466 plus 6 letter 1d467 equals minus 1223. Letter 1d465 plus letter 1d466 plus letter 1d467 equals 142 letter 1d466 plus 3 letter 1d467 equals minus 14 minus 16 letter 1d466 minus 24 letter 1d467 equals minus 11224. 5 letter 1d465 minus 3 letter 1d466 plus 4 letter 1d467 equals minus 1 minus 4 letter 1d465 plus 2 letter 1d466 minus 3 letter 1d467 equals 0 minus x plus 5 letter 1d466 plus 7 letter 1d467 equals minus 1125. Letter 1d465 plus letter 1d466 plus letter 1d467 equals 0 2 letter 1d465 minus letter 1d466 plus 3 letter 1d467 equals 0 letter 1d465 minus letter 1d467 equals 0 26. 3 letter 1d465 plus 2 letter 1d466 minus 5 letter 1d467 equals 65 letter 1d465 minus 4 letter 1d466 plus 3 letter 1d467 equals minus 124 letter 1d465 plus 5 letter 1d466 minus 2 letter 1d467 equals 1527. Letter 1d465 plus letter 1d466 plus letter 1d467 equals 0 2 letter 1d465 minus letter 1d466 plus 3 letter 1d467 equals 0 letter 1d465 minus letter 1d467 equals 128. 3 letter 1d465 minus 12 letter 1d466 minus letter 1d467 equals minus 124 letter 1d465 plus letter 1d467 equals 3 minus letter 1d465 plus 32 letter 1d466 equals 5229. 6 letter 1d465 minus 5 letter 1d466 plus 6 letter 1d467 equals 3815 letter 1d465 minus 12 letter 1d466 plus 35 letter 1d467 equals 1 minus 4 letter 1d465 minus 32 letter 1d466 minus letter 1d467 equals minus 7430. 12 letter 1d465 minus 15 letter 1d466 plus 25 letter 1d467 equals minus 131,014 letter 1d465 minus 25 letter 1d466 minus 15 letter 1d467 equals minus 720 minus 12 letter 1d465 minus 34 letter 1d466 minus 12 letter 1d467 equals minus 5431. 32. 12 letter 1d465 minus 14 letter 1d466 plus 34 letter 1d467 equals 0 14 letter 1d465 minus 110 letter 1d466 plus 25 letter 1d467 equals minus 218 letter 1d465 plus 15 letter 1d466 minus 18 letter 1d467 equals 233. 45 letter 1d465 minus 78 letter 1d466 plus 12 letter 1d467 equals 1 minus 45 letter 1d465 minus 34 letter 1d466 plus 13 letter 1d467 equals minus 8 minus 25 letter 1d465 minus 78 letter 1d466 plus 12 letter 1d467 equals minus 534. Minus 13 letter 1d465 minus 18 letter 1d466 plus 16 letter 1d467 equals minus 43 minus 23 letter 1d465 minus 78 letter 1d466 plus 13 letter 1d467 equals minus 233 minus 13 letter 1d465 minus 58 letter 1d466 plus 56 letter 1d467 equals 035. Minus 14 letter 1d465 minus 54 letter 1d466 plus 52 letter 1d467 equals minus 5 minus 12 letter 1d465 minus 53 letter 1d466 plus 54 letter 1d467 equals 5,512 minus 13 letter 1d465 minus 13 letter 1d466 plus 13 letter 1d467 equals 5336. 140 letter 1d465 plus 160 letter 1d466 plus 180 letter 1d467 equals 1,100 minus 12 letter 1d465 minus 13 letter 1d466 minus 14 letter 1d467 equals minus 1,538 letter 1d465 plus 312 letter 1d466 plus 316 letter 1d467 eq. 37. 0. 1 letter 1d465 minus 0. 2 y plus 0. 3 letter 1d467 equals 20. 5 letter 1d465 minus 0. 1 y plus 0. 4 letter 1d467 equals 80. 7 letter 1d465 minus 0. 2 y plus 0. 3 letter 1d467 equals 838. 2x plus 0. 1 letter 1d466 minus 0. 3 letter 1d467 equals 0. 20. 8x plus 0. 4 letter 1d466 minus 1. 2 letter 1d467 equals 0. 11. 6x plus 0. 8 letter 1d466 minus 2. 4 letter 1d467 equals 0. 239. 1. 1x plus 0. 7 letter 1d466 minus 3. 1 letter 1d467 equals minus 1. 792. 1x plus 0. 5 letter 1d466 minus 1. 6 letter 1d467 equals minus 0. 130. 5x plus 0. 4 letter 1d466 minus 0. 5 letter 1d467 equals minus 0. 740. 0. 5 letter 1d465 minus 0. 5y plus 0. 5 letter 1d467 equals 100. 2 letter 1d465 minus 0. 2y plus 0. 2 letter 1d467 equals 40. 1 letter 1d465 minus 0. 1y plus 0. 1 letter 1d467 equals 241. 0. 1x plus 0. 2y plus 0. 3 letter 1d467 equals 0. 370. 1 letter 1d465 minus 0. 2 letter 1d466 minus 0. 3 letter 1d467 equals minus 0. 270. 5 letter 1d465 minus 0. 1 letter 1d466 minus 0. 3 letter 1d467 equals minus 0. 342. 0. 5 letter 1d465 minus 0. 5 letter 1d466 minus 0. 3 letter 1d467 equals 0. 130. 4 letter 1d465 minus 0. 1 letter 1d466 minus 0. 3 letter 1d467 equals 0. 110. 2 letter 1d465 minus 0. 8 letter 1d466 minus 0. 9 letter 1d467 equals minus 0. 3243. 5x plus 0. 2 letter 1d466 minus 0. 3 letter 1d467 equals 10. 4 letter 1d465 minus 0. 6 y plus 0. 7 letter 1d467 equals 0. 80. 3 letter 1d465 minus 0. 1 letter 1d466 minus 0. 9 letter 1d467 equals 0. 644. 0. 3x plus 0. 3y plus 0. 5 letter 1d467 equals 0. 60. 4x plus 0. 4y plus 0. 4 letter 1d467 equals 1. 80. 4x plus 0. 2y plus 0. 1 letter 1d467 equals 1. 645. 8x plus 0. 8y plus 0. 8 letter 1d467 equals 2. 40. 3 letter 1d465 minus 0. 5y plus 0. 2 letter 1d467 equals 0 0. 1x plus 0. 2y plus 0. 3 letter 1d467 equals 0. 6 extensions for the following exercises. Solve the system for x, y, and z. 46. Letter 1d465 plus letter 1d466 plus letter 1d467 equals 3 letter 1d465 minus 12 plus letter 1d466 minus 32 plus letter 1d467 plus 12 equals 0 letter 1d465 minus 23 plus letter 1d466 plus 43 plus letter 1d467 minus 33 equals 2347. 5 letter 1d465 minus 3 letter 1d466 minus letter 1d467 plus 12 equals 126 letter 1d465 plus letter 1d466 minus 92 plus 2 letter 1d467 equals minus 3 letter 1d465 plus 82 minus 4 letter 1d466 plus letter 1d467 equals 448. Letter 1d465 plus 47 minus letter 1d466 minus 16 plus letter 1d467 plus 23 equals 1 letter 1d465 minus 24 plus letter 1d466 plus 18 minus letter 1d467 plus 812 equals 0 letter 1d465 plus 63 minus letter 1d466 plus 23 plus letter 1d467 plus 42 equals 349. Letter 1d465 minus 36 plus letter 1d466 plus 22 minus letter 1d467 minus 33 equals 2 letter 1d465 plus 24 plus letter 1d466 minus 52 plus letter 1d467 plus 42 equals 1 letter 1d465 plus 62 minus letter 1d466 minus 32 plus letter 1d467 plus 1 equals 950. Letter 1d465 minus 13 plus letter 1d466 plus 34 plus letter 1d467 plus 26 equals 14 letter 1d465 plus 3 letter 1d466 minus 2 letter 1d467 equals 110. 2x plus 0. 0, 15 letter 1d466 minus 0. 0, 1 letter 1d467 equals 0. 65 real-world applications 51. 3 even numbers sum up to 108. The smaller is half the larger, and the middle number is 30 for the larger. What are the 3 numbers? 52. 3 numbers sum up to 147. The smallest number is half the middle number, which is half the largest number. What are the 3 numbers? 53. At a family reunion, there were only blood relatives, consisting of children, parents, and grandparents in attendance. There were 400 people total. There were twice as many parents as grandparents, and 50 more children than parents. How many children, parents, and grandparents were in attendance? 54. An animal shelter has a total of 350 animals comprised of cats, dogs, and rabbits. If the number of rabbits is 5 less than 1/2 the number of cats, and there are 20 more cats than dogs, how many of each animal are at the shelter? 55. Your roommate, Shani, offered to buy groceries for you and your other roommate. The total bill was $82. She forgot to save the individual receipts, but remembered that your groceries were $0. 5 cheaper than half of her groceries, and that your other roommate's groceries were $2. $10 more than your groceries. How much was each of your share of the groceries? 56. Your roommate, John, offered to buy household supplies for you and your other roommate. You live near the border of 3 states, each of which has a different sales tax. The total amount of money spent was $100, $75. Your supplies were bought with 5% tax, John, S with 8% tax, and your third roommate, S with 9% sales tax. The total amount of money spent without taxes is $93, $50. If your supplies before tax were $1 more than half of what your third roommate's supplies were before tax, how much did each of you spend? Give your answer both with and without taxes. 57. 3 coworkers work for the same employer. Their jobs are warehouse manager, office manager, and truck driver. The sum of the annual salaries of the warehouse manager and office manager is $82,000. The office manager makes $4,000 more than the truck driver annually. The annual salaries of the warehouse manager and the truck driver total $78,000. What is the annual salary of each of the coworkers? 58. At a carnival, $2,914. $25 in receipts were taken at the end of the day. The cost of a child's ticket was $20, $50, an adult ticket was $29, $75, and a senior citizen ticket was $15, $25. There were twice as many senior citizens as adults in attendance and 20 more children than senior citizens. How many children, adult, and senior citizen tickets were sold? 59. A local band sells out for their concert. They sell all 1,175 tickets for a total purse of $28,112. 50. The tickets were priced at $20 for student tickets, $22, $50 for children, and $29 for adult tickets. If the band sold twice as many adult as children tickets, how many of each type was sold? 60. In a bag, a child has 325 coins worth $19, $50. There were 3 types of coins: pennies, nickels, and dimes. If the bag contained the same number of nickels as dimes, how many of each type of coin was in the bag? 61. Last year, at Havens Pond Car Dealership, for a particular model of BMW, Jeep, and Toyota, one could purchase all 3 cars for a total of $140,000. This year, due to inflation, the same cars would cost $151,830. The cost of the BMW increased by 8%, the Jeep by 5%, and the Toyota by 12%. If the price of last year's Jeep was $7,000 less than the price of last year's BMW, what was the price of each of the 3 cars last year? 62. When his youngest child moved out, Diender sold his home and made 3 investments using gains from the sale. He invested $80,500 into 3 accounts, one that paid 4% simple interest, one that paid 318% simple interest, and one that paid 212% simple interest. He earned $2,670 interest at the end of 1 year. If the amount of the money invested in the second account was 4 times the amount invested in the third account, how much was invested in each account? 63. You inherit $1 million. You invest it all in 3 accounts for 1 year. The first account pays 3% compounded annually, the second account pays 4% compounded annually, and the third account pays 2% compounded annually. After 1 year, you earn $34,000 in interest. If you invest 4 times the money into the account that pays 3% compared to 2%, how much did you invest in each account? 64. An entrepreneur sells a portion of their business for $100,000 and invests it all in 3 accounts for 1 year. The first account pays 4% compounded annually, the second account pays 3% compounded annually, and the third account pays 2% compounded annually. After 1 year, the entrepreneur earns $3,650 in interest. If they invested 5 times the money in the account that pays 4% compared to 3%, how much did they invest in each account? 65. The top 3 countries in oil consumption in a certain year are as follows: the United States, Japan, and China. In millions of barrels per day, the 3 top countries consumed 39.8% of the world's consumed oil. The United States consumed 0.7% more than 4 times China's consumption. The United States consumed 5% more than triple Japan's consumption. What percent of the world oil consumption did the United States, Japan, and China consume? 166. The top 3 countries in oil production in the same year are Saudi Arabia, the United States, and Russia. In millions of barrels per day, the top 3 countries produced 31.4% of the world's produced oil. Saudi Arabia and the United States combined for 22.1% of the world's production, and Saudi Arabia produced 2% more oil than Russia. What percent of the world oil production did Saudi Arabia, the United States, and Russia produce? 267. The top 3 sources of oil imports for the United States in the same year were Saudi Arabia, Mexico, and Canada. The 3 top countries accounted for 47% of oil imports. The United States imported 1.8% more from Saudi Arabia than they did from Mexico, and 1.7% more from Saudi Arabia than they did from Canada. What percent of the United States oil imports were from these 3 countries? 368. The top 3 oil producers in the United States in a certain year are the Gulf of Mexico, Texas, and Alaska. The 3 regions were responsible for 64% of the United States oil production. The Gulf of Mexico and Texas combined for 47% of oil production. Texas produced 3% more than Alaska. What percent of United States oil production came from these regions? 469. At one time, in the United States, 398 species of animals were on the endangered species list. The top groups were mammals, birds, and fish, which comprised 55% of the endangered species. Birds accounted for 0.7% more than fish, and fish accounted for 1.5% more than mammals. What percent of the endangered species came from mammals, birds, and fish? 70. Meat consumption in the United States can be broken into 3 categories: red meat, poultry, and fish. If fish makes up 4% less than 1/4 of poultry consumption, and red meat consumption is 18.2% higher than poultry consumption, what are the percentages of meat consumption? Learning objectives. In this section, you will solve a system of nonlinear equations using substitution, solve a system of nonlinear equations using elimination, graph a nonlinear inequality, graph a system of nonlinear inequalities. Halley's Comet, Figure 1, orbits the Sun about once every 75 years. Its path can be considered to be a very elongated ellipse. Other comets follow similar paths in space. These orbital paths can be studied using systems of equations. These systems, however, are different from the ones we considered in the previous section because the equations are not linear. Figure 1, Halley's Comet, credit NASA Blueshift/Flickr. In this section, we will consider the intersection of a parabola and a line, a circle and a line, and a circle and an ellipse. The methods for solving systems of nonlinear equations are similar to those for linear equations. Solving a system of nonlinear equations using substitution. A system of nonlinear equations is a system of 2 or more equations in 2 or more variables containing at least one equation that is not linear. Recall that a linear equation can take the form letter 1d434 letter 1d465 plus letter 1d435 letter 1d466 plus letter 1d436 equals 0. Any equation that cannot be written in this form in nonlinear. The substitution method we used for linear systems is the same method we will use for nonlinear systems. We solve one equation for one variable and then substitute the result into the second equation to solve for another variable, and so on. There is, however, a variation in the possible outcomes. Intersection of a parabola and a line. There are 3 possible types of solutions for a system of nonlinear equations involving a parabola and a line. Possible types of solutions for points of intersection of a parabola and a line. Figure 2 illustrates possible solution sets for a system of equations involving a parabola and a line. No solution. The line will never intersect the parabola. One solution. The line is tangent to the parabola and intersects the parabola at exactly one point. Two solutions. The line crosses on the inside of the parabola and intersects the parabola at 2 points. Figure 2. How to. Given a system of equations containing a line and a parabola, find the solution. Solve the linear equation for one of the variables. Substitute the expression obtained in step 1 into the parabola equation. Solve for the remaining variable. Check your solutions in both equations. Example 1. Solving a system of nonlinear equations, representing a parabola and a line. Solve the system of equations. Letter 1d465 minus letter 1d466 equals minus 1 letter 1d466 equals letter 1d465 2 plus 1. Solution. Solve the first equation for letter 1d465, and then substitute the resulting expression into the second equation. Letter 1d465 minus letter 1d466 equals minus 1 letter 1d465 equals letter 1d466 minus 1 letter 1d466 equals letter 1d465 2 plus 1 letter 1d466 equals letter 1d466 minus 1, 2 plus 1. Solve for x. Substitute expression for x, expand the equation, and set it equal to 0. Letter 1d466 equals letter 1d466 minus 1, 2 plus 1 equals letter 1d466 2 minus 2 letter 1d466 plus 1 equals letter 1d466 2 minus 2 letter 1d466 plus 20 equals letter 1d466 2 minus 3 letter 1d466 plus 2 equals letter 1d466 minus 2. Letter 1d466 minus 1. Solving for letter 1d466 gives letter 1d466 equals 2, and letter 1d466 equals 1. Next, substitute each value for letter 1d466 into the first equation to solve for letter 1d465. Always substitute the value into the linear equation to check for extraneous solutions. Letter 1d465 equals 1 letter 1d465 minus 1 equals minus 1. The solutions are 1, 2, and 0, 1, which can be verified by substituting these x, y values into both of the original equations. See Figure 3, Figure 3. Q&A. Could we have substituted values for letter 1d466 into the second equation to solve for letter 1d465? In example 1, yes, but because letter 1d465 is squared in the second equation, this could give us extraneous solutions for letter 1d465. For letter 1d466 equals 1, letter 1d466 equals letter 1d465 2, plus 11 equals letter 1d465 2, plus 1 letter 1d465 2 equals 0 letter 1d465 equals plus 0 square equals 0. This gives us the same value as in the solution. For letter 1d466 equals 2, letter 1d466 equals letter 1d465 2, plus 12 equals letter 1d465 2, plus 1 letter 1d465 2 equals 1 letter 1d465 equals plus 1 square equals plus 1. Notice that minus 1 is an extraneous solution. Try it 1. Solve the given system of equations by substitution. 3 letter 1d465 minus letter 1d466 to letter 1d465, 2 minus letter 1d466 equals minus 20. Intersection of a circle and a line. Just as with a parabola and a line, there are 3 possible outcomes when solving a system of equations representing a circle and a line. Possible types of solutions for the points of intersection of a circle and a line. Figure 4 illustrates possible solution sets for a system of equations involving a circle and a line. No solution. The line does not intersect the circle. One solution. The line is tangent to the circle and intersects the circle at exactly 1 point. Two solutions. The line crosses the circle and intersects it at 2 points. Figure 4. How to. Given a system of equations containing a line and a circle, find the solution. Solve the linear equation for one of the variables. Substitute the expression obtained in step 1 into the equation for the circle. Solve for the remaining variable. Check your solutions in both equations. Example 2. Finding the intersection of a circle and a line by substitution. Find the intersection of the given circle and the given line by substitution. Letter 1D4652 plus letter 1D4662 equals 5 letter 1D466 equals 3 letter 1D465 minus 5. Solution. One of the equations has already been solved for letter 1D466. We will substitute letter 1D466 equals 3 letter 1D465 minus 5 into the equation for the circle. Letter 1D4652 plus 3 letter 1D465 minus 52 equals 5 letter 1D4652 plus 9 letter 1D4652 minus 30 letter 1D465 plus 25 equals 510 letter 1D4652 minus 30 letter 1D465 plus 20 equals 0. Now, we factor and solve for letter 1D465. 10 letter 1D465 2 minus 3 letter 1D465 plus 2 equals 0 10 letter 1D465 minus 2. Letter 1D465 minus 1 equals 0 letter 1D465 equals 2 letter 1D465 equals 1. Substitute the two x values into the original linear equation to solve for letter 1D466. Letter 1D466 equals 3. 2 minus 5 equals 1 letter 1D466 equals 3. 1 minus 5 equals minus 2. The line intersects the circle at 21 and 1 minus 2, which can be verified by substituting these xy values into both of the original equations. See Figure 5, Figure 5. Try it too. Solve the system of nonlinear equations. x2 plus white letter 1D465 minus 3 letter 1D466 equals 10 minus 10. Solving a system of nonlinear equations using elimination. We have seen that substitution is often the preferred method when a system of equations includes a linear equation and a nonlinear equation. However, when both equations in the system have like variables of the second degree, solving them using elimination by addition is often easier than substitution. Generally, elimination is a far simpler method when the system involves only two equations in two variables, a 2x2 system, rather than a 3x3 system, as there are fewer steps. As an example, we will investigate the possible types of solutions when solving a system of equations representing a circle and an ellipse. Possible types of solutions for the points of intersection of a circle and an ellipse. Figure 6 illustrates possible solution sets for a system of equations involving a circle and an ellipse. No solution. The circle and ellipse do not intersect. One shape is inside the other or the circle, and the ellipse are a distance away from the other. One solution. The circle and ellipse are tangent to each other and intersect at exactly one point. Two solutions. The circle and the ellipse intersect at 2 points. 3 solutions. The circle and the ellipse intersect at 3 points. 4 solutions. The circle and the ellipse intersect at 4 points. Figure 6. Example 3. Solving a system of nonlinear equations representing a circle and an ellipse. Solve the system of nonlinear equations. Letter 1D4652 plus letter 1D4662 equals 263 letter 1D4652 plus 25 letter 1D4662 equals 100. 1, 2. Solution. Let's begin by multiplying equation 1 by minus 3 and adding it to equation 2. Minus 3, letter 1D4652 plus letter 1D4662 equals minus 3. 26. Minus 3 letter 1D4652 minus 3 letter 1D4662 equals minus 78 3 letter 1D4652 plus 25 letter 1D4662 equals 122 letter 1D4662 equals 22. After we add the two equations together, we solve for letter 1D466. Letter 1D4662 equals 1 letter 1D466 equals plus 1 square equals plus 1. Substitute letter 1D466 equals plus 1 into one of the equations and solve for letter 1D465. Letter 1D4652 plus 1 2 equals 26 letter 1D4652 plus 1 equals 26 letter 1D4652 equals 25 letter 1D465 equals plus 25 square equals plus 5 letter 1D4652 plus minus 1 2 equals 26 letter 1D4652 plus 1 equals 26 letter 1D4652 equals 25 equals plus 5. There are 4 solutions. 5 1 minus 5 1, 5 minus 1, and minus 5 minus 1 See Figure 7. Figure 7. Try it 3. Find the solution, set for the given system, of nonlinear equations. 4x2 plus white letter 1d4652 plus letter 1d4662 equals 1310. Graphing a nonlinear inequality. All of the equations in the systems that we have encountered so far have involved equalities, but we may also encounter systems that involve inequalities. We have already learned to graph linear inequalities by graphing the corresponding equation, and then shading the region represented by the inequality symbol. Now, we will follow similar steps to graph a nonlinear inequality so that we can learn to solve systems of nonlinear inequalities. A nonlinear inequality is an inequality containing a nonlinear expression. Graphing a nonlinear inequality is much like graphing a linear inequality. Recall that when the inequality is greater than letter 1d466 letter 1d44e, or less than letter 1d466 letter 1d44e, the graph is drawn with a dashed line. When the inequality is greater than or equal to letter 1d466 greater or equal to letter 1d44e, or less than or equal to letter 1d466 less or equal to letter 1d44e, the graph is drawn with a solid line. The graphs will create regions in the plane, and we will test each region for a solution. If one point in the region works, the whole region works. That is the region we shade. See Figure 8. Figure 8a, an example of letter 1d466 letter 1d44e. B, an example of letter 1d466 greater or equal to letter 1d44e. C, an example of letter 1d466 letter 1d44e. D, an example of letter 1d466 less or equal to letter 1d44e. How to? Given an inequality bounded by a parabola, sketch a graph. Graph the parabola as if it were an equation. This is the boundary for the region that is the solution set. If the boundary is included in the region, the operator is less or equal to, or greater or equal to. The parabola is graphed as a solid line. If the boundary is not included in the region, the operator is, or the parabola is graphed as a dashed line. Test a point in one of the regions to determine whether it satisfies the inequality statement. If the statement is true, the solution set is the region including the point. If the statement is false, the solution set is the region on the other side of the boundary line. Shade the region representing the solution set. Example 4. Graphing an inequality for a parabola. Graph the inequality letter 1d466 letter 1d4652 plus 1. Solution. First, graph the corresponding equation letter 1d466 equals letter 1d4652 plus 1. Since letter 1d466 letter 1d4652 plus 1 has a greater than symbol, we draw the graph with a dashed line. Then we choose points to test both inside and outside the parabola. Let's test the points 2 and 20. One point is clearly inside the parabola, and the other point is clearly outside. Letter 1d466 letter 1d4652 plus 12, 0, 2 plus 12, 10, 2, 2 plus 10, 5, true, false. The graph is shown in Figure 9. We can see that the solution set consists of all points inside the parabola, but not on the graph itself. Figure 9. Graphing a system of nonlinear inequalities. Now that we have learned to graph nonlinear inequalities, we can learn how to graph systems of nonlinear inequalities. A system of nonlinear inequalities is a system of two or more inequalities in two or more variables containing at least one inequality that is not linear. Graphing a system of nonlinear inequalities is similar to graphing a system of linear inequalities. The difference is that our graph may result in more shaded regions that represent a solution than we find in a system of linear inequalities. The solution to a nonlinear system of inequalities is the region of the graph where the shaded regions of the graph of each inequality overlap, or where the regions intersect, called the feasible region. How to? Given a system of nonlinear inequalities, sketch a graph. Find the intersection points by solving the corresponding system of nonlinear equations. Graph the nonlinear equations. Find the shaded regions of each inequality. Identify the feasible region as the intersection of the shaded regions of each inequality, or the set of points common to each inequality. Example 5. Graphing a system of inequalities. Graph the given system of inequalities. letter 1d4652 minus letter 1d466, less or equal to 0, 2, letter 1d4652 plus letter 1d466, less or equal to 12. Solution. These two equations are clearly parabolas. We can find the points of intersection by the elimination process. Add both equations and the variable letter 1d466 will be eliminated. Then we solve for letter 1d465. Letter 1d4652 minus letter 1d466 equals 0, 2, letter 1d4652 plus letter 1d466 equals 12, 3, letter 1d4652 equals 12, letter 1d4652 equals 4, letter 1d465 equals plus 2. Substitute the x values into one of the equations and solve for letter 1d466. Letter 1d465 minus letter 1d466 equals 0. 2, 2 minus letter 1d466 equals 0. 4 minus letter 1d466 equals 0. Letter 1d466 equals 4. Minus 2, 2 minus letter 1d466 equals 0. 4 minus letter 1d466 equals 0. Letter 1d466 equals 4. The 2 points of intersection are 2, 4, and minus 2, 4. Notice that the equations can be rewritten as follows. Letter 1d4652 minus letter 1d466 less or equal to 0, letter 1d4652 less or equal to letter 1d466, letter 1d466 greater or equal to letter 1d465, 22, letter 1d4652 plus letter 1d466 less or equal to 12, letter 1d466 less minus 2, letter 1d4652 plus 12. Graph each inequality. See Figure 10. The feasible region is the region between the two equations bounded by 2, letter 1d465, 2 plus letter 1d466, less or equal to 12. On the top, and letter 1d465, 2 minus letter 1d466, less or equal to 0. On the bottom, Figure 10. Try it 4. Graph the given system of inequalities. Letter 1d466, letter 1d465, minus letter 1d466, greater letter 1d465, 2 minus 1 minus 1. Media. Access these online resources for additional instruction and practice with nonlinear equations. Solve a system of nonlinear equations using substitution. Solve a system of nonlinear equations using elimination. 7 3-section exercises. Verbal. 1. Explain whether a system of 2 nonlinear equations can have exactly 2 solutions. What about exactly 3? If not, explain why not. If so, give an example of such a system in graph form and explain why your choice gives 2 or 3 answers. 2. When graphing an inequality, explain why we only need to test one point to determine whether an entire region is the solution. 3. When you graph a system of inequalities, will there always be a feasible region? If so, explain why. If not, give an example of a graph of inequalities that does not have a feasible region. Why does it not have a feasible region? 4. If you graph a revenue and cost function, explain how to determine in what regions there is profit. 5. If you perform your break-even analysis and there is more than one solution, explain how you would determine which x values are profit and which are not. Algebraic. For the following exercises, solve the system of nonlinear equations using substitution. 6. Letter 1d465 plus letter 1d466 equals 4, letter 1d4652 plus letter 1d4662 equals 9. 7. Letter 1d466 equals letter 1d465 minus 3, letter 1d4652 plus letter 1d4662 equals 9. 8. Letter 1d466 equals letter 1d465, letter 1d465 2 plus letter 1d466 equals 9. 9. Letter 1d466 equals minus letter 1d465, letter 1d465 2 plus letter 1d466 equals 9. 10. Letter 1d465 equals 2, letter 1d465 2 minus letter 1d466 equals 9. For the following exercises, solve the system of nonlinear equations using elimination. 11. 4, letter 1d465 2 minus 9, letter 1d466 equals 364, letter 1d465 plus 9, letter 1d466 equals 36. 12. 13. 2, letter 1d465 plus 4, letter 1d466 equals 42 letter 1d465, 2 minus 4 letter 1d4662 equals 25 letter 1d465 minus 10. 14. Letter 1d4662 minus letter 1d465 2 equals 93 letter 1d465 2 plus 2 letter 1d4662 equals 8. 15. Letter 1d465 2 plus letter 1d4662 plus 116 equals 2500 letter 1d466 equals 2 letter 1d465 2. For the following exercises, use any method to solve the system of nonlinear equations. 16. Minus 2 letter 1d465 2 plus letter 1d466 equals minus 5 6 letter 1d465 minus letter 1d466 equals 9. 17. Minus letter 1d465 2 plus letter 1d466 equals 2 minus letter 1d465 plus letter 1d466 equals 2. 18. Letter 1d465 2 plus letter 1d466 2 equals 1 letter 1d466 equals 20 letter 1d465 2 minus 1. 19. Letter 1d465 2 plus letter 1d466 2 equals 1 letter 1d466 equals minus letter 1d465 2. 20. 2 letter 1d465 3 minus letter 1d465 2 equals letter 1d466 letter 1d466 equals 12 minus letter 1d465. 21. 9 letter 1d465 2 plus 25 letter 1d466 2 equals 225. Letter 1d465 minus 62 plus letter 1d466 2 equals 1. 22. Letter 1d465 4 minus letter 1d465 2 equals letter 1d466 letter 1d465 2 plus letter 1d466 equals 0. 23. 2 letter 1d465 3 minus letter 1d465 2 equals letter 1d466 letter 1d465 2 plus letter 1d466 equals 0. For the following exercises, use any method to solve the nonlinear system. 24. Letter 1d465 2 plus letter 1d466 2 equals 9 letter 1d466 equals 3 minus letter 1d465 2. 25. Letter 1d465 2 minus letter 1d466 2 equals 9 letter 1d465 equals 3. 26. Letter 1d465 2 minus letter 1d466 2 equals 9 letter 1d466 equals 3. 27. Letter 1d465 2 minus letter 1d466 2 equals 9 letter 1d465 minus letter 1d466 equals 0. 28. Minus letter 1d465 2 plus letter 1d466 equals 2 minus 4 letter 1d465 plus letter 1d466 equals minus 1. 29. Minus letter 1d465 2 plus letter 1d466 equals 2 letter 1d466 equals minus letter 1d465. 30. Letter 1d465 2 plus letter 1d466 2 equals 25 letter 1d465 2 minus letter 1d466 2 equals 36. 31. Letter 1d465 2 plus letter 1d466 2 equals 1 letter 1d466 2 equals letter 1d465 2. 32. 16 letter 1d465 2 minus 9 letter 1d466 2 plus 144 equals 0 letter 1d466 2 plus letter 1d465 2 equals 16. 33. 3 letter 1d465 2 minus letter 1d466 2 equals 12. Letter 1d465 minus 1 2 plus letter 1d466 2 equals 1. 34. 3 letter 1d465 2 minus letter 1d466 2 equals 12. Letter 1d465 minus 1 2 plus letter 1d466 2 equals 4. 35. 3 letter 1d465 2 minus letter 1d466 2 equals 12 letter 1d465 2 plus letter 1d466 2 equals 16. 36. Letter 1d465 2 minus letter 1d466 2 minus 6 letter 1d465 minus 4 letter 1d466 minus 11 equals 0 minus letter 1d465 2 plus letter 1d466 2 equals 5. 37. letter 1d4652 plus letter 1d466, 2 minus 6 letter 1d466 equals 7 letter 1d4652 plus letter 1d466 equals 1. 38. Letter 1d4652 plus letter 1d466, 2 equals 6, letter 1d465 letter 1d466 equals 1. Graphic. For the following exercises, graph the inequality. 39. Letter 1d4652 plus letter 1d4669. 40. Letter 1d4652 plus letter 1d4662. For the following exercises, graph the system of inequalities. Label all points of intersection. 41. Letter 1d4652 plus letter 1d466, 1 letter 1d466, 2 letter 1d465. 42. Letter 1d4652 plus letter 1d466 minus 5 letter 1d466, 5 letter 1d465 plus 10. 43. Letter 1d4652 plus letter 1d466, 253, letter 1d4652 minus letter 1d466, 212. 44. Letter 1d4652 minus letter 1d466, 2 minus 4 letter 1d4652 plus letter 1d466, 212. 45. Letter 1d4652 plus 3 letter 1d466, 2 163, letter 1d4652 minus letter 1d466, 2 1. Extensions. For the following exercises, graph the inequality. 46. Letter 1d466 greater or equal to letter 1d45 to letter 1d465 letter 1d466 less or equal to ln letter 1d465 plus 5. 47. Letter 1d466 less minus log letter 1d465 letter 1d466 less or equal to letter 1d45 to letter 1d465. For the following exercises, find the solutions to the nonlinear equations with two variables. 48. 4 letter 1d4652 plus 1 letter 1d4662 equals 245 letter 1d4652 minus 2 letter 1d4662 plus 4 equals 0. 49. 6 letter 1d4652 minus 1 letter 1d4662 equals 81 letter 1d4652 minus 6 letter 1d4662 equals 18. 50. Letter 1d465 2 minus letter 1d465 letter 1d466 plus letter 1d466 2 minus 2 equals 0 letter 1d465 plus 3 letter 1d466 equals 4. 51. Letter 1d465 2 minus letter 1d465 letter 1d466 minus 2 letter 1d466 2 minus 6 equals 0 letter 1d465 2 plus letter 1d466 2 equals 1. 52. Letter 1d465 2 plus 4 letter 1d465 letter 1d466 minus 2 letter 1d466 2 minus 6 equals 0 letter 1d465 equals letter 1d466 plus 2. Technology. For the following exercises, solve the system of inequalities. Use a calculator to graph the system to confirm the answer. 53. Letter 1d465 letter 1d466 1 letter 1d466 letter 1d465 square. 54. Letter 1d465 2 plus letter 1d466 3 letter 1d466 2 letter 1d465. Real-world applications. For the following exercises, construct a system of nonlinear equations to describe the given behavior. Then solve for the requested solutions. 55. Two numbers add up to 300. One number is twice the square of the other number. What are the numbers? 56. The squares of two numbers add to 360. The second number is half the value of the first number squared. What are the numbers? 57. A laptop company has discovered their cost and revenue functions for each day. Letter 1d436, letter 1d465, equals 3 letter 1d465, 2 minus 10 letter 1d465 plus 200. And letter 1d445, letter 1d465, equals minus 2 letter 1d465 2 plus 100 letter 1d465 plus 50. If they want to make a profit, what is the range of laptops per day that they should produce? Round to the nearest number which would generate profit. 58. A cell phone company has the following cost and revenue functions. Letter 1d436, letter 1d465, equals 8 letter 1d465, 2 minus 600 letter 1d465 plus 21, 500. And letter 1d445, letter 1d465, equals minus 3 letter 1d465, 2 plus 480 letter 1d465. What is the range of cell phones they should produce each day so there is profit? Round to the nearest number that generates profit. Learning objectives. In this section, you will decompose letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where has only non-repeated linear factors. Decompose letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where has repeated linear factors. Decompose letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where has a non-repeated, irreducible quadratic factor. Decompose letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where has a repeated, irreducible quadratic factor. Earlier in this chapter, we studied systems of 2 equations in 2 variables, systems of 3 equations in 3 variables, and nonlinear systems. Here we introduce another way that systems of equations can be utilized, the decomposition of rational expressions. Fractions can be complicated. Adding a variable in the denominator makes them even more so. The methods studied in this section will help simplify the concept of a rational expression. Decomposing letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where q, x, has only non-repeated linear factors. Recall the algebra regarding adding and subtracting rational expressions. These operations depend on finding a common denominator so that we can write the sum or difference as a single, simplified rational expression. In this section, we will look at partial fraction decomposition, which is the undoing of the procedure to add or subtract rational expressions. In other words, it is a return from the single simplified rational expression to the original expressions, called the partial fraction. For example, suppose we add the following fractions: 2 letter 1d465 minus 3 plus minus 1 letter 1d465 plus 2. We would first need to find a common denominator, letter 1d465 plus 2, letter 1d465 minus 3. Next, we would write each expression with this common denominator and find the sum of the terms. 2 letter 1d465 minus 3, letter 1d465 plus 2 letter 1d465 plus 2, plus minus 1 letter 1d465 plus 2, letter 1d465 minus 3 letter 1d465 minus 3 equals 2 letter 1d465 plus 4 minus letter 1d465 plus 3, letter 1d465 plus 2, letter 1d465 minus 3 equals letter 1d465 plus 7 letter 1d465, 2 minus letter 1d465 minus 6. Partial fraction decomposition is the reverse of this procedure. We would start with the solution and rewrite. Decompose it as the sum of 2 fractions. Letter 1d465 plus 7 letter 1d465, 2 minus letter 1d465 minus 6. Simplifism equals 2 letter 1d465 minus 3 plus minus 1 letter 1d465 plus 2 partial fraction decomposition. We will investigate rational expressions with linear factors and quadratic factors in the denominator, where the degree of the numerator is less than the degree of the denominator. Regardless of the type of expression we are decomposing, the first and most important thing to do is factor the denominator. When the denominator of the simplified expression contains distinct linear factors, it is likely that each of the original rational expressions, which were added or subtracted, had one of the linear factors as the denominator. In other words, using the example above, the factors of letter 1d465, 2 minus letter 1d465 minus 6, are letter 1d465 minus 3, letter 1d465 plus 2, the denominators of the decomposed rational expression. So we will rewrite the simplified form as the sum of individual fractions and use a variable for each numerator. Then, we will solve for each numerator using one of several methods available for partial fraction decomposition. Partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, letter 1d444, letter 1d465, has non-repeated linear factors. The partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, when has non-repeated linear factors and the degree of letter 1d443, letter 1d465, is less than the degree of letter 1d444, letter 1d465, is letter 1d443, letter 1d465, letter 1d444, letter 1d465 equals letter 1d434 letter 1d44e 1, letter 1d465 plus letter 1d44f 1, plus letter 1d434 2, letter 1d44e 2, letter 1d465 plus letter 1d44f 2, plus letter 1d434 3, letter 1d44e 3, letter 1d465 plus letter 1d44f 3, plus letter 1d434, letter 1d45b, letter 1d44, letter 1d45b, letter 1d465, plus letter 1d44f, letter 1d45b. How to, given a rational expression with distinct linear factors in the denominator, decompose it. Use a variable for the original numerators, usually a, b, or c, depending on the number of factors, placing each variable over a single factor. For the purpose of this definition, we use an for each numerator, letter 1d443, letter 1d465, letter 1d444, letter 1d465 equals letter 1d434 1, letter 1d44e 1, letter 1d465 plus letter 1d44f 1, plus letter 1d434 2, letter 1d44e 2, letter 1d465 plus letter 1d44f 2, plus letter 1d434, letter 1d45b, letter 1d44, letter 1d45b, letter 1d465, plus letter 1d44f, letter 1d45b. Multiply both sides of the equation by the common denominator to eliminate fractions. Expand the right side of the equation and collect like terms. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Example 1. Decomposing a rational function with distinct linear factors. Decompose the given rational expression with distinct linear factors. 3, letter 1d465, letter 1d465 plus 2, letter 1d465 minus 1. Solution. We will separate the denominator factors and give each numerator a symbolic label, like AB. Or C. 3, letter 1d465, letter 1d465 plus 2, letter 1d465 minus 1 equals letter 1d434, letter 1d465 plus 2, plus letter 1d435, letter 1d465 minus 1. Multiply both sides of the equation by the common denominator to eliminate the fractions. Letter 1d465 plus 2, letter 1d465 minus 1, 3, letter 1d465, letter 1d465 plus 2, letter 1d465 minus 1 equals letter 1d465 plus 2, letter 1d465 minus 1, letter 1d434, letter 1d465 plus 2 plus letter 1d465 plus 2, letter 1d465 minus 1, letter 1d435, letter 1d465 minus 1. The resulting equation is 3, letter 1d465 equals letter 1d434, letter 1d465 minus 1 plus letter 1d435, letter 1d465 plus 2. Expand the right side of the equation and collect like terms. 3, letter 1d465 equals letter 1d434, letter 1d465 minus letter 1d434 plus letter 1d435, letter 1d465 plus 2, letter 1d435, 3, letter 1d465 equals letter 1d434 plus letter 1d435, letter 1d465 minus letter 1d434 plus 2, letter 1d435. Set up a system of equations associating corresponding coefficients. 3 equals letter 1d434 plus letter 1d435, 0 equals minus letter 1d434 plus 2, letter 1d435. Add the two equations and solve for b. 3 equals letter 1d434 plus letter 1d435, 0 equals minus letter 1d434 plus 2, letter 1d435, 3 equals 0 plus 3, letter 1d435, 1 equals letter 1d435. Substitute letter 1d435 equals into one of the original equations in the system. 3 equals letter 1d434 plus 12 equals letter 1d434. Thus, the partial fraction decomposition is 3 letter 1d465, letter 1d465 plus 2 letter 1d465 minus 1 equals 2 letter 1d465 plus 2 plus 1 letter 1d465 minus 1. Another method to use to solve for A or B is by considering the equation that resulted from eliminating the fractions and substituting a value for x. That will make either the A or B term equal 0. If we let letter 1d465 equals 1, the A term becomes 0, and we can simply solve for B. 3 letter 1d465 equals letter 1d434, letter 1d465 minus 1 plus letter 1d435, letter 1d465 plus 2, 3, 1 equals letter 1d434, 1 minus 1 plus letter 1d435, 1 plus 2 plus 3b1 equals letter 1d435. Next, either substitute letter 1d435 equals 1 into the equation and solve for A, or make the B term 0 by substituting letter 1d465 equals minus 2 into the equation. 3 letter 1d465 equals letter 1d434, letter 1d465 minus 1 plus letter 1d435, letter 1d465 plus 2, 3, minus 2 equals letter 1d434, minus 2 minus 1 plus letter 1d435, minus 2, plus 2, minus 6 equals minus 3 letter 1d434, plus 0 minus 6 minus 3 equals letter 1d434, 2 equals letter 1d434. We obtain the same values for A and B using either method, so the decompositions are the same using either method. 3 letter 1d465, letter 1d465 plus 2 letter 1d465 minus 1 equals 2 letter 1d465 plus 2 plus 1 letter 1d465 minus 1. Although this method is not seen very often in textbooks, we present it here as an alternative that may make some partial fraction decompositions easier. It is known as the Heaviside method, named after Charles Heaviside, a pioneer in the study of electronics. Try it one. Find the partial fraction decomposition of the following expression: letter 1d465, letter 1d465 minus 3, letter 1d465 minus 2. Decomposing letter 1d443, letter 1d465, letter 1d444, letter 1d465. Where Q(x) has repeated linear factors, some fractions we may come across are special cases that we can decompose into partial fractions with repeated linear factors. We must remember that we account for repeated factors by writing each factor in increasing powers. Partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, letter 1d444, letter 1d465, has repeated linear factors. The partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, when has a repeated linear factor occurring n times and the degree of letter 1d443, letter 1d465, is less than the degree of letter 1d444, letter 1d465, is letter 1d443, letter 1d465, letter 1d444. Letter 1d465 equals letter 1d434, 1, letter 1d44, letter 1d465, plus letter 1d44f, plus letter 1d434, 2, letter 1d44, letter 1d465, plus letter 1d44f, 2, plus letter 1d434, 3, letter 1d44, letter 1d465, plus letter 1d44f, 3, plus letter 1d434 let. Write the denominator powers in increasing order. How to: given a rational expression with repeated linear factors, decompose it. Use a variable like AB or C for the numerators and account for increasing powers of the denominators. Letter 1d443, letter 1d465, letter 1d444, letter 1d465 equals letter 1d434, 1, letter 1d44, letter 1d465, plus letter 1d44f, plus letter 1d434, 2, letter 1d44, letter 1d465, plus letter 1d44f, 2 plus letter 1d434, letter 1d45b, letter 1d44, letter 1d465, plus letter 1d44f, letter 1d45b. Multiply both sides of the equation by the common denominator to eliminate fractions. Expand the right side of the equation and collect like terms. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Example 2. Decomposing with repeated linear factors. Decompose the given rational expression with repeated linear factors. Minus letter 1d4652 plus 2 letter 1d465 plus 4 letter 1d465 3 minus 4 letter 1d465 2 plus 4 letter 1d465. Solution. The denominator factors are letter 1d465, letter 1d465 minus 2 2. To allow for the repeated factor of letter 1d465 minus 2, the decomposition will include three denominators, letter 1d465, letter 1d465 minus 2, and letter 1d465 minus 2, 2. Thus, minus letter 1d465 2 plus 2 letter 1d465 plus 4 letter 1d465 3 minus 4 letter 1d465 2 plus 4 letter 1d465 equals letter 1d434 letter 1d465 plus letter 1d435. Letter 1d465 minus 2 plus letter 1d436. Letter 1d465 minus 2, 2. Next, we multiply both sides by the common denominator. Letter 1d465. Letter 1d465 minus 2 2 minus letter 1d465 2 plus 2 letter 1d465 plus 4 letter 1d465. Letter 1d465 minus 2 equals letter 1d434 letter 1d465 plus letter 1d435 letter 1d465 minus 2 plus letter 1d436. Letter 1d465 minus 2 letter 1d465. Letter 1d465 minus 2 2. Minus letter 1d465 2 plus 2 letter 1d465 plus 4 equals letter 1d434. Letter 1d465 minus 2 2 plus letter 1d435 letter 1d465. Letter 1d465 minus 2 plus letter 1d436 letter 1d465. On the right side of the equation, we expand and collect like terms. Minus letter 1d465 2 plus 2 letter 1d465 plus 4 equals letter 1d434. Letter 1d465 2 minus 4 letter 1d465 plus 4 plus letter 1d435. Letter 1d465 2 minus 2 letter 1d465 plus letter 1d436 letter 1d465 equals letter 1d434 letter 1d465 2 minus 4 letter 1d434 letter 1d465 plus 4 letter 1d434 plus letter 1d435 letter 1d465 2 minus 2 letter 1d435 letter 1d465 plus letter 1d436 letter 1d465. Letter 1d434 plus letter 1d435. Letter 1d465 2 plus minus 4 letter 1d434 minus 2 letter 1d435 plus letter 1d436. Letter 1d465 plus 4 letter 1d434. Next, we compare the coefficients of both sides. This will give the system of equations in three variables. Minus letter 1d465 2 plus 2 letter 1d465 plus 4 equals letter 1d434 plus letter 1d435. Letter 1d465 2 plus minus 4 letter 1d434 minus 2 letter 1d435 plus letter 1d436. Letter 1d465 plus 4 letter 1d434. Letter 1d434 plus letter 1d435 equals minus 1 minus 4 letter 1d434 minus 2 letter 1d435 plus letter 1d436 equals 24 letter 1d434 equals 4, 1, 2, 3. Solving for A, we have 4 letter 1d434 equals 4 letter 1d434 equals 1. Substitute letter 1d434 equals 1 into equation 1. Letter 1d434 plus letter 1d435 equals minus 1. 1 plus letter 1d435 equals minus 1 letter 1d435 equals minus 2. Then, to solve for C, substitute the values for A and B into equation 2. Minus 4 letter 1d434 minus 2 letter 1d435 plus letter 1d436 equals 2 minus 4. 1 minus 2 minus 2 plus letter 1d436 equals 2 plus 4 plus letter 1d436 equals 2 letter 1d436 equals 2. Thus, minus letter 1d465 2 plus 2 letter 1d465 plus 4 letter 1d465 3 minus 4 letter 1d465 2 plus 4 letter 1d465 equals 1 letter 1d465 minus 2, letter 1d465 minus 2, plus 2, letter 1d465 minus 2, 2. Try it too. Find the partial fraction decomposition of the expression with repeated linear factors. 6 letter 1d465 minus 11, letter 1d465 minus 1, 2. Decomposing letter 1d443, letter 1d465, letter 1d444, letter 1d465, where q, x, has a non-repeated irreducible quadratic factor. So far, we have performed partial fraction decomposition with expressions that have had linear factors in the denominator, and we applied numerators a, b, or c, representing constants. Now we will look at an example where one of the factors in the denominator is a quadratic expression that does not factor. This is referred to as an irreducible quadratic factor. In cases like this, we use a linear numerator, such as letter 1d434, letter 1d465, plus letter 1d435, letter 1d435, letter 1d465, plus letter 1d436, etc. Decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, letter 1d444, letter 1d465, has a non-repeated, irreducible quadratic factor. The partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, such that letter 1d444, letter 1d465, has a non-repeated, irreducible quadratic factor, and the degree of letter 1d443, letter 1d465, is less than the degree of letter 1d444, letter 1d465, is written as letter 1d443, letter 1d465, letter 1d444. Letter 1d465 equals letter 1d434, 1 letter 1d465, plus letter 1d435, 1 letter 1d440, 1 letter 1d465, 2, plus letter 1d44f, 1 letter 1d465, plus letter 1d450, 1 plus letter 1d434 to letter 1d465, plus letter 1d435, 2 letter 1d440 to x, 2, plus b, to letter 1d465, plus letter 1d450, 2 plus letter 1d434, letter 1d45b, letter 1d465, plus letter 1d435, letter 1d45b, letter 1d44, letter 1d45b, letter 1d465, 2 plus letter 1d44f, letter 1d45b, letter 1d465, plus letter 1d450, letter 1d45b. The decomposition may contain more rational expressions if there are linear factors. Each linear factor will have a different constant numerator, a, b, c, and so on. How to? Given a rational expression where the factors of the denominator are distinct, irreducible quadratic factors, decompose it. Use variables such as a, b, or c for the constant numerators over linear factors, and linear expressions such as a1x plus b1a2x plus b2, etc. for the numerators of each quadratic factor in the denominator. Letter 1d443, letter 1d465, letter 1d444. Letter 1d465 equals letter 1d434, letter 1d440, letter 1d465, plus letter 1d44f, plus letter 1d434, 1 letter 1d465, plus letter 1d435, 1 letter 1d440, 1 letter 1d465, 2, plus letter 1d44f, 1 letter 1d465, plus letter 1d450, 1, plus letter 1d43, to letter 1d465, plus letter 1d435, 2, letter 1d440 to x, 2, plus b2. Letter 1d465 plus letter 1d450, 2, plus letter 1d434, letter 1d45b, letter 1d465, plus letter 1d435, letter 1d45b, letter 1d44, letter 1d45b, letter 1d465, 2, plus letter 1d44f, letter 1d45b, letter 1d465, plus letter 1d450, letter 1d45b. Multiply both sides of the equation by the common denominator to eliminate fractions. Expand the right side of the equation and collect like terms. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Example 3. Decomposing letter 1d443, letter 1d465, letter 1d444, letter 1d465. When q, x, contains a non-repeated irreducible quadratic factor, find a partial fraction decomposition of the given expression, 8 letter 1d465, 2, plus 12 letter 1d465 minus 20, letter 1d465 plus 3, letter 1d4652 plus letter 1d465 plus 2. Solution: we have one linear factor and one irreducible quadratic factor in the denominator. So one numerator will be a constant, and the other numerator will be a linear expression. Thus, 8 letter 1d4652 plus 12 letter 1d465 minus 20, letter 1d465 plus 3. Letter 1d4652 plus letter 1d465 plus 2 equals letter 1d434. Letter 1d465 plus 3 plus letter 1d435 letter 1d465 plus letter 1d436. Letter 1d4652 plus letter 1d465 plus 2. We follow the same steps as in previous problems. First, clear the fractions by multiplying both sides of the equation by the common denominator. Letter 1d465 plus 3. Letter 1d4652 plus letter 1d465 plus 2 8 letter 1d4652 plus 12 letter 1d465 minus 20, letter 1d465 plus 3. Letter 1d4652 plus letter 1d465 plus 2 equals letter 1d434. Letter 1d465 plus 3 plus letter 1d435 letter 1d465 plus letter 1d436. Letter 1d465 to 8 letter 1d465 plus 12 letter 1d465 minus 20 equals letter 1d434. Letter 1d465 plus letter 1d465 plus 2 plus letter 1d435 letter 1d465 plus letter 1d436. Letter 1d465 plus 3. Notice we could easily solve for a by choosing a value for x that will make the letter 1d435 letter 1d465 plus letter 1d436 term equal 0. Let letter 1d465 equals minus 3 and substitute it into the equation. 8 letter 1d465 plus 12 letter 1d465 minus 20 equals letter 1d434. Letter 1d465 plus letter 1d465 plus 2 plus letter 1d435 letter 1d465 plus letter 1d436. Letter 1d465 plus 3. 8 minus 3 2 plus 12 minus 3 minus 20 equals letter 1d434. Minus 3 2 plus minus 3 plus 2 plus letter 1d435 minus 3 plus letter 1d436. Minus 3 plus 3, 16 equals 8 letter 1d434 now that we know the value of a. Substitute it back into the equation. Then expand the right side and collect like terms. 8 letter 1d465 plus 12 letter 1d465 minus 20 equals 2, letter 1d465 plus letter 1d465 plus 2 plus letter 1d435 letter 1d465 plus letter 1d436. Letter 1d465 plus 3. 8 letter 1d465 plus 12 letter 1d465 minus 20 equals 2 letter 1d465 plus 2 letter 1d465 plus 4 plus letter 1d4. Setting the coefficients of terms on the right side equal to the coefficients of terms on the left side gives the system of equations. 2 plus letter 1d435 equals 82 plus 3 letter 1d435 plus letter 1d436 equals 12 4 plus 3 letter 1d436 equals minus 21. 2. 3. Solve for b using equation 1 and solve for c using equation 3. 2 plus letter 1d435 equals 8 letter 1d435 equals 64 plus 3 letter 1d436 equals minus 23 letter 1d436 equals minus 24 letter 1d436 equals minus 8. 1. 3. Thus, the partial fraction decomposition of the expression is 8 letter 1d465 plus 12 letter 1d465 minus 20. Letter 1d465 plus 3. Letter 1d465 plus letter 1d465 plus 2 equals 2 letter 1d465 plus 3 plus 6 letter 1d465 minus 8. Letter 1d465 plus letter 1d465 plus 2. Q and A, could we have just set up a system of equations to solve? Example 3. Yes, we could have solved it by setting up a system of equations without solving for A first. The expansion on the right would be 8 letter 1d465 plus 12 letter 1d465 minus 20 equals letter 1d434 letter 1d465 2 plus letter 1d434 letter 1d465 plus 2 letter 1d434 plus letter 1d435 letter 1d465 2 plus 3 letter 1d435 plus letter 1d436 letter 1d465 plus 3 letter 1d436 8 letter 1d465 2 plus 12 letter 1d4s. So the system of equations would be Letter 1d434 plus letter 1d435 equals 8 letter 1d434 plus 3 letter 1d435 plus letter 1d436 equals 122 letter 1d434 plus 3 letter 1d436 equals minus 20. Try it. 3. Find the partial fraction decomposition of the expression with a non-repeating irreducible quadratic factor. 5 letter 1d465 2 minus 6 letter 1d465 plus 7 letter 1d465 minus 1 letter 1d465 2 plus 1 decomposing letter 1d443 letter 1d465 letter 1d444 letter 1d465 when q x has a repeated irreducible quadratic factor. Now that we can decompose a simplified rational expression with an irreducible quadratic factor, we will learn how to do partial fraction decomposition when the simplified rational expression has repeated irreducible quadratic factors. The decomposition will consist of partial fractions with linear numerators over each irreducible quadratic factor represented in increasing powers. Decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465. When qx has a repeated irreducible quadratic factor, the partial fraction decomposition of letter 1d443, letter 1d465, letter 1d444, letter 1d465, when has a repeated irreducible quadratic factor and the degree of letter 1d443, letter 1d465, is less than the degree of letter 1d444, letter 1d465, is letter 1d443, letter 1d465. Letter 1d44, letter 1d465, 2, plus letter 1d44f, letter 1d465, plus letter 1d450, letter 1d45b, equals letter 1d434, 1, letter 1d465, plus letter 1d435, 1. Letter 1d44, letter 1d465, 2, plus letter 1d44f, letter 1d465, plus letter 1d450, plus letter 1d434, 2. Letter 1d465, plus letter 1d435, 2. Letter 1d44, letter 1d465, 2. Plus letter 1d44f, letter 1d465, plus letter 1d4502, plus letter 1d434, 3 letter 1d465, plus letter 1d435, 3 letter 1d44, letter 1d465, 2, plus letter 1d44f, letter 1d465, plus letter 1d450, plus letter 1d434, letter 1. Write the denominators in increasing powers. How to given a rational expression that has a repeated irreducible factor, decompose it. Use variables like a, b, or c for the constant numerators over linear factors, and linear expressions such as a1x plus b1 a2x plus b2, etc. for the numerators of each quadratic factor in the denominator writ in increasing powers, such as letter 1d443, letter 1d465, letter 1d444, letter 1d465 equals letter 1d434, letter 1d44, letter 1d465, plus letter 1d44f, plus letter 1d434, 1 letter 1d465, plus letter 1d435, 1 letter 1d44, letter 1d465, 2 plus letter 1d44f, letter 1d465, plus letter 1d450, plus letter 1d434, 2. Letter 1d465, plus letter 1d435, 2 letter 1d44, letter 1d465, 2 plus letter 1d44f, letter 1d465, plus letter 1d4502, plus letter 1d434, letter 1d45b, plus letter 1d435, letter 1d45b. Letter 1d44, letter 1d465, 2, plus letter 1d44f, letter 1d465, plus letter 1d450, letter 1d45b. Multiply both sides of the equation by the common denominator to eliminate fractions. Expand the right side of the equation and collect like terms. Set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. Example 4. Decomposing a rational function with a repeated irreducible quadratic factor in the denominator. Decompose the given expression that has a repeated irreducible factor in the denominator. Letter 1d465 4 plus letter 1d465 3 plus letter 1d465 2 minus letter 1d465 plus 1 letter 1d465. Letter 1d465 2 plus 1. To solution, the factors of the denominator are letter 1d465, letter 1d465 2 plus 1, and letter 1d465 2 plus 1, 2. Recall that, When a factor in the denominator is a quadratic that includes at least two terms, the numerator must be of the linear form ax plus b. So, let's begin the decomposition. Letter 1 d465 4 plus letter 1 d465 3 plus letter 1 d465 2 minus letter 1 d465 plus 1 letter 1 d465. Letter 1 d465 2 plus 1 2 equals letter 1 d434 letter 1 d465 plus letter 1 d435 letter 1 d465 plus letter 1 d436. Letter 1 d465 2 plus 1 plus letter 1 d437 letter 1 d465 plus letter 1 d438. We eliminate the denominators by multiplying each term by letter 1 d465. Letter 1 d465 2 plus 1, 2. Thus, letter 1 d465 4 plus letter 1 d465 3 plus letter 1 d465 2 minus letter 1 d465 plus 1 equals letter 1 d434. Letter 1 d465 2 plus 1 2 plus letter 1 d435 letter 1 d465 plus letter 1 d436. Letter 1 d465. Letter 1 d465 2 plus 1 plus letter 1 d437 letter 1 d465 plus letter 1 d438. Letter 1 d46. Expand the right side. Letter 1 d465 4 plus letter 1 d465 3 plus letter 1 d465 2 minus letter 1 d465 plus 1 equals letter 1 d434. Letter 1 d465 4 plus 2 letter 1 d465 2 plus 1 plus letter 1 d435 letter 1 d465 4 plus letter 1 d435 letter 1 d465 2 plus letter 1 d436 letter 1 d465 3 plus letter 1 d436 letter 1 d4s equals letter 1 d434 letter 1 d465 4 plus 2 letter 1 d434 letter 1 d465 2 plus letter 1 d434 plus letter 1 d435 letter 1 d465 4 plus letter 1 d435 letter 1 d465 2 plus letter 1 d436 letter 1 d465 3 plus letter 1 d436 letter 1 d465 plus letter 1 d437 letter 1 d465 2 plus letter 1 d438 letter. Now we will collect like terms. Letter 1 d465 4 plus letter 1 d465 3 plus letter 1 d465 2 minus letter 1 d465 plus 1 equals letter 1 d434 plus letter 1 d435 letter 1 d465 4 plus letter 1 d436. Letter 1 d465 3 plus 2 letter 1 d434 plus letter 1 d435 plus letter 1 d437 letter 1 d465 2 plus letter 1 d436 plus letter 1 d43. Set up the system of equations, matching corresponding coefficients on each side of the equal sign. Letter 1 d434 plus letter 1 d435 equals 1 letter 1 d436 equals 12 letter 1 d434 plus letter 1 d435 plus letter 1 d437 equals 1 letter 1 d436 plus letter 1 d438 equals minus 1. We can use substitution from this point. Substitute into the first equation. 1 plus letter 1 d435 equals 1 letter 1 d435 equals 0 substitute, and letter 1 d435 equals 0 into the third equation. 2, 1 plus 0 plus letter 1 d437 equals 1 letter 1 d437 equals minus 1 substitute letter 1 d436 equals 1 into the fourth equation. 1 plus letter 1 d438 equals minus 1 letter 1 d438 equals minus 2. Now, we have solved for all of the unknowns on the right side of the equal sign. We have letter 1 d434 equals 1, letter 1 d435 equals 0, letter 1 d436 equals 1, letter 1 d437 equals minus 1, and letter 1 d438 equals minus 2. We can write the decomposition as follows. Letter 1 d465 4 plus letter 1 d465 3 plus letter 1 d465 2 minus letter 1 d465 plus 1 letter 1 d465. Letter 1 d465 2 plus 1 2 equals 1 letter 1 d465 plus 1. Letter 1 d465 2 plus 1 minus letter 1 d465 plus 2. Letter 1 d465 2 plus 1 2. Try it 4. Find the partial fraction decomposition of the expression with a repeated irreducible. Quadratic factor. Letter 1 d465 3 minus 4 letter 1 d465 2 plus 9 letter 1 d465 minus 5. Letter 1 d465 2 minus 2 letter 1 d465 plus 3 2 media access, these online resources for additional instruction and practice with partial fractions. Partial fraction decomposition with repeated linear factors. Partial fraction decomposition with linear and quadratic factors. 7-4 section, exercises verbal 1. Can any quotient of polynomials be decomposed into at least 2 partial fractions? If so, explain why, and if not, give an example of such a fraction too. Can you explain why a partial fraction decomposition is unique? Hint, think about it as a system of equations. 3. Can you explain how to verify a partial fraction decomposition graphically, for you are unsure if you correctly decompose the partial fraction correctly? Explain how you could double-check your answer. 5. Once you have a system of equations generated by the partial fraction decomposition, can you explain another method to solve it? For example, if you had 7 letter 1d465 plus 133 letter 1d465, 2 plus 8 letter 1d465 plus 15 equals letter 1d434 letter 1d465 plus 1 plus letter 1d435, 3 letter 1d465 plus 5. We eventually simplify to 7 letter 1d465 plus 13 equals letter 1d434, 3 letter 1d465 plus 5, plus letter 1d435, letter 1d465 plus 1. Explain how you could intelligently choose an x value that will eliminate either a or b, and solve for a and b. Algebraic for the following exercises, find the decomposition of the partial fraction for the non-repeating linear factors. 6(5x) plus 16x2 plus 10x plus 24 7. 3 letter 1d465 minus 79, letter 1d465 2 minus 5, letter 1d465 minus 24 8. Minus letter 1d465 minus 24, letter 1d465 2 minus 2, letter 1d465 minus 24 9. 10x plus 47x2 plus 7x plus 10 10 plus 25x plus 25 11. 32 letter 1d465 minus 1120, letter 1d465 2 minus 13, letter 1d465 plus 212. X plus 1x2 plus 7x plus 10 13. 5 letter 1d465, letter 1d465 2 minus 9 14. 10 letter 1d465, letter 1d465 2 minus 25 15. 6 letter 1d465, letter 1d465 2 minus 4 16. 2 letter 1d465 minus 3 letter 1d465 2 minus 6 letter 1d465 plus 5 17. 4 letter 1d465 minus 1 letter 1d465 2 minus letter 1d465 minus 6 18. 4x plus 3x2 plus 8x plus 15 19. 3 letter 1d465 minus 1 letter 1d465 2 minus 5 letter 1d465 plus 6 for the following exercises. Find the decomposition of the partial fraction for the repeating linear factors. 20 minus 5 letter 1d465 minus 19 letter 1d465 plus 4 221. Letter 1d465 letter 1d465 minus 2 22. 7 letter 1d465 plus 14, letter 1d465 plus 3, 223. Minus 24 letter 1d465 minus 27, 4 letter 1d465 plus 5, 224. Minus 24 letter 1d465 minus 27, 6 letter 1d465 minus 7, 225. 5 minus letter 1d465, letter 1d465 minus 7 226. 5x plus 142x2 plus 12x plus 1827. 5 letter 1d465 2 plus 20 letter 1d465 plus 82 letter 1d465. Letter 1d465 plus 1, 228. 4 letter 1d465 2 plus 55 letter 1d465 plus 255 letter 1d465. 3 letter 1d465 plus 5 229. 54 letter 1d465 3 plus 127 letter 1d465 2 plus 80 letter 1d465 plus 162 letter 1d465 2 3 letter 1d465 plus 2 230. Letter 1d465 3 minus 5 letter 1d465 2 plus 12 letter 1d465 plus 144 letter 1d465 2. Letter 1d465 2 plus 12 letter 1d465 plus 36. For the following exercises, find the decomposition of the partial fraction for the irreducible non-repeating quadratic factor. 31. 4 letter 1d4652 plus 6 letter 1d465 plus 11, letter 1d465 plus 2, letter 1d4652 plus letter 1d465 plus 3, 32. 4 letter 1d4652 plus 9 letter 1d465 plus 23, letter 1d465 minus 1. Letter 1d4652 plus 6 letter 1d465 plus 11, 33. Minus 2 letter 1d4652 plus 10 letter 1d465 plus 4, letter 1d465 minus 1. Letter 1d4652 plus 3 letter 1d465 plus 8, 34. Letter 1d4652 plus 3 letter 1d465 plus 1, letter 1d465 plus 1. Letter 1d4652 plus 5 letter 1d465 minus 2, 35. 4 letter 1d4652 plus 17 letter 1d465 minus 1, letter 1d465 plus 3. Letter 1d4652 plus 6 letter 1d465 plus 1, 36. 4 letter 1d4652, letter 1d465 plus 5. Letter 1d4652 plus 7 letter 1d465 minus 5, 37. 4 letter 1d4652 plus 5 letter 1d465 plus 3 letter 1d465 3 minus 138. Minus 5 letter 1d465 218 letter 1d465 minus 4 letter 1d465 3 plus 839. 3 letter 1d465 2 minus 7 letter 1d465 plus 33 letter 1d465 3 plus 2740. Letter 1d465 2 plus 2 letter 1d465 plus 40 letter 1d465 3 minus 12541. 4 letter 1d465 2 plus 4 letter 1d465 plus 128 letter 1d465 3 minus 2742. Minus 50 letter 1d465 2 plus 5 letter 1d465 minus 3125 letter 1d465 3 minus 143. Minus 2 letter 1d465 3 minus 30 letter 1d465 236x plus 216x 4 plus 216x for the following exercises. Find the decomposition of the partial fraction for the irreducible repeating quadratic factor. 44. 3 letter 1d465 3 plus 2 letter 1d465 2 plus 14 letter 1d465 plus 15. Letter 1d465 2 plus 4, 245. Letter 1d465 3 plus 6 letter 1d465 2 plus 5 letter 1d465 plus 9. Letter 1d465 2 plus 1, 246. Letter 1d465 3 minus letter 1d465 2 plus letter 1d465 minus 1. Letter 1d465 2 minus 3, 247. Letter 1d465 2 plus 5 letter 1d465 plus 5. Letter 1d465 plus 2, 248. Letter 1d465 3 plus 2 letter 1d465 2 plus 4 letter 1d465. Letter 1d465 2 plus 2 letter 1d465 plus 9, 249. Letter 1d465 2 plus 25. Letter 1d465 2 plus 3 letter 1d465 plus 25, 250. 2 letter 1d465 3 plus 11 letter 1d465 2 plus 7 letter 1d465 plus 70, 2 letter 1d465 2 plus letter 1d465 plus 14, 251. 5 letter 1d465 plus 2 letter 1d465. Letter 1d465 2 plus 4, 252. Letter 1d465 4 plus letter 1d465 3 plus 8 letter 1d465 2 plus 6 letter 1d465 plus 36 letter 1d465. Letter 1d465 2 plus 6, 253. 2 letter 1d465 minus 9. Letter 1d465 2 minus letter 1d465 2, 54. 5 letter 1d465 3 minus 2 letter 1d465 plus 1 letter 1d465 2 plus 2 letter 1d4652 extensions for the following exercises. Find the partial fraction expansion. 55. Letter 1d4652 plus 4. Letter 1d465 plus 1, 356. Letter 1d465 3 minus 4, letter 1d465 2, plus 5, letter 1d465 plus 4. Letter 1d465 minus 2, 3 for the following exercises. Perform the operation, and then find the partial fraction decomposition. 57. 7 letter 1d465 plus 8 plus 5 letter 1d465 minus 2 minus letter 1d465 minus 1 letter 1d465 2 minus 6 letter 1d465 minus 1658. 1 letter 1d465 minus 4 minus 3 letter 1d465 plus 6 minus 2 letter 1d465 plus 7 letter 1d465 2 plus 2 letter 1d465 minus 2459. 2 letter 1d465 letter 1d465 2 minus 16 minus 1 minus 2 letter 1d465 letter 1d465 2 plus 6 letter 1d465 plus 8 minus letter 1d465 minus 5 letter 1d465 2 minus 4 letter 1d465. Learning objectives. In this section, you will find the sum and difference of two matrices, find scalar multiples of a matrix, find the product of two matrices. Figure 1, credit. SD Dirk, Flickr. Two club soccer teams, the Wildcats and the Mudcats, are hoping to obtain new equipment for an upcoming season. Table 1 shows the needs of both teams. Wildcats Mudcats. Goals 610. Balls 30-24. Jerseys 14-20. Table 1. A goal costs $300, a ball costs $10, and a jersey costs $30. How can we find the total cost for the equipment needed for each team? In this section, we discover a method in which the data in the soccer equipment table can be displayed and used for calculating other information. Then, we will be able to calculate the cost of the equipment, finding the sum and difference of two matrices. To solve a problem like the one described for the soccer teams, we can use a matrix, which is a rectangular array of numbers. A row in a matrix is a set of numbers that are aligned horizontally. A column in a matrix is a set of numbers that are aligned vertically. Each number is an entry, sometimes called an element, of the matrix. Matrices, plural, are enclosed in or and are usually named with capital letters. For example, three matrices named letter 1d434, letter 1d435, and letter 1d436 are shown below. Letter 1d434 equals 1,324. Letter 1d435 equals 1,072 minus 58,762. Letter 1d436 equals minus 103,321. Describing matrices. A matrix is often referred to by its size or dimensions. Letter 1d45a times letter 1d45b, indicating letter 1d45a. Rows and letter 1d45b. Columns. Matrix entries are defined first by row and then by column. For example, to locate the entry in matrix letter 1d434, identified as letter 1d44, letter 1d456, letter 1d457, we look for the entry in row letter 1d456, column letter 1d457, in matrix letter 1d434. Shown below, the entry in row 2, column 3, is letter 1d44e23. Letter 1d434 equals letter 1d44e, 11 letter 1d44e, 21 letter 1d44e, 31 letter 1d44e, 12 letter 1d44e, 22 letter 1d44e, 32 letter 1d44e, 13 letter 1d44e, 23 letter 1d44e, 33. A square matrix is a matrix with dimensions letter 1d45b times letter 1d45b, meaning that it has the same number of rows as columns. The 3 times 3 matrix above is an example of a square matrix. A row matrix is a matrix consisting of one row with dimensions 1 times letter 1d45b. Letter 1d44e, 11 letter 1d44e, 12 letter 1d44e, 13. A column matrix is a matrix consisting of one column with dimensions letter 1d45a times 1. Letter 1d44e, 11 letter 1d44e, 21 letter 1d44e, 31. A matrix may be used to represent a system of equations. In these cases, the numbers represent the coefficients of the variables in the system. Matrices often make solving systems of equations easier because they are not encumbered with variables. We will investigate this idea further in the next section, but first we will look at basic matrix operations. Matrices. A matrix is a rectangular array of numbers that is usually named by a capital letter, A, B, C, and so on. Each entry in a matrix is referred to as letter 1d44, letter 1d456, letter 1d457, such that letter 1d456 represents the row and letter 1d457 represents the column. Matrices are often referred to by their dimensions. Letter 1d45a times letter 1d45b, indicating letter 1d45a. Rows and letter 1d45b. Columns. Example 1. Finding the dimensions of the given matrix and locating entries. Given matrix letter 1d434. What are the dimensions of matrix letter 1d434? B. What are the entries at letter 1d44, 31, and letter 1d44, 22? Letter 1d434 equals 22,314,107 minus 2. Solution. The dimensions are 3 times 3, because there are 3 rows and 3 columns. B. Entry letter 1d44, 31, is the number at row 3, column 1, which is 3. The entry letter 1d44, 22, is the number at row 2, column 2, which is 4. Remember, the row comes first, then the column. Adding and subtracting matrices. We use matrices to list data or to represent systems. Because the entries are numbers, we can perform operations on matrices. We add or subtract matrices by adding or subtracting corresponding entries. In order to do this, the entries must correspond. Therefore, addition and subtraction of matrices is only possible when the matrices have the same dimensions. We can add or subtract a 3 times 3 matrix and another 3 times 3 matrix, but we cannot add or subtract a 2 times 3 matrix and a 3 times 3 matrix because some entries in one matrix will not have a corresponding entry in the other matrix. Adding and subtracting matrices. Given matrices, letter 1d434 and letter 1d435, of like dimensions, addition and subtraction of letter 1d434 and letter 1d435 will produce matrix letter 1d436, or matrix letter 1d437, of the same dimension. Letter 1d434 plus letter 1d435 equals letter 1d436 such that letter 1d44, letter 1d456, letter 1d457 plus letter 1d44f, letter 1d456, letter 1d457 equals letter 1d450, letter 1d456, letter 1d457. Letter 1d434 minus letter 1d435 equals letter 1d437 such that letter 1d44, letter 1d456, letter 1d457 minus letter 1d44f, letter 1d456, letter 1d457 equals letter 1d451, letter 1d456, letter 1d457. Matrix addition is commutative. Letter 1d434 plus letter 1d435 equals letter 1d435 plus letter 1d434. It is also associative. Letter 1d434 plus letter 1d435 plus letter 1d436 equals letter 1d434 plus letter 1d435 plus letter 1d436. Example 2. Finding the sum of matrices. Find the sum of letter 1d434 and letter 1d435. Given letter 1d434 equals letter 1d44, letter 1d450, letter 1d44f, letter 1d451, and letter 1d435 equals letter 1d452, letter 1d454, letter 1d453, letter 210e. Solution. Add corresponding entries. Letter 1d434 plus letter 1d435 equals letter 1d44, letter 1d450, letter 1d44f, letter 1d451 plus letter 1d452, letter 1d454, letter 1d453, letter 210e equals letter 1d440 plus letter 1d452, letter 1d450 plus letter 1d454, letter 1d44f plus letter 1d453, letter 1d451 plus letter 210e. Example 3. Adding matrix A and matrix B. Find the sum of letter 1d434 and letter 1d435. Letter 1d434 equals 4,312, and letter 1d435 equals 5,097. Solution. Add corresponding entries. Add the entry in row 1, column 1, letter 1d44 11, of matrix letter 1d434, To the entry in row 1, column 1, letter 1D44F11, of letter 1D435. Continue the pattern until all entries have been added. Letter 1D434 plus letter 1D435 equals 4,312 plus 5, 1,097, equals 4 plus 53 plus 0, 1 plus 92 plus 7, equals 93,109. Example 4. Finding the difference of two matrices. Find the difference of letter 1D434 and letter 1D435. Letter 1D434 equals minus 2,031, and letter 1D435 equals 8,514. Solution. We subtract the corresponding entries of each matrix. Letter 1D434 minus letter 1D435 equals minus 2,031 minus 8,514 equals minus 2 minus 80 minus 53 minus 11 minus 4 equals minus 10 minus 52 minus 3. Example 5. Finding the sum and difference of two 3x3 matrices. Given letter 1D434 and letter 1D435. A. Find the sum. B. Find the difference. Letter 1D434 equals 2,144 minus 1,012 minus 2 minus 2,102, and letter 1D435 equals 60 minus 510 minus 122 minus 2 minus 4 minus 2. Solution. Add the corresponding entries. Letter 1D434 plus letter 1D435 equals 2,140, 4 minus 1,012 minus 2 minus 2,102, plus 60 minus 510 minus 122 minus 2 minus 4 minus 2 equals 2, plus 614 plus 0, 4 minus 5 minus 10, plus 1,012 minus 12 minus 2, plus 2 minus 2 minus 210 minus 42 minus 2 equals 800. B. Subtract the corresponding entries. Letter 1D434 minus letter 1D435 equals 2,140, 4 minus 1,012, minus 2 minus 2,102, minus 60 minus 510, minus 122 minus 2 minus 4 minus 2 equals 2 minus 614 minus 0, 4 plus 5 minus 10 minus 1,012, plus 12 minus 2 minus 2 minus 2, plus 210 plus 42, plus 2 equals minus 4. Try it 1. Add matrix letter 1D434 and matrix letter 1D435. Letter 1D434 equals 21,160 minus 3, and letter 1D435 equals 31 minus 4 minus 253. Finding scalar multiples of a matrix. Besides adding and subtracting whole matrices, there are many situations in which we need to multiply a matrix by a constant called a scalar. Recall that a scalar is a real number quantity that has magnitude, but not direction. For example, time, temperature, and distance are scalar quantities. The process of scalar multiplication involves multiplying each entry in a matrix by a scalar. A scalar multiple is any entry of a matrix that results from scalar multiplication. Consider a real-world scenario in which a university needs to add to its inventory of computers, computer tables, and chairs in 2 of the campus labs due to increased enrollment. They estimate that 15% more equipment is needed in both labs. The school's current inventory is displayed in Table 2. Lab B. Computers 1527. Computer tables 1634. Chairs 1634. Table 2. Converting the data to a matrix. We have letter 1D436 2013 equals 151,600. 16,273,434. To calculate how much computer equipment will be needed, we multiply all entries in matrix letter 1D436 by 0, 15, 0, 15 letter 1D436 2013 equals 0, 15, 15, 0, 15, 16, 0, 15, 16, 0, 15, 27, 0, 15, 34, 0. 1534 equals 2, 252, 42, 44, 55, 15, 1. We must round up to the next integer, so the amount of new equipment needed is 330, 3,566. Adding the two matrices as shown below, we see the new inventory amounts: 151,600, 16,273,430, 4 plus 330, 3,566 equals 180, 1,919,324,040. This means letter 1D436 2014 equals 180, 1,919,324,040. Thus, Lab A will have 18 computers, 19 computer tables, and 19 chairs. Lab B will have 32 computers, 40 computer tables, and 40 chairs. Scalar multiplication. Scalar multiplication involves finding the product of a constant by each entry in the matrix. Given letter 1D434 equals letter 1D44e, 11 letter 1D44e, 21 letter 1D44e, 12 letter 1D44e, 22. The scalar multiple letter 1D450, letter 1D434, is letter 1D450, letter 1D434 equals letter 1D450, letter 1D44e, 11 letter 1D44e, 21 letter 1D44e, 12 letter 1D44e, 22. Equals letter 1D450, letter 1D44e, 11 letter 1D450, letter 1D44e, 21 letter 1D450, letter 1D44e, 12 letter 1D450, letter 1D44e, 22. Scalar multiplication is distributive for the matrices letter 1D434, B, and letter 1D436, with scalars letter 1D44e and letter 1D44f, letter 1D44e, letter 1D434 plus letter 1D435 equals letter 1D44e, letter 1D434 plus letter 1D44e, letter 1D435, letter 1D44e plus letter 1D44f, letter 1D434 equals letter 1D44e, letter 1D434 plus letter 1D44f, letter 1D434. Example 6. Multiplying the matrix by a scalar. Multiply matrix, letter 1D434, by the scalar 3, letter 1D434, equals 8,514. Solution. Multiply each entry in letter 1D434 by the scalar 3, 3 letter 1D434 equals 38,514 equals 380, 353, 13, 4 equals 2,415,312. Try it too. Given matrix letter 1D435, find minus 2 letter 1D435, where letter 1D435 equals 4,312. Example 7. Finding the sum of scalar multiples. Find the sum 3 letter 1D434 plus 2 letter 1D435. Letter 1D434 equals 104 minus 2 minus 1,300, 2 minus 6. And letter 1D435 equals minus 1,002 minus 3,112 minus 4. Solution first, find 3a, then 2b. 3 letter 1D434 equals 313,0, 343. Minus 2, 3. Minus 1, 333,0, 323. Minus 6 equals 3,012 minus 6 minus 3,906 minus 18, 2. Letter 1D435 equals 2 minus 1, 2020, 222. Minus 3, 2, 12, 12, 22 minus 4. Equals minus 2,004 minus 6,224 minus 8 now. Add 3a plus 2b. 3 letter 1D434 plus 2 letter 1D435 equals 3,012 minus 6 minus 3,906 minus 18 plus minus 2,004 minus 6,224 minus 8 equals 3 minus 20 plus 0, 12, plus 0 minus 6 plus 4 minus 3 minus 69 plus 20 plus 26 plus 4 minus 18 minus 8 equals 1,012 minus 2 minus 911,210 minus 26. Finding the product of two matrices in addition to multiplying a matrix by a scalar. We can multiply two matrices. Finding the product of two matrices is only possible when the inner dimensions are the same, meaning that the number of columns of the first matrix is equal to the number of rows of the second matrix. If A is in letter 1D45A times letter 1D45F matrix, and B is in letter 1D45F times letter 1D45B matrix, then the product matrix OB is in letter 1D45A times letter 1D45B matrix. For example, the product OB is possible because the number of columns in A is the same as the number of rows in B. If the inner dimensions do not match, the product is not defined. We multiply entries of A with entries of B according to a specific pattern as outlined below. The process of matrix multiplication becomes clearer when working a problem with real numbers. To obtain the entries in row I of OB, we multiply the entries in row I of A by column J in B and add. For example, given matrices A and B, where the dimensions of A are 2 times 3 and the dimensions of B are 3 times 3, the product of OB will be a 2 times 3 matrix. Letter 1 D434 equals letter 1 D44E, 11 letter 1 D44E, 21 letter 1 D44E, 12 letter 1 D44E, 22 letter 1 D44E, 13 letter 1 D44E, 23 and multiply and add as follows to obtain the first entry of the product matrix. To obtain the entry in row 1, column 1 of OB, multiply the first row in A by the first column in B, and add. Letter 1 D44E, 11 letter 1 D44E, 12 letter 1 D44E, 13 letter 1 D44F, 11 letter 1 D44F, 21 letter 1 D44F, 31 equals letter 1 D44E, 11 letter 1 D44F, 11 plus letter 1 D44E, 12 letter 1 D44F, 21 plus letter 1 D44E, 13 letter 1 D44F, 31 to obtain the entry in row 1. Column 2 of OB, multiply the first row of A by the second column in B, and add. Letter 1 D44E, 11 letter 1 D44E, 12 letter 1 D44E, 13 letter 1 D44F, 12 letter 1 D44F, 22 letter 1 D44F, 32 equals letter 1 D44E, 11 letter 1 D44F, 12 plus letter 1 D44E, 12 letter 1 D44F, 22 plus letter 1 D44E, 13 letter 1 D44F, 32 to obtain the entry in row 1. Column 3 of OB, multiply the first row of A by the third column in B, and add. Letter 1 D44E, 11 letter 1 D44E, 12 letter 1 D44E, 13 letter 1 D44F, 13 letter 1 D44F, 23 letter 1 D44F, 33 equals letter 1 D44E, 11 letter 1 D44F, 13 plus letter 1 D44E, 12 letter 1 D44F, 23 plus letter 1 D44E, 13 letter 1 D44F, 33. We proceed the same way to obtain the second row of OB. In other words, row 2 of A times column 1 of B, row 2 of A times column 2 of B, row 2 of A times column 3 of B. When complete, the product matrix will be letter 1 D434 letter 1 D435 equals letter 1 D44E, 11 letter 1 D44F, 11 plus letter 1 D44E, 12 letter 1 D44F, 21 plus letter 1 D44E, 13 letter 1 D44F, 31 letter 1 D44E, 21 letter 1 D44F, 11 plus letter 1 D44E, 22 letter 1 D44F, 21 plus letter 1 D44E, 23 letter 1 D44F, 31. Properties of matrix multiplication for the matrices A, B, and C. The following properties hold. Matrix multiplication is associative. Letter 1 D434 letter 1 D435, letter 1 D436 equals letter 1 D434, letter 1 D435 letter 1 D436. Matrix multiplication is distributive. Letter 1 D436, letter 1 D434 plus letter 1 D435 equals letter 1 D436 letter 1 D434 plus letter 1 D436 letter 1 D435. Letter 1 D434 plus letter 1 D435 letter 1 D436 equals letter 1 D434 letter 1 D436 plus letter 1 D435 letter 1 D436. Note that matrix multiplication is not commutative. Example 8 multiplying two matrices multiply matrix A and matrix B. Letter 1 D434 equals 1,324 and letter 1 D435 equals 5,768. Solution first. We check the dimensions of the matrices. Matrix A has dimensions 2 times 2, and matrix B has dimensions 2 times 2. The inner dimensions are the same, so we can perform the multiplication. The product will have the dimensions 2 times 2. We perform the operations outlined previously. Example 9 multiplying two matrices given A and B. A find B find BA. Letter 1 D434 equals minus 123,405 and letter 1 D435 equals 5 minus 42 minus 103 analysis. Notice that the products OB and BA are not equal. Letter 1 D434 letter 1 D435 equals minus 7,301,011 not minus 940, 1,010, minus 8,410, minus 1,221 equals letter 1 D435 letter 1 D434. This illustrates the fact that matrix multiplication is not commutative. Q and A, is it possible for OB to be defined but not BA? Yes, consider a matrix A with dimension 3 times 4 and matrix B with dimension 4 times 2. For the product OB, the inner dimensions are 4 and the product is defined. But for the product BA, the inner dimensions are 2 and 3, so the product is undefined. Example 10, using matrices in real-world problems, let's return to the problem presented at the opening of this section. We have Table 3, representing the equipment needs of 2 soccer teams. Wildcats Mudcats goals, 6-10 balls, 30-24 jerseys, 14-20. Table 3, we are also given the prices of the equipment, as shown in Table 4. Goal $300, ball $10, jersey $30. Table 4, we will convert the data to matrices. Thus, the equipment need matrix is written as letter 1D438 equals 63,014,100,2,420. The cost matrix is written as letter 1D436 equals 3,001,030. We perform matrix multiplication to obtain costs for the equipment. Letter 1D436, letter 1D438 equals 3,001,030, 63,014,100,2,420 equals 300. 6 plus 10, 30, plus 30, 14, 300. 10 plus 10, 24, plus 30, 20 equals 2. 5203, 840. The total cost for equipment for the Wildcats is $2, $520, and the total cost for equipment for the Mudcats is $3, $840. How to given a matrix operation, evaluate using a calculator. Save each matrix as a matrix variable letter 1D434, letter 1D435, letter 1D436. Enter the operation into the calculator, calling up each matrix variable as needed. If the operation is defined, the calculator will present the solution matrix. If the operation is undefined, it will display an error message. Example 11, using a calculator to perform matrix operations. Find, given letter 1D434 equals minus 15,400,11,025 minus 73,432 minus 28 minus 2. Letter 1D435 equals 45 minus 2,462,152 minus 48 minus 3,719 minus 31. And letter 1D436 equals minus 10,025 minus 67 minus 89 minus 5,642 minus 9,874 minus 75. Media access, these online resources for additional instruction and practice with matrices and matrix operations. Dimensions of a matrix, matrix addition and subtraction matrix operations, matrix multiplication 7. 5-section exercises. Verbal 1. Can we add any 2 matrices together? If so, explain why. If not, explain why not and give an example of 2 matrices that cannot be added together. 2. Can we multiply any column matrix by any row matrix? Explain why or why not. 3. Can both the products OB and BA be defined? If so, explain how. If not, explain why. 4. Can any 2 matrices of the same size be multiplied? If so, explain why, and if not, explain why not and give an example of 2 matrices of the same size that cannot be multiplied together. 5. Does matrix multiplication commute? That is, does letter 1D434 letter 1D435 equals letter 1D435 letter 1D434? If so, prove why it does. If not, explain why it does not. Algebraic for the following exercises, use the matrices below and perform the matrix addition or subtraction. Indicate if the operation is undefined. Letter 1D434 equals 1,037. Letter 1D435 equals 222,146. Letter 1D436 equals 18,125,926. Letter 1D437 equals 107,514,261. Letter 1D438 equals 614,125. Letter 1D439 equals 078,159,1746. A plus B 7, C plus D 8, A plus C 9. Letter 1D435 minus letter 1D438 10. C plus F 11. letter 1d437 minus letter 1d435 for the following exercises. Use the matrices below to perform scalar multiplication. Letter 1d434 equals 413,612. Letter 1d435 equals 321,091,264. Letter 1d436 equals 169,030,030, 5,730,1,829. Letter 1d437 equals 18,871,200,000, 14,400,000, 13,621.12. 5a13, 3b14, minus 2 letter 1d435 15, minus 4 letter 1d436 16, 12c17. 100d for the following exercises. Use the matrices below to perform matrix multiplication. Letter 1d434 equals minus 1,352. Letter 1d435 equals 3 minus 860,412. Letter 1d436 equals 4 minus 251,069. Letter 1d437 equals 290 minus 330, 8,121, minus 1018. Ob 19, BC 20, CA 21, BD 22, DC 23. CB for the following exercises. Use the matrices below to perform the indicated operation if possible. If not possible, explain why the operation cannot be performed. Letter 1d434 equals 26 minus 57. Letter 1d435 equals minus 9 minus 462. Letter 1d436 equals 0791. Letter 1d437 equals minus 840,739 minus 522. Letter 1d438 equals 4,715 minus 603 minus 5924. Letter 1d434 plus letter 1d435 minus letter 1d436 25. 4a plus 5d 26. 2c plus b 27. 3d plus 4e 28. Letter 1d436 minus 0. 5d 29. 100 letter 1d437 minus 10, letter 1d438 for the following exercises. Use the matrices below to perform the indicated operation if possible. If not possible, explain why the operation cannot be performed. Hint: letter 1d434 2 equals letter 1d434 letter 1d434. Letter 1d434 equals minus 1,052,025. Letter 1d435 equals 40 minus 201,030. Letter 1d436 equals minus 1,010 minus 1030. Ob 31, BA 32, CA 33, BC 34, A2 35, B2 36, C2 37, B2A 238, A to B 239. Letter 1d434 letter 1d435 240. Letter 1d435 letter 1d434 2 for the following exercises. Use the matrices below to perform the indicated operation if possible. If not possible, explain why the operation cannot be performed. Hint: letter 1d434 2 equals letter 1d434 letter 1d434. Letter 1d434 equals 1,203. Letter 1d435 equals minus 2 minus 1,314 minus 5. Letter 1d436 equals 0. 51 minus 0. 50. 1020. 3. Letter 1d437 equals 1 minus 64,072 minus 15141. Ob 42, BA 43, BD 44, DC 45, D2 46, A2 47, D3 48. Letter 1d434 letter 1d435, letter 1d436 49. Letter 1d434, letter 1d435 letter 1d436. Technology for the following exercises. Use the matrices below to perform the indicated operation if possible. If not possible, explain why the operation cannot be performed. Use a calculator to verify your solution. Letter 1d434 equals minus 210. 50,840, 9 minus 35. Letter 1d435 equals 0. 5 minus 40, 8,317,062. Letter 1d436 equals 101,010,100, 150. OB 51, BA 52, CA 53, BC 54. ABC extensions for the following exercises. Use the matrix below to perform the indicated operation on the given matrix. Letter 1D435 equals 100,001,010.55, B256, B357, B458, B559. Using the above questions, find a formula for letter 1D435, letter 1D45B. Test the formula for B201 and B202 using a calculator. Learning objectives. In this section, you will write the augmented matrix of a system of equations. Write the system of equations from an augmented matrix. Perform row operations on a matrix. Solve a system of linear equations using matrices. Figure 1. German mathematician Carl Friedrich Gauss, 1777–1855. Carl Friedrich Gauss lived during the late 18th century and early 19th century, but he is still considered one of the most prolific mathematicians in history. His contributions to the science of mathematics and physics span fields such as algebra, number theory, analysis, differential geometry, astronomy, and optics, among others. His discoveries regarding matrix theory changed the way mathematicians have worked for the last 2 centuries. We first encountered Gaussian elimination in systems of linear equations, 2 variables. In this section, we will revisit this technique for solving systems, this time using matrices. Writing the augmented matrix of a system of equations. A matrix can serve as a device for representing and solving a system of equations. To express a system in matrix form, we extract the coefficients of the variables and the constants, and these become the entries of the matrix. We use a vertical line to separate the coefficient entries from the constants, essentially replacing the equal signs. When a system is written in this form, we call it an augmented matrix. For example, consider the following 2 times 2 system of equations. 3 letter 1D465 plus 4 letter 1D466 equals 74 letter 1D465 minus 2 letter 1D466 equals 5. We can write this system as an augmented matrix. 340, 4 minus 2, 75. We can also write a matrix containing just the coefficients. This is called the coefficient matrix. 340, 4 minus 2. A 3 by 3 system of equations such as 3 letter 1D465 minus letter 1D466 minus letter 1D467 equals 0 letter 1D465 plus letter 1D466 equals 5 2 letter 1D465 minus 3 letter 1D467 equals 2. Has a coefficient matrix, 312 minus 110 minus 10 minus 3, and is represented by the augmented matrix, 312 minus 110 minus 10 minus 3, 0, 52. Notice that the matrix is written so that the variables line up in their own columns. X terms go in the first column, Y terms in the second column, and Z terms in the third column. It is very important that each equation is written in standard form, letter 1D44, letter 1D465, plus letter 1D44F, letter 1D466, plus letter 1D450, letter 1D467 equals letter 1D451, so that the variables line up. When there is a missing variable term in an equation, the coefficient is 0. How to? Given a system of equations, write an augmented matrix. Write the coefficients of the x terms as the numbers down the first column. Write the coefficients of the y terms as the numbers down the second column. If there are z terms, write the coefficients as the numbers down the third column. Draw a vertical line and write the constants to the right of the line. Example 1. Writing the augmented matrix for a system of equations. Write the augmented matrix for the given system of equations. Letter 1D465 plus 2 letter 1D466 minus letter 1D467 equals 32 letter 1D465 minus letter 1D466 plus 2 letter 1D467 equals 6 letter 1D465 minus 3 letter 1D466 plus 3 letter 1D467 equals 4. Solution. The augmented matrix displays the coefficients of the variables and an additional column for the constants. 1212 minus 1 minus 3 minus 123, 364. Try it 1. Write the augmented matrix of the given system of equations. 4 letter 1D465 minus 3 letter 1D466 equals 113 letter 1D465 plus 2 letter 1d466 equals 4. Writing a system of equations from an augmented matrix, we can use augmented matrices to help us solve systems of equations because they simplify operations when the systems are not encumbered by the variables. However, it is important to understand how to move back and forth between formats in order to make finding solutions smoother and more intuitive. Here, we will use the information in an augmented matrix to write the system of equations in standard form. Example 2. Writing a system of equations from an augmented matrix form. Find the system of equations from the augmented matrix 12 minus 3 minus 3 minus 55 minus 5 minus 44 minus 256. Solution. When the columns represent the variables letter 1d465, y, and letter 1d467, 12 minus 3 minus 3 minus 55 minus 5 minus 44 minus 256, write letter 1d465 minus 3 letter 1d466 minus 5 letter 1d467 equals minus 22 letter 1d465 minus 5 letter 1d466 minus 4 letter 1d467 equals 5 minus 3 letter 1d465 plus 5 letter 1d466 plus 4 letter 1d467 equals 6. Try it too. Write the system of equations from the augmented matrix 120 minus 1 minus 11,130, 151 minus 9. Performing row operations on a matrix. Now that we can write systems of equations in augmented matrix form, we will examine the various row operations that can be performed on a matrix, such as addition, multiplication by a constant, and interchanging rows. Performing row operations on a matrix is the method we use for solving a system of equations. In order to solve the system of equations, we want to convert the matrix to row echelon form, in which there are ones down the main diagonal from the upper left corner to the lower right corner, and zeros in every position below the main diagonal as shown. Row echelon form 100 letter 1d44e, 10 letter 1d44f letter 1d4511. 1. We use row operations corresponding to equation operations to obtain a new matrix that is row equivalent in a simpler form. Here are the guidelines to obtaining row echelon form. In any non-zero row, the first non-zero number is a 1. It is called a leading one. Any all-zero rows are placed at the bottom on the matrix. Any leading one is below and to the right of a previous leading one. Any column containing a leading one has zeros in all other positions in the column. To solve a system of equations, we can perform the following row operations to convert the coefficient matrix to row echelon form and do back substitution to find the solution. Interchange rows. Notation. Letter 1d445 letter 1d456, left right arrow, letter 1d445 letter 1d457. Multiply a row by a constant. Notation. Letter 1d450, letter 1d445 letter 1d456. Add the product of a row multiplied by a constant to another row. Notation. Letter 1d445 letter 1d456 plus letter 1d450, letter 1d445 letter 1d457. Each of the row operations corresponds to the operations we have already learned to solve systems of equations in 3 variables. With these operations, there are some key moves that will quickly achieve the goal of writing a matrix in row echelon form. To obtain a matrix in row echelon form for finding solutions, we use Gaussian elimination, a method that uses row operations to obtain a 1 as the first entry so that row 1 can be used to convert the remaining rows. Gaussian elimination. The Gaussian elimination method refers to a strategy used to obtain the row echelon form of a matrix. The goal is to write matrix letter 1d434 with the number 1 as the entry down the main diagonal and have all zeros below. Letter 1d434 equals letter 1d44e, 11 letter 1d44e, 21 letter 1d44e, 31 letter 1d44e, 12 letter 1d44e, 22 letter 1d44e, 32 letter 1d44e, 13 letter 1d44e, 23 letter 1d44e, 33 minus right minus 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 after Gaussian. Elimination letter 1d434 equals 100 letter 1d44f, 1210 letter 1d44f, 13 letter 1d44f, 231. The first step of the Gaussian strategy includes obtaining a 1 as the first entry, so that row 1 may be used to alter the rows below. How to, given an augmented matrix, perform row operations to achieve row echelon form. The first equation should have a leading coefficient of 1. Interchange rows or multiply by a constant, if necessary. Use row operations to obtain zeros down the first column below the first entry of 1. Use row operations to obtain a 1 in row 2, column 2. Use row operations to obtain zeros down column 2 below the entry of 1. Use row operations to obtain a 1 in row 3, column 3. Continue this process for all rows until there is a 1 in every entry down the main diagonal and there are only zeros below. If any rows contain all zeros, place them at the bottom. Example 3. Solving a 2 times 2 system by Gaussian elimination. Solve the given system by Gaussian elimination. 2 letter 1d465 plus 3 letter 1d466 equals 6 letter 1d465 minus letter 1d466 equals 12. Solution. First, we write this as an augmented matrix. 213 minus 1 612. We want a 1 in row 1, column 1. This can be accomplished by interchanging row 1 and row 2. Letter 1 d445 1 left right arrow, letter 1 d445 2 right arrow 12 minus 13 126. We now have a 1 as the first entry in row 1, column 1. Now let's obtain a 0 in row 2, column 1. This can be accomplished by multiplying row 1 by minus 2, and then adding the result to row 2. Minus 2 letter 1 d445 1 plus letter 1 d445 2 equals letter 1 d445 2 right arrow 10 minus 15 125. We only have one more step, to multiply row 2 by 15. 15 letter 1 d445 2 equals letter 1 d445 2 right arrow 10 minus 11 121. Use back substitution. The second row of the matrix represents letter 1 d466 equals 1. Back substitute letter 1 d466 equals 1 into the first equation. Letter 1 d465 minus 1 equals 12 letter 1 d465 equals 32. The solution is the point 321. Try it 3. Solve the given system by Gaussian elimination. 4 letter 1 d465 plus 3 letter 1 d466 equals 11 letter 1 d465 minus 3 letter 1 d466 equals minus 1. Example 4. Using Gaussian elimination to solve a system of equations. Use Gaussian elimination to solve the given 2 times 2 system of equations. 2 letter 1 d465 plus letter 1 d466 equals 14 letter 1 d465 plus 2 letter 1 d466 equals 6. Solution. Write the system as an augmented matrix. 2412, 16. Obtain a 1 in row 1, column 1. This can be accomplished by multiplying the first row by 12. 12 letter 1 d445, 1 equals letter 1 d445, 1 right arrow 14,122, 126. Next, we want a 0 in row 2, column 1. Multiply row 1 by minus 4, and add row 1 to row 2, 124. The second row represents the equation. Therefore, the system is inconsistent and has no solution. Example 5. Solving a dependent system. Solve the system of equations. Solution. Perform row operations on the augmented matrix to try and achieve row echelon form. Letter 1 d434 equals 3,640, 8 1,224. Minus 12 letter 1 d445 2 plus letter 1 d445 1 equals letter 1 d445 1 right arrow 0608 0 20 4 letter 1 d445 1 left right arrow letter 1 d445 2 right arrow 6080 240. The matrix ends up with all zeros in the last row. 0 letter 1 d466 equals 0. Thus, there are an infinite number of solutions, and the system is classified as dependent. To find the generic solution, return to one of the original equations and solve for letter 1 d466. 3 letter 1 d465 plus 4 letter 1 d466 equals 12 4 letter 1 d466 equals 12 minus 3 letter 1 d465 letter 1 d466 equals 3 minus 34 letter 1 d465. So the solution to this system is letter 1 d465. 3 minus 34 letter 1d465. Example 6. Performing row operations on a 3 times 3 augmented matrix to obtain row echelon form. Perform row operations on the given matrix to obtain row echelon form. 366. Solution. The first row already has a 1 in row 1, column 1. The next step is to multiply row 1 by -2 and add it to row 2. Then replace row 2 with the result. -2 letter 1d445 1 plus letter 1d445 2 equals letter 1d445 2 right 10 minus 3 minus 3134 minus 24,306. Next, obtain a 0 in row 3, column 1. 3 letter 1d445 1 plus letter 1d445 3 equals letter 1d445 3 right 100 minus 30 1 minus 64 minus 216 3015. Next, obtain a 0 in row 3, column 2. 6 letter 1d445 2 plus letter 1d445 3 equals letter 1d445 3 right 100 minus 3104 minus 24 3015. The last step is to obtain a 1 in row 3, column 3. 14 letter 1d445 3 equals letter 1d445 3 right 100 minus 3104 minus 21 30,154. Try it 4. Write the system of equations in row echelon form. Letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 9 minus letter 1d465 plus 3 letter 1d466 equals minus 42 letter 1d465 minus 5 letter 1d466 plus 5 letter 1d467 equals 17. Solving a system of linear equations using matrices. We have seen how to write a system of equations with an augmented matrix, and then how to use row operations and back substitution to obtain row echelon form. Now, we will take row echelon form a step farther to solve a 3 by 3 system of linear equations. The general idea is to eliminate all but one variable using row operations and then back substitute to solve for the other variables. Example 7. Solving a system of linear equations using matrices. Solve the system of linear equations using matrices. Letter 1d465 minus letter 1d466 plus letter 1d467 equals 82 letter 1d465 plus 3 letter 1d466 minus letter 1d467 equals minus 23 letter 1d465 minus 2 letter 1d466 minus 9 letter 1d467 equals 9. Solution. First, we write the augmented matrix. 123 minus 13 minus 21 minus 1 minus 9, 8 minus 29. Next, we perform row operations to obtain row echelon form. -2 letter 1d445 1 plus letter 1d445 2 equals letter 1d445 2 right 103 minus 15 minus 21 minus 3 minus 9, 8 minus 189 minus 3 letter 1d445 1 plus letter 1d445 3 equals letter 1d445 3 right 100 minus 1511 minus 3 minus 12 8 minus 18 minus 15. The easiest way to obtain a 1 in row 2 of column 1 is to interchange letter 1d4452 and letter 1d4453. Interchange R2 and letter 1d445 3 right 100 minus 1151 minus 12 minus 38 minus 15 minus 18. Then, minus 5 letter 1d445 2 plus letter 1d445 3 equals letter 1d445 3 right 100 minus 1101 minus 1257 8 minus 1557 minus 157 letter 1d445 3 equals letter 1d445 3 right 100 minus 1101 minus 121 8 minus 151. The last matrix represents the equivalent system. Letter 1d465 minus letter 1d466 plus letter 1d467 equals 8 letter 1d466 minus 12 letter 1d467 equals minus 15 letter 1d467 equals 1. Using back substitution, we obtain the solution as 4 minus 3 1. Example 8. Solving a dependent system of linear equations using matrices. Solve the following system of linear equations using matrices. minus letter 1d465 minus 2 letter 1d466 plus letter 1d467 equals minus 1 2 letter 1d465 plus 3 letter 1d466 equals 2 letter 1d466 minus 2 letter 1d467 equals 0. Solution. Write the augmented matrix. Minus 120, minus 23,110, minus 2, minus 120. First, multiply row 1 by minus 1 to get a 1 in row 1, column 1. Then, perform row operations to obtain row echelon form. 120. Letter 1d445, 2, left right arrow, letter 1d445, 3 right 102,213 minus 1 minus 2102. Minus 2 letter 1d445, 1 plus letter 1d445, 3 equals letter 1d445, 3 right 10,021 minus 1, minus 1, minus 22 100. Letter 1d445, 2 plus letter 1d445, 3 equals letter 1d445, 3 right 100,210 minus 1 minus 2110. The last matrix represents the following system. Letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 1 letter 1d466 minus 2 letter 1d467 equals 0. We see by the identity that this is a dependent system with an infinite number of solutions. We then find the generic solution by solving the second equation for letter 1d466 and substituting it into the first equation. We can solve for letter 1d467. In terms of letter 1d465, letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 1 letter 1d466 equals 2 letter 1d467 letter 1d465 plus 2 letter 1d467 minus letter 1d467 equals 1 letter 1d465 plus 3 letter 1d467 equals 1 letter 1d467 equals 1 minus letter 1d465 3. Now we substitute the expression for letter 1d467 into the second equation to solve for letter 1d466. In terms of letter 1d465, the generic solution is x, 2 minus 2 letter 1d4653, 1 minus letter 1d4653. Try it 5. Solve the system using matrices. Letter 1d465 plus 4 letter 1d466 minus letter 1d467 equals 42 letter 1d465. Plus 5 letter 1d466 plus 8 letter 1d467 equals 15 letter 1d465 plus 3 letter 1d466 minus 3 letter 1d467 equals 1. Q&A. Can any system of linear equations be solved by Gaussian elimination? Yes, a system of linear equations of any size can be solved by Gaussian elimination. How to? Given a system of equations, solve with matrices using a calculator. Save the augmented matrix as a matrix variable letter 1d434, letter 1d435, letter 1d436. Use the ref function in the calculator, calling up each matrix variable as needed. Example 9. Solving systems of equations with matrices using a calculator. Solve the system of equations. 5 letter 1d465 plus 3 letter 1d466 plus 9 letter 1d467 equals minus 1 minus 2 letter 1d465 plus 3 letter 1d466 minus letter 1d467 equals minus 2 minus letter 1d465 minus 4 letter 1d466 plus 5 letter 1d467 equals 1. Solution. Write the augmented matrix for the system of equations. 5 minus 2 minus 133 minus 49 minus 15 minus 1 minus 2 minus 1. On the matrix page of the calculator, enter the augmented matrix above as the matrix variable letter 1d434. Letter 1d434 equals 5 minus 2 minus 133 minus 49 minus 15 minus 1 minus 21. Use the ref function in the calculator, calling up the matrix variable letter 1d434. Ref letter 1d434. Evaluate 10,35,109,513,211 minus 15 minus 47 minus 24,187. Right letter 1d465 plus 35 letter 1d466 plus 95 letter 1d467 equals minus 15 letter 1d466 plus 1,321 letter 1d467 equals minus 47 letter 1d467 equal. Using back substitution, the solution is 61,187 minus 92,187 minus 24,187. Example 10. Applying 2 times 2 matrices to finance. Carolyn invests a total of $12,000 in 2 municipal bonds, one paying 10.5% interest and the other paying 12% interest. The annual interest earned on the 2 investments last year was $1,335. How much was invested at each rate? Solution. We have a system of 2 equations in 2 variables. Let the amount invested at 10.5% interest and letter 1d466 equals the amount invested at 12% interest. Letter 1d465 plus letter 1d466 equals 12, 0, 0, 0, 0. 105x plus 0. 12 letter 1d466 equals 1, 335. As a matrix we have 10, 10,510. 12, 120,001,335. Multiply row 1 by minus 0, 105, and add the result to row 2, 1,010. 15, 1,200,075. Then, 0, 0, 15 letter 1d466 equals 75 letter 1d466 equals 5, 0, 0, 0. So 12, 0, 0, 0 minus 5, 0, 0, 0 equals 7, 0, 0, 0. Thus, $5,000 was invested at 12% interest and $7,000 at 10.5% interest. Example 11. Applying 3 times 3 matrices to finance. Ava invests a total of $10,000 in 3 accounts, one paying 5% interest, another paying 8% interest, and the third paying 9% interest. The annual interest earned on the 3 investments last year was $770. The amount invested at 9% was twice the amount invested at 5%. How much was invested at each rate? Solution. We have a system of 3 equations in 3 variables. Let letter 1d465 be the amount invested at 5% interest. Let letter 1d466 be the amount invested at 8% interest. And let letter 1d467 be the amount invested at 9% interest. Thus, letter 1d465 plus letter 1d466 plus letter 1d467 equals 10, 0, 0, 0, 0. 5x plus 0. 8y plus 0. 0, 9 letter 1d467 equals 772 letter 1d465 minus letter 1d467 equals 0. As a matrix we have 10, 5,210, 8,010, 0, 9 minus 110, 0, 0, 0, 7, 7, 0, 0. Now we perform Gaussian elimination to achieve row echelon form. Minus 0. 0, 5 letter 1d445 1 plus letter 1d445 2 equals letter 1d445 2 right 10,210 3,010 0 4 minus 110 0 0 0 2 7 0 0 minus 2 letter 1d445 1 plus letter 1d445 3 equals letter 1d445 3 right 10,010 0 3 minus 210 0, 4 minus 310, 0, 0, 0, 270 minus 20, 0, 0, 0, 10. 0, 3, letter 1d445 2 equals letter 1d445 2 right 0, 0, 0. 1, 1 minus 2,143 minus 310. 9, 0, 0, 0 minus 20. 0, 0, 0, 2 letter 1d445 2 plus letter 1d445 3 equals letter 1d445 3 right 100,110,140, 3 minus 1310. 9, 0, 0, 0 minus 2, 0, 0, 0. The third row tells us minus 13 letter 1d467 equals minus 2, 0. Thus letter 1d467 equals 6, 0, 0, 0. The second row tells us letter 1d466 plus 43 letter 1d467 equals 9, 0, 0, 0. Substituting letter 1d467 equals 6, 0, 0, 0. We get letter 1d466 plus 43, 6, 0, 0, 0 equals 9, 0, 0, 0 letter 1d466 plus 8, 000 equals 9, 000 letter 1d466 equals 1, 000. The first row tells us letter 1d465 plus letter 1d466 plus letter 1d467 equals 10, 000. Substituting letter 1d466 equals 1, 0, and letter 1d467 equals 6, 0, we get x plus 1, 0 plus 6, 000 equals 10, 0, 0. The answer is $3, $0 invested at 5% interest, $1, 0 invested at 8%, and $6, $0 invested at 9% interest. Try at 6. A small shoe company took out a loan of $1,500,000 to expand their inventory. Part of the money was borrowed at 7%, part was borrowed at 8%, and part was borrowed at 10%. The amount borrowed at 10% was 4 times the amount borrowed at 7%, and the annual interest on all 3 loans was $130,500. Use matrices to find the amount borrowed at each rate. Media. Access these online resources for additional instruction and practice with solving systems of linear equations using Gaussian elimination. Solve a system of 2 equations using an augmented matrix. Solve a system of 3 equations using an augmented matrix. Augmented matrices on the calculator. 7-6 section exercises. Verbal. 1. Can any system of linear equations be written as an augmented matrix? Explain why or why not. Explain how to write that augmented matrix. 2. Can any matrix be written as a system of linear equations? Explain why or why not. Explain how to write that system of equations. 3. Is there only one correct method of using row operations on a matrix? Try to explain 2 different row operations possible to solve the augmented matrix 913-26. 4. Can a matrix whose entry is 0 on the diagonal be solved? Explain why or why not. What would you do to remedy the situation? 5. Can a matrix that has 0 entries for an entire row have one solution? Explain why or why not. Algebraic. For the following exercises, write the augmented matrix for the linear system. 6, 8 letter 1d465 minus 37 letter 1d466 equals 82 letter 1d465 plus 12 letter 1d466 equals 3. 7. 16 letter 1d466 equals 49 letter 1d465 minus letter 1d466 equals 2. 8. 3 letter 1d465 plus 2 letter 1d466 plus 10 letter 1d467 equals 3 minus 6 letter 1d465 plus 2 letter 1d466 plus 5 letter 1d467 equals 13 4 letter 1d465 plus letter 1d467 equals 18. 9. Letter 1d465 plus 5 letter 1d466 plus 8 letter 1d467 equals 1912 letter 1d465 plus 3 letter 1d466 equals 43 letter 1d465 plus 4 letter 1d466 plus 9 letter 1d467 equals minus 7. 10. 6 letter 1d465 plus 12 letter 1d466 plus 16 letter 1d467 equals 419 letter 1d465 minus 5 letter 1d466 plus 3 letter 1d467 equals minus 9 letter 1d465 plus 2 letter 1d466 equals minus 8. For the following exercises, write the linear system from the augmented matrix. 11 minus 265 minus 18, 526. 12, 310,417, 10,439. 13. 3 minus 182 minus 95,047, 3 minus 18. 14. 8 minus 102,970,153, 433,810. 15. 122 minus 5. For the following exercises, solve the system by Gaussian elimination. 16. 1,030. 17. 1,112. 18. 1,425, 36. 19. Minus 142 minus 5 minus 36. 20. Minus 2002, 1 minus 1. 21. 2 letter 1d465 minus 3 letter 1d466 equals minus 95 letter 1d465 plus 4 letter 1d466 equals 58. 22. 6 letter 1d465 plus 2 letter 1d466 equals minus 43 letter 1d465 plus 4 letter 1d466 equals minus 17. 23. 2 letter 1d465 plus 3 letter 1d466 equals 12 4 letter 1d465 plus letter 1d466 equals 14. 24. Minus 4 letter 1d465 minus 3 letter 1d466 equals minus 2 3 letter 1d465 minus 5 letter 1d466 equals minus 13. 25. Minus 5 letter 1d465 plus 8 letter 1d466 equals 310 letter 1d465 plus 6 letter 1d466 equals 5. 26. 3 letter 1d465 plus 4 letter 1d466 equals 12 minus 6 letter 1d465 minus 8 letter 1d466 equals minus 24. 27. Minus 60 letter 1d465 plus 45 letter 1d466 equals 12 20 letter 1d465 minus 15 letter 1d466 equals minus 4. 28. 11 letter 1d465 plus 10 letter 1d466 equals 4,315 letter 1d465 plus 20 letter 1d466 equals 65. 29. 2 letter 1d465 minus letter 1d466 equals 23 letter 1d465 plus 2 letter 1d466 equals 17. 30 minus 1. 0 6 letter 1d465 minus 2. 25 letter 1d466 equals 5. 51 minus 5. 0 3 letter 1d465 minus 1. 0 8 letter 1d466 equals 5. 40. 31. 34 letter 1d465 minus 35 letter 1d466 equals 414 letter 1d465 plus 23 letter 1d466 equals 1. 32. 14 letter 1d465 minus 23 letter 1d466 equals minus 112 letter 1d465 plus 13 letter 1d466 equals 3. 33. 100 million, 10,011, 314,587. 34. 110 million, 11,101, 5,020 minus 90. 35. 100 million, 250,000, 368, 479. 36. Minus 0, 1 minus 0, 40, 60 30 20, 1 minus 0, 10 10 7 0 20. 8 minus 0, 8. 37. Minus 2 letter 1d465 plus 3 letter 1d466 minus 2 letter 1d467 equals 3 4 letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 94 letter 1d465 minus 8 letter 1d466 plus 2 letter 1d467 equals minus 6. 38. Letter 1d465 plus letter 1d466 minus 4 letter 1d467 equals minus 4 5 letter 1d465 minus 3 letter 1d466 minus 2 letter 1d467 equals 0 2 letter 1d465 plus 6 letter 1d466 plus 7 letter 1d467 equals 30. 39. 2 letter 1d465 plus 3 letter 1d466 plus 2 letter 1d467 equals 1 minus 4 letter 1d465 minus 6 letter 1d466 minus 4 letter 1d467 equals minus 210 letter 1d465 plus 15 letter 1d466 plus 10 letter 1d467 equals 5. 40. Letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 1 minus letter 1d465 minus 2 letter 1d466 plus 2 letter 1d467 equals minus 23 letter 1d465 plus 6 letter 1d466 minus 3 letter 1d467 equals 5. 41. Letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 1 minus letter 1d465 minus 2 letter 1d466 plus 2 letter 1d467 equals minus 23 letter 1d465 plus 6 letter 1d466 minus 3 letter 1d467 equals 3. 42. letter 1d465 plus letter 1d466 equals 2 letter 1d465 plus letter 1d467 equals 1 minus letter 1d466 minus letter 1d467 equals minus 3. 43. Letter 1d465 plus letter 1d466 plus letter 1d467 equals 100 letter 1d465 plus 2 letter 1d467 equals 125 minus letter 1d466 plus 2 letter 1d467 equals 25. 44. 14 letter 1d465 minus 23 letter 1d467 equals minus 1215 letter 1d465 plus 13 letter 1d466 equals 4715 letter 1d466 minus 13 letter 1d467 equals 29. 45. Minus 12 letter 1d465 plus 12 letter 1d466 plus 17 letter 1d467 equals minus 5314 12 letter 1d465 minus 12 letter 1d466 plus 14 letter 1d467 equals 314 letter 1d465 plus 15 letter 1d466 plus 13 letter 1d467 equals 2315. 46. Minus 12 letter 1d465 minus 13 letter 1d466 plus 14 letter 1d467 equals minus 296. 15 letter 1d465 plus 16 letter 1d466 minus 17 letter 1d467 equals 431,210 minus 18 letter 1d465 plus 19 letter 1d466 plus 110 letter 1d467 equals minus 4,945. Extensions. For the following exercises, use Gaussian elimination to solve the system. 47. Letter 1d465 minus 17 plus letter 1d466 minus 28 plus letter 1d467 minus 34 equals 0 letter 1d465 plus letter 1d466 plus letter 1d467 equals 6 letter 1d465 plus 23 plus 2 letter 1d466 plus letter 1d467 minus 33 equals 5. 48. Letter 1d465 minus 14 minus letter 1d466 plus 14 plus 3 letter 1d467 equals minus 1 letter 1d465 plus 52 plus letter 1d466 plus 74 minus letter 1d467 equals 4 letter 1d465 plus letter 1d466 minus letter 1d467 minus 22 equals 1. 49. Plus 2 letter 1d467 equals minus 1 letter 1d465 plus 52 plus letter 1d466 plus 52 plus letter 1d467 plus 52 equals 8 letter 1d465 plus letter 1d466 plus letter 1d467 equals 1. 50. Letter 1d465 minus 310 plus letter 1d466 plus 32 minus 2 letter 1d467 equals 3 letter 1d465 plus 54 minus letter 1d466 minus 18 plus letter 1d467 equals 32 letter 1d465 minus 14 plus letter 1d466 plus 42 plus 3 letter 1d467 equals 32. 51. Plus 2 letter 1d467 equals minus 1 letter 1d465 plus 52 plus letter 1d466 plus 52 plus letter 1d467 plus 52 equals 7 letter 1d465 plus letter 1d466 plus letter 1d467 equals 1. Real-world applications. For the following exercises, set up the augmented matrix that describes the situation and solve for the desired solution. 52. Every day, Angeni's Cupcake Store sells 5,000 cupcakes in chocolate and vanilla flavors. If the chocolate flavor is 3 times as popular as the vanilla flavor, how many of each cupcake does the store sell per day? 53. At Bakari's competing cupcake store, $4,520 worth of cupcakes are sold daily. The chocolate cupcakes cost $2, $25, and the red velvet cupcakes cost $1. 75. If the total number of cupcakes sold per day is 2,200, how many of each flavor are sold each day? 54. You invested $10,000 into 2 accounts, one that has simple 3% interest, the other with 25% interest. If your total interest payment after 1 year was $283, $50, how much was in each account after the year passed? 55. You invested $2,300 into account 1 and $2,700 into account 2. If the total amount of interest after 1 year is $254 and account 2 has 5 times the interest rate of account 1, what are the interest rates? Assume simple interest rates. 56. Bikesaurus manufactures bikes which sell for $250. It costs the manufacturer $180 per bike, plus a startup fee of $3,500. After how many bikes sold will the manufacturer break even? 57. A major appliance store has agreed to order vacuums from a startup founded by college engineering students. The store would be able to purchase the vacuums for $86 each, with a delivery fee of $9,200, regardless of how many vacuums are sold. If the store needs to start seeing a profit after 230 units are sold, how much should they charge for the vacuums? 58. The 3 most popular ice cream flavors are chocolate, strawberry, and vanilla, comprising 83% of the flavors sold at an ice cream shop. If vanilla sells 1% more than twice strawberry, and chocolate sells 11% more than vanilla, how much of the total ice cream consumption are the vanilla, chocolate, and strawberry flavors? 59. At an ice cream shop, 3 flavors are increasing in demand. Last year, banana, pumpkin, and Rocky Road ice cream made up 12% of total ice cream sales. This year, the same 3 ice creams made up 9% of ice cream sales. The Rocky Road sales doubled, the banana sales increased by 50%, and the pumpkin sales increased by 20%. If the Rocky Road ice cream had 1 less percent of sales than the banana ice cream, find out the percentage of ice cream sales each individual ice cream made last year. 60. A bag of mixed nuts contains cashews, pistachios, and almonds. There are 1,000 total nuts in the bag, and there are 100 less almonds than pistachios. The cashews weigh 3g, pistachios weigh 4g, and almonds weigh 5g. If the bag weighs 37 kg, find out how many of each type of nut is in the bag. 61. A bag of mixed nuts contains cashews, pistachios, and almonds. Originally, there were 900 nuts in the bag. 30% of the almonds, 20% of the cashews, and 10% of the pistachios were eaten, and now there are 770 nuts left in the bag. Originally, there were 100 more cashews than almonds. Figure out how many of each type of nut was in the bag to begin with. Learning objectives. In this section, you will find the inverse of a matrix. Solve a system of linear equations using an inverse matrix. Soria plans to invest $10,500 into 2 different bonds to spread out her risk. The first bond has an annual return of 10%, and the second bond has an annual return of 6%. In order to receive an 5% return from the 2 bonds, how much should Soria invest in each bond? What is the best method to solve this problem? There are several ways we can solve this problem. As we have seen in previous sections, systems of equations and matrices are useful in solving real-world problems involving finance. After studying this section, we will have the tools to solve the bond problem using the inverse of a matrix. Finding the inverse of a matrix. We know that the multiplicative inverse of a real number letter 1d44e is letter 1d44e minus 1, and letter 1d44e letter 1d44e minus 1 equals letter 1d44e minus 1 letter 1d44e equals 1 letter 1d44e letter 1d44e equals 1. For example, 2 minus 1 equals 12, and 12 and 2 equals 1. The multiplicative inverse of a matrix is similar in concept, except that the product of matrix letter 1d434 and its inverse letter 1d434 minus 1 equals the identity matrix. The identity matrix is a square matrix containing ones down the main diagonal and zeros everywhere else. We identify identity matrices by letter 1d43c letter 1d45b, where letter 1d45b represents the dimension of the matrix. Observe the following equations. Letter 1d43c2 equals 1001. Letter 1d43c 3 equals 100,010,001. The identity matrix acts as a 1 in matrix algebra. For example, letter 1d434 letter 1d434c equals letter 1d434c letter 1d434 equals letter 1d434. A matrix that has a multiplicative inverse has the properties letter 1d434 letter 1d434 minus 1 equals letter 1d434c letter 1d434 minus 1 letter 1d434 equals letter 1d434c. A matrix that has a multiplicative inverse is called an invertible matrix. Only a square matrix may have a multiplicative inverse. As the reversibility, letter 1d434 letter 1d434 minus 1 equals letter 1d434 minus 1 letter 1d434 equals letter 1d43c. Is a requirement. Not all square matrices have an inverse, but if letter 1d434 is invertible, then letter 1d434 minus 1 is unique. We will look at two methods for finding the inverse of a 2 times 2 matrix and a third method that can be used on both 2 times 2 and 3 times 3 matrices. The identity matrix and multiplicative inverse. The identity matrix, letter 1d434c letter 1d45b, is a square matrix containing ones down the main diagonal and zeros everywhere else. Letter 1d43c, 2 equals 1001 letter 1d43c, 3 equals 100,010,001, 2 times 2 3 times 3. If letter 1d434 is in letter 1d45b times letter 1d45b, matrix and letter 1d435 is in letter 1d45b times letter 1d45b, matrix such that letter 1d434 letter 1d435 equals letter 1d435 letter 1d434 equals letter 1d43c letter 1d45b. Then letter 1d435 equals letter 1d434 minus 1, the multiplicative inverse of a matrix letter 1d434. Example 1. Showing that the identity matrix acts as a 1. Given matrix A, show that letter 1d434 letter 1d43c equals letter 1d43c letter 1d434 equals letter 1d434. Letter 1d434 equals 3 minus 245. Solution. Use matrix multiplication to show that the product of letter 1d434 and the identity is equal to the product of the identity and A. Letter 1d434 letter 1d43c equals 3 minus 240, 5 1001 equals 3, 1 plus 40 minus 2, 1 plus 5030 plus 4, 1 minus 20 plus 5, 1 equals 3 minus 245. Letter 1d443c letter 1d434 equals 1013 minus 240, 5 equals 13 plus 0. Minus 2, 0 3 plus 1 minus 2, 1 4 plus 0 54 plus 1 5 equals 3 minus 245. How to. Given two matrices, show that one is the multiplicative inverse of the other. Given matrix letter 1d434 of order letter 1d45b times letter 1d45b, and matrix letter 1d435 of order letter 1d45b times letter 1d45b. Multiply letter 1d434 letter 1d435. If letter 1d434 letter 1d435 equals letter 1d43c, then find the product letter 1d435 letter 1d434. If letter 1d435 letter 1d434 equals letter 1d43c, then letter 1d435 equals letter 1d434 minus 1, and letter 1d434 equals letter 1d435 minus 1. Example 2. Showing that matrix A is the multiplicative inverse of matrix B. Show that the given matrices are multiplicative inverses of each other. Letter 1d434 equals 1 minus 25 minus 9. Letter 1d435 equals minus 92 minus 51. Solution. Multiply letter 1d434 letter 1d435 and letter 1d435 letter 1d434. If both products equal the identity, then the two matrices are inverses of each other. Letter 1d434 letter 1d435 equals 1 minus 25 minus 9 minus 92 minus 51 equals 1, minus 9 plus 5. 2 minus 2, minus 9 minus 9, 2, 1 minus 5 plus 5, 1 minus 2 minus 5 minus 9, 1 equals 1001. Letter 1d435 letter 1d434 equals minus 92 minus 50 1 minus 25 minus 9 equals minus 9. 1 minus 5 minus 2 2 1 plus 1 minus 2 minus 9 5 minus 5 minus 9 2 5 plus 1 minus 9 equals 1001. And letter 1d435 are inverses of each other. Try it 1. Show that the following two matrices are inverses of each other. Letter 1d434 equals 1 minus 14 minus 3. Letter 1d435 equals minus 30, 1 minus 41. Finding the multiplicative inverse using matrix multiplication. We can now determine whether two matrices are inverses. But how will we find the inverse of a given matrix? Since we know that the product of a matrix and its inverse is the identity matrix, we can find the inverse of a matrix by setting up an equation using matrix multiplication. Example 3. Finding the multiplicative inverse using matrix multiplication. Use matrix multiplication to find the inverse of the given matrix. Solution. For this method, we multiply letter 1d434 by a matrix containing unknown constants and set it equal to the identity. 12 minus 2 minus 3. Letter 1d44, letter 1d450, letter 1d44f, letter 1d451 equals 1001. Find the product of the two matrices on the left side of the equal sign. 12 minus 2 minus 3. Letter 1d44, letter 1d450, letter 1d44f, letter 1d451 equals 1. Letter 1d440. Minus 2, letter 1d450 to letter 1d440. Minus 3, letter 1d450. 1, letter 1d44f. Minus 2, letter 1d451 to letter 1d44f. Minus 3, letter 1d451. Next, set up a system of equations with the entry in row 1, column 1 of the new matrix equal to the first entry of the identity, 1. Set the entry in row 2, column 1 of the new matrix equal to the corresponding entry of the identity, which is 0. 1 letter 1d440 minus 2 letter 1d450 equals 1 letter 1d445 12 letter 1d440 minus 3 letter 1d450 equals 0 letter 1d4452. Using row operations, multiply and add as follows. Minus 2, letter 1d445 1 plus letter 1d445 2 right arrow letter 1d4452. Add the equations and solve for letter 1d450. 1 letter 1d440 minus 2 letter 1d450 equals 10 plus 1 letter 1d450 equals minus 2 letter 1d450 equals minus 2. Back substitute to solve for letter 1d440. Letter 1d440 minus 2. Minus 2 equals 1 letter 1d440 plus 4 equals 1 letter 1d440 equals minus 3. Write another system of equations setting the entry in row 1, column 2 of the new matrix equal to the corresponding entry of the identity, 0. Set the entry in row 2, column 2 equal to the corresponding entry of the identity. 1 letter 1d44f minus 2 letter 1d451 equals 0 2 letter 1d44f minus 3 letter 1d451 equals 1 letter 1d445 1 letter 1d4452. Using row operations, multiply and add as follows. Minus 2, letter 1d445 1 plus letter 1d445 2 equals letter 1d4452. Add the two equations and solve for letter 1d451. 1 letter 1d44f minus 2 letter 1d451 equals 0 0 plus 1 letter 1d451 equals 1 letter 1d451 equals 1. Once more, back substitute and solve for letter 1d44f. Letter 1d44f minus 2. 1 equals 0 letter 1d44f minus 2 equals 0 letter 1d44f equals 2. Finding the multiplicative inverse by augmenting with the identity. Another way to find the multiplicative inverse is by augmenting with the identity. When matrix letter 1d434 is transformed into letter 1d43c, the augmented matrix letter 1d43c transforms into letter 1d434 minus 1. For example, given letter 1d434 equals 2513, augment letter 1d434 with the identity 2513, 1001. Perform row operations with the goal of turning letter 1d434 into the identity. Switch row 1 and row 2. 5230, 10110. Multiply row 2 by minus 2 and add to row 1. 1211 minus 2110. Multiply row 1 by minus 2 and add to row 2. 101 minus 1 minus 251 minus 2. Add row 2 to row 1. 100 minus 135 minus 1 minus 2. Multiply row 2 by minus 1. 1001, 3 minus 5 minus 12. The matrix we have found is letter 1d434 minus 1. Letter 1d434 minus 1 equals 3 minus 5 minus 12. Finding the multiplicative inverse of 2 times 2 matrices using a formula. When we need to find the multiplicative inverse of a 2 times 2 matrix, we can use a special formula instead of using matrix multiplication or augmenting with the identity. If letter 1d434 is a 2 times 2 matrix, such as letter 1d434 equals letter 1d44, letter 1d450, letter 1d44f, letter 1d451. The multiplicative inverse of letter 1d434 is given by the formula letter 1d434 minus 1 equals 1, letter 1d44, letter 1d451, minus letter 1d44f, letter 1d450, letter 1d451, minus letter 1d450, minus letter 1d44f, letter 1d440, where letter 1d440, letter 1d451, minus letter 1d44f, letter 1d450, not equal to 0. If letter 1d440, letter 1d451, minus letter 1d44f, letter 1d450 equals 0, then letter 1d434 has no inverse. Example 4. Using the formula to find the multiplicative inverse of matrix A. Use the formula to find the multiplicative inverse of letter 1d434 equals 12 minus 2 minus 3. Solution. Using the formula, we have letter 1d434 minus 1 equals 1, 1, minus 3 minus 2, 2, minus 3 minus 221 equals 1 minus 3 plus 4 minus 3 minus 221 equals minus 3 minus 221. Analysis. We can check that our formula works by using one of the other methods to calculate the inverse. Let's augment letter 1d434 with the identity 12 minus 2 minus 3 1001. Perform row operations with the goal of turning letter 1d434 into the identity. Multiply row 1 by minus 2 and add to row 2 10 minus 21, 1 minus 201. Multiply row 2 by 2 and add to row 1 1001 minus 3 minus 221. So we have verified our original solution. Try it too. Use the formula to find the inverse of matrix letter 1d434. Verify your answer by augmenting with the identity matrix. Letter 1d434 equals 12 minus 13. Example 5. Finding the inverse of the matrix if it exists. Find the inverse if it exists of the given matrix. Letter 1d434 equals 3162. Solution. We will use the method of augmenting with the identity. 3162, 1001. Switch row 1 and row 2. 1332, 0110. Multiply row 1 by minus 3 and add it to row 2. 1021 minus 301. There is nothing further we can do. The zeros in row 2 indicate that this matrix has no inverse. Finding the multiplicative inverse of 3 times 3 matrices. Unfortunately, we do not have a formula similar to the one for a 2 times 2 matrix to find the inverse of a 3 times 3 matrix. Instead, we will augment the original matrix with the identity matrix and use row operations to obtain the inverse. Given a 3 times 3 matrix, letter 1d434 equals 230, 2,334,111. Augment letter 1d434 with the identity matrix. Letter 1d434, letter 1d436 equals 230, 2,334,111. 100,010,001. To begin, we write the augmented matrix with the identity on the right and letter 1d434 on the left, performing elementary row operations so that the identity matrix appears on the left. We will obtain the inverse matrix on the right. We will find the inverse of this matrix in the next example. How to, given a 3 times 3 matrix, find the inverse. Write the original matrix augmented with the identity matrix on the right. Use elementary row operations so that the identity appears on the left. What is obtained on the right is the inverse of the original matrix. Use matrix multiplication to show that letter 1d434 letter 1d434 minus 1 equals letter 1d43c, and letter 1d434 minus 1 letter 1d434 equals letter 1d43c. Example 6. Finding the inverse of a 3 times 3 matrix. Given the 3 times 3 matrix letter 1d434. Find the inverse. Letter 1d434 equals 230, 2,334,111. Solution. Augment letter 1d434 with the identity matrix, and then begin row operations until the identity matrix replaces letter 1d434. The matrix on the right will be the inverse of letter 1d434, 230, 2,334,111, 100,010,001. Write interchange artwent letter 1d445, 1,322,334,111, 010, 100,001. Minus letter 1d445, 2 plus letter 1d445, 1 equals letter 1d445, 1 write 122,034,011, minus 110,100,001. Minus letter 1d445, 2 plus letter 1d445, 3 equals letter 1d445, 3 write 120,030,1010, minus 11 minus 1,100,001. Letter 1d445, 3 left right arrow, letter 1d445, 2 right 102,013,001, minus 1 minus 11,100,010. Minus 2 letter 1d445, 1 plus letter 1d445, 3 equals letter 1d445, 3 right 100,013,001, minus 1, minus 1,310, minus 2,010. Minus 3 letter 1d445, 2 plus letter 1d445, 3 equals letter 1d445, 3 right 100,010,001, minus 1, minus 1,610, minus 201 minus 3. Thus, letter 1d434 minus 1 equals letter 1d435 equals minus 1 minus 1,610 minus 201 minus 3. Analysis. To prove that letter 1d435 equals letter 1d434 minus 1, let's multiply the two matrices together to see if the product equals the identity. If letter 1d434 minus 1 equals letter 1d43c, and letter 1d434 minus 1 letter 1d434 equals letter 1d43c. Letter 1d434 minus 1 equals 230, 2,334,111. Minus 1 minus 1,610 minus 201 minus 3 equals 2 minus 1, plus 3 minus 1 plus 1 6, 3 minus 1 plus 3 minus 1 plus 1 6, 2 minus 1 plus 4 minus 1 plus 1 6, 2 1 plus 3 0, plus 1 minus 2 3 1 plus 3 0, plus 1 minus 2 2 1 plus 4 0, plus 1 minus 2 2 0, plus 3 1 plus 1 minus 3 3 0, plus 3 1 plus 1. Letter 1d434 minus 1, letter 1d434 equals minus 1 minus 1,610 minus 201 minus 3. 232,334,111 equals minus 1, 2 plus 1 3 plus 0, 2 minus 1 2 plus 0 3, plus 1 2 6 2 plus minus 2 3 plus minus 3 2 minus 1 3 plus 1 3 plus 0, 4 minus 1 3 plus 0 3 plus 1 4 6, 3 plus minus 2 3 plus minus 3 4 minus 1 1 plus 1 1 plus 0, 1 minus 1 1 plus 0, 1 plus 1 1 6, 1. Try it 3. Find the inverse of the 3 times 3 matrix. Letter 1d434 equals 2 minus 10 minus 1,700, 11,300, 11 minus 7 minus 2. Solving a system of linear equations using the inverse of a matrix. Solving a system of linear equations using the inverse of a matrix requires the definition of two new matrices. X is the matrix representing the variables of the system, and letter 1d435 is the matrix representing the constants. Using matrix multiplication, we may define a system of equations with the same number of equations as variables as letter 1d434 letter 1d44b equals letter 1d435. To solve a system of linear equations using an inverse matrix, let letter 1d434 be the coefficient matrix, let letter 1d44b be the variable matrix, and let letter 1d435 be the constant matrix. Thus, we want to solve a system letter 1d434 letter 1d44b equals letter 1d435. For example, look at the following system of equations. Letter 1d44e, 1 letter 1d465 plus letter 1d44f, 1 letter 1d466 equals letter 1d450, 1 letter 1d44e2x plus beta letter 1d466 equals letter 1d450, From this system, the coefficient matrix is letter 1d434 equals letter 1d44e, 1 letter 1d44e to be 1b2. The variable matrix is letter 1d44b equals letter 1d465 letter 1d466, and the constant matrix is letter 1d435 equals letter 1d450, 1 letter 1d450, Then letter 1d434 letter 1d44b equals letter 1d435. Looks like letter 1d44e, 1 letter 1d44e to be 1b2, letter 1d465 letter 1d466 equals letter 1d450, 1 letter 1d450, Recall the discussion earlier in this section regarding multiplying a real number by its inverse. 2 minus 1 2 equals 12 2 equals 1. To solve a single linear equation, letter 1d44 letter 1d465 equals letter 1d44f. For letter 1d465, we would simply multiply both sides of the equation by the multiplicative inverse, reciprocal, of. Thus, letter 1d44 letter 1d465 equals letter 1d44f. 1 letter 1d44e, letter 1d44 letter 1d465 equals 1 letter 1d44e letter 1d44f. Letter 1d44e minus 1. Letter 1d44 letter 1d465 equals letter 1d44e minus 1 letter 1d44f. Letter 1d44e minus 1 letter 1d44e letter 1d465 equals letter 1d44e minus 1 letter 1d44f, 1 letter 1d465 equals letter 1d44e minus 1 letter 1d44f, letter 1d465 equals letter 1d44e minus 1, letter 1d44f. The only difference between solving a linear equation and a system of equations written in matrix form is that finding the inverse of a matrix is more complicated, and matrix multiplication is a longer process. However, the goal is the same: to isolate the variable. We will investigate this idea in detail, but it is helpful to begin with a 2 times 2 system and then move on to a 3 times 3 system. Solving a system of equations using the inverse of a matrix. Given a system of equations, write the coefficient matrix letter 1d434, the variable matrix letter 1d44b, and the constant matrix letter 1d435. Then, letter 1d434 letter 1d44b equals letter 1d435. Multiply both sides by the inverse of letter 1d434 to obtain the solution. Letter 1d434 minus 1 letter 1d434 letter 1d44b equals letter 1d434 minus 1 letter 1d435. Letter 1d434 minus 1 letter 1d434 letter 1d44b equals letter 1d434 minus 1 letter 1d435 letter 1d436 letter 1d44b equals letter 1d434 minus 1 letter 1d435 letter 1d44b equals letter 1d434 minus 1. Q&A. If the coefficient matrix does not have an inverse, does that mean the system has no solution? No, if the coefficient matrix is not invertible, the system could be inconsistent and have no solution, or be dependent and have infinitely many solutions. Example 7. Solving a 2 times 2 system using the inverse of a matrix. Solve the given system of equations using the inverse of a matrix. 3 letter 1d465 plus 8 letter 1d466 equals 54 letter 1d465 plus 11 letter 1d466 equals 7. Solution. Write the system in terms of a coefficient matrix, a variable matrix, and a constant matrix. Letter 1d434 equals 34,811. Letter 1d44b equals letter 1d465 letter 1d466. Letter 1d435 equals 57. Then, 34,811. Letter 1d465 letter 1d466 equals 57. First, we need to calculate letter 1d434 minus 1. Using the formula to calculate the inverse of a 2 by 2 matrix, we have letter 1d434 minus 1 equals 1 letter 1d44 letter 1d451 minus letter 1d44f letter 1d450 letter 1d451 minus letter 1d450 minus letter 1d4 4f letter 1d4 4e equals 13. 11 minus 8. 4 11 minus 4 minus 83 equals 11 11 minus 4 minus 83. So, letter 1d4 3 4 minus 1 equals 11 minus 4 minus 83. Now we are ready to solve. Multiply both sides of the equation by letter 1d4 3 4 minus 1. Letter 1d4 3 4 minus 1, letter 1d4 3 4 letter 1d4 4b equals letter 1d4 3 4 minus 1 letter 1d4 3 5 11 minus 4 minus 83. 34,811. Letter 1d4 6 5 letter 1d4 6 6 equals 11 minus 4 minus 80 357 1001. Letter 1d4 6 5 letter 1d4 6 6 equals 11 5 plus minus 8 7 minus 4 5 plus 3 7 letter 1d4 6 5 letter 1d4 6 6 equals minus 11. The solution is minus 1. 1. Q&A. Can we solve for letter 1d4 4b? By finding the product letter 1d4 3 5 letter 1d4 3 4 minus 1? No. Recall that matrix multiplication is not commutative, so letter 1d4 3 4 minus 1, letter 1d4 3 5, not equal to letter 1d4 3 5 letter 1d4 3 4 minus 1. Consider our steps for solving the matrix equation. Letter 1d4 3 4 minus 1 letter 1d4 3 4 letter 1d4 4b equals letter 1d4 3 4 minus 1 letter 1d4 3 5. Letter 1d4 3 4 minus 1 letter 1d4 3 4 letter 1d4 4b equals letter 1d4 3 4 minus 1 letter 1d4 3 5 letter 1d4 3 c letter 1d4 4b equals letter 1d4 3 4 minus 1 letter 1d4 3 5 letter 1d4 4b equals letter 1d4 3 4 minus 1. Notice in the first step, we multiplied both sides of the equation by letter 1d4 3 4 minus 1, but the letter 1d4 3 4 minus 1 was to the left of letter 1d4 3 4, on the left side, and to the left of letter 1d4 3 5, on the right side. Because matrix multiplication is not commutative, order matters. Example 8. Solving a 3 times 3 system using the inverse of a matrix. Solve the following system using the inverse of a matrix. 5 letter 1d4 6 5 plus 15 letter 1d4 6 6 plus 56 letter 1d4 6 7 equals 35 minus 4 letter 1d4 6 5 minus 11 letter 1d4 6 6 minus 41 letter 1d4 6 7 equals minus 26 minus letter 1d4 6 5 minus 3 letter 1d4 6 6 minus 11 letter 1d4 6 7 equals minus 7. Solution. Write the equation letter 1d4 3 4 letter 1d4 4b equals letter 1d4 3 5. 5 minus 4 minus 115 minus 11 minus 356 minus 41 minus 11. Letter 1d4 6 5 letter 1d4 6 6 letter 1d4 6 7 equals 35 minus 26 minus 7. First, we will find the inverse of letter 1d4 3 4 by augmenting with the identity. 5 minus 4 minus 115 minus 11 minus 356 minus 41 minus 11 100 million 10,001. Multiply row 1 by 15. 1 minus 4 minus 13 minus 11 minus 3,565 minus 41 minus 11. 1,500,010,001. Multiply row 1 by 4 and add to row 2. 10 minus 130, 1 minus 3,565,195 minus 11,15,450,010,001. Add row 1 to row 3. 10,030,000,030, 1,056,519,515,154,515,010,001. Multiply row 2 by minus 3 and add to row 1. 100,010 minus 1,519,515 minus 1,154,515 minus 310,001. Multiply row 3 by 5. 100,010 minus 151,951 minus 115,451 minus 310,005. Multiply row 3 by 15 and add to row 1. 10,001,001,951 minus 2,451 minus 310,105. Multiply row 3 by minus 195 and add to row 2. 100,010,001 minus 2 minus 30, 1 minus 3101 minus 195. So, letter 1d434 minus 1 equals minus 2 minus 30, 1 minus 3100, 1 minus 195. Multiply both sides of the equation by letter 1d434 minus 1. We want letter 1d434 minus 1, letter 1d434, letter 1d44b, equals letter 1d434 minus 1, letter 1d435. Minus 2 minus 31 minus 3101 minus 195 5 minus 4 minus 115 minus 11 minus 356 minus 40, 1 minus 11. Letter 1d465, letter 1d466, letter 1d467 equals minus 2 minus 30, 1 minus 3101 minus 195 35 minus 26 minus 7. Thus, letter 1d434 minus 1, letter 1d435 equals minus 70 plus 78 minus 7 minus 105 minus 26 plus 13,335 plus 0 minus 35 equals 120. The solution is 1, 2, 0. Try it 4. Solve the system using the inverse of the coefficient matrix. 2 letter 1d465 minus 17 letter 1d466 plus 11 letter 1d467 equals 0 minus letter 1d465 plus 11 letter 1d466 minus 7 letter 1d467 equals 8 3 letter 1d466 minus 2 letter 1d467 equals minus 2. How to, given a system of equations, solve with matrix inverses using a calculator. Save the coefficient matrix and the constant matrix as matrix variables letter 1d434 and letter 1d435. Enter the multiplication into the calculator, calling up each matrix variable as needed. If the coefficient matrix is invertible, the calculator will present the solution matrix. If the coefficient matrix is not invertible, the calculator will present an error message. Example 9. Using a calculator to solve a system of equations with matrix inverses. Solve the system of equations with matrix inverses using a calculator. 2 letter 1d465 plus 3 letter 1d466 plus letter 1d467 equals 323 letter 1d465 plus 3 letter 1d466 plus letter 1d467 equals minus 272 letter 1d465 plus 4 letter 1d466 plus letter 1d467 equals minus 2. Solution. On the matrix page of the calculator, enter the coefficient matrix as the matrix variable letter 1d434, and enter the constant matrix as the matrix variable letter 1d435. On the home screen of the calculator, type in the multiplication to solve for letter 1d44b, calling up each matrix variable as needed. Letter 1d434 minus 1 times letter 1d435. Evaluate the expression. Minus 59 minus 34,252. Media. Access these online resources for additional instruction and practice with solving systems with inverses. The identity matrix. Determining inverse matrices. Using a matrix equation to solve a system of equations. 7.7 section exercises. Verbal. 1. In a previous section, we showed that matrix multiplication is not commutative. That is, letter 1d434, letter 1d435 not equal to letter 1d435, letter 1d434. In most cases, can you explain why matrix multiplication is commutative for matrix inverses? That is, letter 1d434 minus 1 letter 1d434 equals letter 1d434, letter 1d434 minus 1. 2. Does every 2 times 2 matrix have an inverse? Explain why or why not. Explain what condition is necessary for an inverse to exist. 3. Can you explain whether a 2 times 2 matrix with an entire row of zeros can have an inverse? 4. Can a matrix with an entire column of zeros have an inverse? Explain why or why not. 5. Can a matrix with zeros on the diagonal have an inverse? If so, find an example. If not, prove why not. For simplicity, assume a 2 times 2 matrix algebraic. In the following exercises, show that matrix letter 1d434 is the inverse of matrix letter 1d435. 6. Letter 1d434 equals 1 minus 101. Letter 1d435 equals 1101. 7. Letter 1D434 equals 1,324. Letter 1D435 equals minus 2,321 minus 12. 8. Letter 1D434 equals 4,750. Letter 1D435 equals 0, 1, 517 minus 435. 9. 10. Letter 1D434 equals 1,111 minus 11. Letter 1D435 equals 12 20,011 minus 1 minus 111. 11. Letter 1D434 equals 141,200, 6,329. Letter 1D435 equals 14,617 minus 120 minus 32 minus 2 minus 54. 12. Letter 1D434 equals 3,158,162,112. Letter 1D435 equals 136 minus 67 minus 180, 4 minus 26 minus 22 minus 615. For the following exercises, find the multiplicative inverse of each matrix, if it exists. 13, 31 minus 29. 14, minus 2,321. 15, minus 3,972. 16, minus 4 minus 5 minus 38. 17, 1,212. 18, 0,110. 19, 0, 511, 5 minus 0, 5. 20, 1 minus 23,010,672. 21, 0,41110, minus 305. 22, 1 minus 3 minus 224 minus 4 minus 11 minus 5. 23, 12,495 minus 2 minus 367. 24, 1 minus 40 1 minus 2,840, 3 minus 122. 25, 121, quadrillion 316 trillion 121 billion 400, 17,121,518. 26, 140, 7,250, 8,369. For the following exercises, solve the system using the inverse of a 2 times 2. Matrix 27. 5 letter 1D465 minus 6 letter 1D466 equals minus 614 letter 1D465 plus 3 letter 1D466 equals minus 2. 28. 8 letter 1D465 plus 4 letter 1D466 equals minus 1003 letter 1D465 minus 4 letter 1D466 equals 1. 29. 3 letter 1D465 minus 2 letter 1D466 equals 6 minus letter 1D465 plus 5 letter 1D466 equals minus 2. 30. 5 letter 1D465 minus 4 letter 1D466 equals minus 54 letter 1D465 plus letter 1D466 equals 2. 3. 31. Minus 3 letter 1D465 minus 4 letter 1D466 equals 912 letter 1D465 plus 4 letter 1D466 equals minus 6. 32. Minus 2 letter 1D465 plus 3 letter 1D466 equals 310 minus letter 1D465 plus 5 letter 1D466 equals 12. 33. 85 letter 1D465 minus 45 letter 1D466 equals 25 minus 85 letter 1D465 plus 15 letter 1D466 equals 710. 34. 12 letter 1D465 plus 15 letter 1D466 equals minus 1,412 letter 1D465 minus 35 letter 1D466 equals minus 94. For the following exercises, solve a system using the inverse of a 3 times 3. Matrix 35. 3 letter 1D465 minus 2 letter 1D466 plus 5 letter 1D467 equals 215 letter 1D465 plus 4 letter 1D466 equals 37 letter 1D465 minus 2 letter 1D466 minus 5 letter 1D467 equals 5. 36. 4 letter 1D465 plus 4 letter 1D466 plus 4 letter 1D467 equals 402 letter 1D465 minus 3 letter 1D466 plus 4 letter 1d467 equals minus 12 minus letter 1d465 plus 3 letter 1d466 plus 4 letter 1d467 equals 9. 37. 6 letter 1d465 minus 5 letter 1d466 minus letter 1d467 equals 31 minus letter 1d465 plus 2 letter 1d466 plus letter 1d467 equals minus 63 letter 1d465 plus 3 letter 1d466 plus 2 letter 1d467 equals 13. 38. 6 letter 1d465 minus 5 letter 1d466 plus 2 letter 1d467 equals minus 42 letter 1d465 plus 5 letter 1d466 minus letter 1d467 equals 122 letter 1d465 plus 5 letter 1d466 plus letter 1d467 equals 12. 39. 4 letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals minus 122 letter 1d465 plus 2 letter 1d466 minus 9 letter 1d467 equals 336 letter 1d466 minus 4 letter 1d467 equals 1. 40. 110 letter 1d465 minus 15 letter 1d466 plus 4 letter 1d467 equals minus 41,215 letter 1d465 minus 20 letter 1d466 plus 25 letter 1d467 equals minus 101,310 letter 1d465 plus 4 letter 1d466 minus 310 letter 1d467 equals 23. 41. 12 letter 1d465 minus 15 letter 1d466 plus 15 letter 1d467 equals 31,100 minus 34 letter 1d465 minus 14 letter 1d466 plus 12 letter 1d467 equals 740 minus 45 letter 1d465 minus 12 letter 1d466 plus 32 letter 1d467 equals 14. 42. 0, 1x plus 0, 2y plus 0, 3 letter 1d467 equals minus 1. 40. 1 letter 1d465 minus 0, 2y plus 0, 3 letter 1d467 equals 0. 60. 4y plus 0, 9 letter 1d467 equals minus 2. Technology. For the following exercises, use a calculator to solve the system of equations with matrix inverses. 43. 2 letter 1d465 minus letter 1d466 equals minus 3 minus letter 1d465 plus 2 letter 1d466 equals 2. 3. 44. Minus 12 letter 1d465 minus 32 letter 1d466 equals minus 432,052 letter 1d465 plus 115 letter 1d466 equals 314. 45. 12. 3 letter 1d465 minus 2 letter 1d466 minus 2. 5 letter 1d467 equals 236. 9 letter 1d465 plus 7 letter 1d466 minus 7. 5 letter 1d467 equals minus 78 letter 1d466 minus 5 letter 1d467 equals minus 10. 46. 0. 5 letter 1d465 minus 3 letter 1d466 plus 6 letter 1d467 equals minus 0. 80. 7 letter 1d465 minus 2 letter 1d466 equals minus 0. 60. 5 letter 1d465 plus 4 letter 1d466 plus 5 letter 1d467 equals 0. Extensions. For the following exercises, find the inverse of the given matrix. 47. 1 quadrillion 11 billion 10 million 110,101. 48. Minus 1 million 1,002 minus 320 minus 105,201. 49. 101 minus 5 minus 214,030 minus 210,231. 50. 1 septillion 22 quintillion 20 quadrillion 13 trillion 12 billion 230,110. 51. 1 0 0 0 0 1 0 1 0 0 0 1 0 0 1 0 0 1 0 0 0 1 0 1 0 0 0 0 1 1 0 0 0 0. Real-world applications. For the following exercises, write a system of equations that represents the situation. Then, solve the system using the inverse of a matrix. 52. 2,400 tickets were sold for a basketball game. If the prices for floor 1 and floor 2 were different, and the total amount of money brought in is $64,000, how much was the price of each ticket? 53. In the previous exercise, if you were told there were 400 more tickets sold for floor 2 than floor 1, how much was the price of each ticket? 54. A food drive collected 2 different types of canned goods, green beans and kidney beans. The total number of collected cans was 350, and the total weight of all donated food was 348 lb, 12 Oz. If the green bean cans weigh 2 Oz less than the kidney bean cans, how many of each can was donated? 55. Students were asked to bring their favorite fruit to class. 95% of the fruits consisted of banana, apple, and oranges. If oranges were twice as popular as bananas, and apples were 5% less popular than bananas, what are the percentages of each individual fruit? 56. The nursing club held a bake sale to raise money and sold brownies and chocolate chip cookies. They priced the brownies at $1 and the chocolate chip cookies at $0. $75. They raised $700 and sold 850 items. How many brownies and how many cookies were sold? 57. A clothing store needs to order new inventory. It has 3 different types of hats for sale: straw hats, beanies, and cowboy hats. The straw hat is priced at $13. $99, the beanie at $7.99, and the cowboy hat at $14. $49. If 100 hats were sold this past quarter, $1,119 was taken in by sales, and the amount of beanies sold was 10 more than cowboy hats. How many of each should the clothing store order to replace those already sold? 58. Anna, Percy, and Morgan weigh a combined 370 lb. If Morgan weighs 20 lb more than Percy, and Anna weighs 1.5 times as much as Percy, how much does each person weigh? 59. 3 roommates shared a package of 12 ice cream bars, but no one remembers who ate how many. If Micah ate twice as many ice cream bars as Joe, and Albert ate 3 less than Micah, how many ice cream bars did each roommate eat? 60. A farmer constructed a chicken coop out of chicken wire, wood, and plywood. The chicken wire cost $2 per square foot, the wood $10 per square foot, and the plywood $5 per square foot. The farmer spent a total of $51, and the total amount of materials used was 14 ft2. He used 3 ft2, more chicken wire than plywood. How much of each material did the farmer use? 61. Jay has lemon, orange, and pomegranate trees in his backyard. An orange weighs 8 Oz, a lemon 5 Oz, and a pomegranate 11 Oz. Jay picked 142 pieces of fruit weighing a total of 70 lb, 10 Oz. He picked 15, 5 times more oranges than pomegranates. How many of each fruit did Jay pick? Learning objectives. In this section, you will evaluate 2 times 2 determinants. Use Kramer's rule to solve a system of equations in 2 variables. Evaluate 3 times 3 determinants. Use Kramer's rule to solve a system of 3 equations in 3 variables. Know the properties of determinants. We have learned how to solve systems of equations in 2 variables and 3 variables, and by multiple methods: substitution, addition, Gaussian elimination, using the inverse of a matrix, and graphing. Some of these methods are easier to apply than others and are more appropriate in certain situations. In this section, we will study 2 more strategies for solving systems of equations. Evaluating the determinant of a 2 times 2 matrix. A determinant is a real number that can be very useful in mathematics because it has multiple applications, such as calculating area, volume, and other quantities. Here, we will use determinants to reveal whether a matrix is invertible by using the entries of a square matrix to determine whether there is a solution to the system of equations. Perhaps one of the more interesting applications, however, is their use in cryptography. Secure signals or messages are sometimes sent encoded in a matrix. The data can only be decrypted with an invertible matrix and the determinant. For our purposes, we focus on the determinant as an indication of the invertibility of the matrix. Calculating the determinant of a matrix involves following the specific patterns that are outlined in this section. Find the determinant of a 2 times 2 matrix. The determinant of a 2 times 2 matrix given letter 1 D434 equals letter 1 D44, letter 1 D450, letter 1 D44F, letter 1 D451 is defined as. Notice the change in notation. There are several ways to indicate the determinant, including det, letter 1 D434, and replacing the brackets in a matrix with straight lines, letter 1 D434. Example 1. Finding the determinant of a 2 times 2 matrix. Find the determinant of the given matrix. Letter 1 D434 equals 5 minus 623. Solution. Det letter 1 D434 equals 5 minus 623 equals 5, 3 minus 6. 2 equals 27. Using Cramer's rule to solve a system of 2 equations in 2 variables. We will now introduce a final method for solving systems of equations that uses determinants. Known as Cramer's rule, this technique dates back to the middle of the 18th century and is named for its innovator, the Swiss mathematician Gabriel Cramer, 1704–1752, who introduced it in 1750 in Introduction à l'analyse des lignes courbes algébriques. Cramer's rule is a viable and efficient method for finding solutions to systems with an arbitrary number of unknowns, provided that we have the same number of equations as unknowns. Cramer's rule will give us the unique solution to a system of equations if it exists. However, if the system has no solution or an infinite number of solutions, this will be indicated by a determinant of 0. To find out if the system is inconsistent or dependent, another method, such as elimination, will have to be used. To understand Cramer's rule, let's look closely at how we solve systems of linear equations using basic row operations. Consider a system of 2 equations in 2 variables. Letter 1 D440, 1 letter 1 D465 plus letter 1 D44F, 1 letter 1 D466 equals letter 1 D450, 1 letter 1 D44E2X plus beta letter 1 D466 equals letter 1 D450, 2. We eliminate one variable using row operations and solve for the other. Say that we wish to solve for letter 1 D465. If equation 2 is multiplied by the opposite of the coefficient of letter 1 D466, in equation 1 is multiplied by the coefficient of letter 1 D466 in equation 2, and we add the 2 equations, the variable letter 1 D466 will be eliminated. B2A 1x plus beta letter 1 D44F, 1 letter 1 D466 equals letter 1 D44F to letter 1 D450, 1 minus letter 1 D44F, 1 letter 1 D44E to letter 1 D465, minus letter 1 D44F, 1 letter 1 D44F to letter 1 D466, equals minus letter 1 D44F, 1 letter 1 D450 to multiply, R1 by beta multiply R2 by minus letter 1 D44F, 1 beta. Letter 1 D440, 1 letter 1 D465, minus letter 1 D44F, 1 letter 1 D440 to letter 1 D465, equals letter 1 D44F to letter 1 D450, 1 minus letter 1 D44F, 1 letter 1 D450, 2. Now, solve for letter 1 D465. Beta letter 1 D440, 1 letter 1 D465, minus letter 1 D44F, 1 letter 1 D440 to letter 1 D465, equals letter 1 D44F to letter 1 D450, 1 minus letter 1 D44F, 1 letter 1 D450 to letter 1 D465. Letter 1 D44F to letter 1 D440, 1 minus letter 1 D44F, 1 letter 1 D440, 2 equals letter 1 D44F to. Letter 1 D450, 1 minus letter 1 D44F, 1 letter 1 D450, 2 letter 1 D465 equals letter 1 D44F to letter 1 D450, 1 minus letter 1 D44F, 1 letter 1 D450 to beta letter 1 D440, 1 minus letter 1 D44F, 1 letter 1 D440, 2 equals letter 1 D450, 1 letter 1 D450 to. Letter 1 D44F, 1 letter 1 D44F, 2 letter 1 D440, 1 letter 1 D440 to letter 1 D44F, 1 letter 1 D44F 2. Similarly, to solve for letter 1 D466, we will eliminate letter 1 D465. A to A 1x plus A to letter 1 D44F, 1 letter 1 D466 equals letter 1 D440 to letter 1 D450, 1 minus letter 1 D440, 1 letter 1d4 to letter 1d465, minus letter 1d4 1 letter 1d4 to letter 1d466, equals minus letter 1d4 1 letter 1d450 to multiply, r1 by a to multiply r2 by minus letter 1d4 1 letter 1d4 to letter 1d4 1 letter 1d466, minus letter 1d4 1 letter 1d4 to letter 1d466 equals letter 1d4 to letter 1d450, 1 minus letter 1d4 1 letter 1d450, 2. Solving for letter 1d466 gives a to letter 1d4 1 letter 1d466 minus letter 1d4 1 letter 1d4 to letter 1d466 equals letter 1d4 to letter 1d450, 1 minus letter 1d4 1 letter 1d450 to letter 1d466. Letter 1d4 to letter 1d4 1 minus letter 1d4 1 letter 1d4 2 equals letter 1d4 to letter 1d450, 1 minus letter 1d4 1 letter 1d450, 2 letter 1d466 equals letter 1d4 to letter 1d450. 1 minus letter 1d4 1 letter 1d450 to a to letter 1d4 1 minus letter 1d4 1 letter 1d4 2 equals letter 1d4 1 letter 1d450, 2 minus letter 1d4 to letter 1d450, 1 letter 1d4 1 letter 1d4 2 minus letter 1d4 to letter 1d4 1 equals letter 1d4 1 letter 1d4 to letter 1d450, 1 letter 1d450, 2 letter 1d4 1 letter 1d4 to letter 1d4 1 letter 1d4 2. Notice that the denominator for both letter 1d465 and letter 1d466 is the determinant of the coefficient matrix. We can use these formulas to solve for letter 1d465 and letter 1d466, but Cramer's rule also introduces new notation, d. Determinant of the coefficient matrix, letter 1d437 letter 1d465. Determinant of the numerator in the solution of letter 1d465. Letter 1d465 equals letter 1d437 letter 1d465, letter 1d437. Letter 1d437 letter 1d466. Determinant of the numerator in the solution of letter 1d466. Letter 1d466 equals letter 1d437 letter 1d466, letter 1d437. The key to Cramer's rule is replacing the variable column of interest with the constant column and calculating the determinants. We can then express letter 1d465 and letter 1d466 as a quotient of two determinants. Cramer's rule for 2 times 2 systems. Cramer's rule is a method that uses determinants to solve systems of equations that have the same number of equations as variables. Consider a system of 2 linear equations in 2 variables. Letter 1d44, 1 letter 1d465 plus letter 1d44f, 1 letter 1d466 equals letter 1d450, 1 letter 1d44e2x plus beta letter 1d466 equals letter 1d450, 2. The solution using Cramer's rule is given as letter 1d465 equals letter 1d437 letter 1d465, letter 1d437 equals letter 1d450, 1 letter 1d450 to letter 1d44f, 1 letter 1d44f, 2 letter 1d44e, 1 letter 1d44e to letter 1d44f, 1 letter 1d44f, 2. Letter 1d437 not equal to 0. Letter 1d466 equals letter 1d437 letter 1d466. Letter 1d437 equals letter 1d440, 1 letter 1d440 to letter 1d450, 1 letter 1d450, 2 letter 1d440, 1 letter 1d440 to letter 1d44f, 1 letter 1d44f, 2. Letter 1d437 not equal to 0. If we are solving for letter 1d465, the letter 1d465 column is replaced with the constant column. If we are solving for letter 1d466, the letter 1d466 column is replaced with the constant column. Example 2. Using Cramer's rule to solve a 2 times 2 system. Solve the following 2 times 2 system using Cramer's rule. 12 letter 1d465 plus 3 letter 1d466 equals 15 2 letter 1d465 minus 3 letter 1d466 equals 13. Solution. Solve for letter 1d465. Letter 1d465 equals letter 1d437 letter 1d465, letter 1d437 equals 15,133 minus 3 1,223 minus 3 equals minus 45 minus 39 minus 36 minus 6 equals minus 84 minus 42 equals 2. Solve for letter 1d466. Letter 1d466 equals letter 1d437 letter 1d466. Letter 1d437 equals 1,221,513. 1,223 minus 3 equals 156 minus 30 minus 36 minus 6 equals minus 12,642 equals minus 3. The solution is 2 minus 3. Try it 1. Use Kramer's rule to solve the 2 times 2 system of equations. Letter 1d465 plus 2 letter 1d466 equals minus 11 minus 2 letter 1d465 plus letter 1d466 equals minus 13. Evaluating the determinant of a 3 times 3 matrix. Finding the determinant of a 2 times 2 matrix is straightforward, but finding the determinant of a 3 times 3 matrix is more complicated. One method is to augment the 3 times 3 matrix with a repetition of the first 2 columns, giving a 3 times 5 matrix. Then, we calculate the sum of the products of entries down each of the 3 diagonals, upper left to lower right, and subtract the products of entries up each of the 3 diagonals, lower left to upper right. This is more easily understood with a visual and an example. Find the determinant of the 3 times 3 matrix. Letter 1d434 equals letter 1d440, 1 letter 1d440 to a, 3b 1b to b 3, c1 c to letter 1d4503. Augment letter 1d434. With the first 2 columns, det letter 1d434 equals letter 1d440, 1 letter 1d440 to a, 3b 1b to b 3 c1 c to letter 1d450, 3 letter 1d440, 1 letter 1d440 to a, 3b1 b to letter 1d44f3. From upper left to lower right, multiply the entries down the first diagonal. Add the result to the product of entries down the second diagonal. Add this result to the product of the entries down the third diagonal. From lower left to upper right, subtract the product of entries up the first diagonal. From this result, subtract the product of entries up the second diagonal. From this result, subtract the product of entries up the third diagonal. The algebra is as follows. Letter 1d434 equals letter 1d440, 1 letter 1d44f to c, 3, plus b1c to a 3, plus c1a to letter 1d44f, 3 minus letter 1d440, 3 letter 1d44f to letter 1d450, 1 minus letter 1d44f, 3 letter 1d450 to letter 1d440, 1 minus letter 1d450, 3 letter 1d440 to be 1. Example 3. Finding the determinant of a 3 times 3 matrix. Find the determinant of the 3 times 3 matrix given. Letter 1d434 equals 0,342 minus 10,111. Solution. Augment the matrix with the first 2 columns, and then follow the formula. Thus, letter 1d434 equals 0,342 minus 10,111, 0,342 minus 10 equals 0, minus 1. 1, plus 2, 1, 4 plus 1, 3, 0 minus 4 minus 1, 1 minus 0, 1, 0, minus 1, 3. 2 equals 0 plus 8 plus 0 plus 4 minus 0 minus 6 equals 6. Try it 2. Find the determinant of the 3 times 3 matrix. Det, letter 1d434, equals 111 minus 30, 1 minus 2,713. Q&A. Can we use the same method to find the determinant of a larger matrix? No, this method only works for 2 times 2 and 3 times 3 matrices. For larger matrices, it is best to use a graphing utility or computer software, using Kramer's rule to solve a system of 3 equations in 3 variables. Now that we can find the determinant of a 3 times 3 matrix, we can apply Kramer's rule to solve a system of 3 equations in 3 variables. Kramer's rule is straightforward, following a pattern consistent with Kramer's rule for 2 times 2 matrices. As the order of the matrix increases to 3 times 3, however, there are many more calculations required. When we calculate the determinant to be 0, Kramer's rule gives no indication as to whether the system has no solution or an infinite number of solutions. To find out, we have to perform elimination on the system. Consider a 3 times 3 system of equations. Letter 1D465 equals letter 1D437 letter 1D465, letter 1D437. Letter 1D466 equals letter 1D437 letter 1D466, letter 1D437. Letter 1D467 equals letter 1D437 letter 1D467, letter 1D437. Letter 1D437 not equal to 0, where, if we are writing the determinant letter 1D437 letter 1D465, we replace the letter 1D465 column with the constant column. If we are writing the determinant letter 1D437 letter 1D466, we replace the letter 1D466 column with the constant column. If we are writing the determinant letter 1D437 letter 1D467, we replace the letter 1D467 column with the constant column. Always check the answer. Example 4. Solving a 3 times 3 system using Cramer's rule. Find the solution to the given 3 times 3 system using Cramer's rule. Letter 1D465 plus letter 1D466 minus letter 1D467 equals 63 letter 1D465 minus 2 letter 1D466 plus letter 1D467 equals minus 5 letter 1D465 plus 3 letter 1D466 minus 2 letter 1D467 equals 14. Solution. Use Cramer's rule. Letter 1D437 equals 1,300, 11 minus 23 minus 11 minus 2. Letter 1D437 letter 1D465 equals 6 minus 5,140, 1, minus 23 minus 11 minus 2. Letter 1D437 letter 1D466 equals 1,316, minus 514, minus 11 minus 2. Letter 1D437 letter 1D467 equals 1,300, 11 minus 230, 6 minus 514. Then, letter 1D465 equals letter 1D437 letter 1D465, letter 1D437 equals minus 3 minus 3 equals 1 letter 1D466, equals letter 1D437 letter 1D466, letter 1D437 equals minus 9 minus 3 equals 3, letter 1D467 equals letter 1D437 letter 1D467, letter 1D437 equals 6 minus 3 equals minus 2. The solution is 1. 3 minus 2. Try it 3. Use Cramer's rule to solve the 3 times 3 matrix. Letter 1D465 minus 3 letter 1D466 plus 7 letter 1D467 equals 13 letter 1D465 plus letter 1D466 plus letter 1D467 equals 1 letter 1D465 minus 2 letter 1D466 plus 3 letter 1D467 equals 4. Example 5. Using Cramer's rule to solve an inconsistent system. Solve the system of equations using Cramer's rule. 3 letter 1D465 minus 2 letter 1D466 equals 4. 1. 6 letter 1D465 minus 4 letter 1D466 equals 0. 2. Solution. We begin by finding the determinants letter 1D437, letter 1D437 letter 1D465, and letter 1D437 letter 1D466. Letter 1D437 equals 36 minus 2 minus 4 equals 3, minus 4 minus 6, minus 2 equals 0. We know that a determinant of 0 means that either the system has no solution, or it has an infinite number of solutions. To see which one, we use the process of elimination. Our goal is to eliminate one of the variables. Multiply equation 1 by minus 2. Add the result to equation 2. Minus 6 letter 1D465 plus 4 letter 1D466 equals minus 86 letter 1D465 minus 4 letter 1D466 equals 0, 0 equals minus 8. We obtain the equation 0 equals minus 8, which is false. Therefore, the system has no solution. Graphing the system reveals 2 parallel lines. See Figure 1. Figure 1. Example 6. Use Cramer's rule to solve a dependent system. Solve the system with an infinite number of solutions. Letter 1D465 minus 2 letter 1D466 plus 3 letter 1D467 equals 0, 3 letter 1D465 plus letter 1D466 minus 2 letter 1D467 equals 0, 2 letter 1D465 minus 4 letter 1D466 plus 6 letter 1D467 equals 0. 1, 2, 3. Solution. Let's find the determinant first. Set up a matrix augmented by the first 2 columns. 132, minus 21 minus 43 minus 26, 132 minus 21 minus 4. Then, 1 1, 6 plus minus 2, minus 2. 2 plus 3 3, minus 4 minus 2 1, 3 minus minus 4, minus 2, 1 minus 6 3, minus 2 equals 0. As the determinant equals 0, there is either no solution or an infinite number of solutions. We have to perform elimination to find out. Multiply equation 1 by minus 2, and add the result to equation 3. Minus 2 letter 1d465, plus 4 letter 1d466, minus 6 letter 1d467 equals 0 2 letter 1d465, minus 4 letter 1d466, plus 6 letter 1d467 equals 0 0 equals 0. Obtaining an answer of a statement that is always true means that the system has an infinite number of solutions. Graphing the system, we can see that two of the planes are the same and they both intersect the third plane on a line. See Figure 2. Figure 2. Understanding properties of determinants. There are many properties of determinants. Listed here are some properties that may be helpful in calculating the determinant of a matrix. Properties of determinants. If the matrix is in upper triangular form, the determinant equals the product of entries down the main diagonal. When two rows are interchanged, the determinant changes sign. If either two rows or two columns are identical, the determinant equals 0. If a matrix contains either a row of zeros or a column of zeros, the determinant equals 0. The determinant of an inverse matrix, letter 1d434-1, is the reciprocal of the determinant of the matrix letter 1d434. If any row or column is multiplied by a constant, the determinant is multiplied by the same factor. Example 7. Illustrating properties of determinants. Illustrate each of the properties of determinants. Solution. Property 1 states that if the matrix is in upper triangular form, the determinant is the product of the entries down the main diagonal. Letter 1d434 equals 10,022,030, 1 minus 1. Augment letter 1d434. With the first two columns, letter 1d434 equals 10,022,030, 1 minus 100,220. Then, det letter 1d434 equals 1 2, minus 1 plus 2 1, 0 plus 3 0, 0 minus 0 2, 3 minus 0 1, 1 plus 1 0. 2 equals minus 2. Property 2 states that interchanging rows changes the sign. Given, letter 1d434 equals minus 145 minus 3. Det letter 1d434 equals minus 1, minus 3 minus 4. 5 equals 3 minus 20 equals minus 17. Letter 1d435 equals 4 minus 1 minus 35. Det letter 1d435 equals 4, 5 minus minus 1, minus 3 equals 20 minus 3 equals 17. Property 3 states that if two rows or two columns are identical, the determinant equals 0. Letter 1d434 equals 12 minus 1,222,222, 12 minus 1,222 det. Letter 1d434 equals 1 2, 2 plus 2, 2 minus 1 plus 2, 2, 2 plus 1 2, 2 minus 2, 2, 1 minus 2, 2. 2 equals 4 minus 4 plus 8 plus 4 minus 4 minus 8 equals 0. Property 4 states that if a row or column equals 0, the determinant equals 0. Thus, letter 1d434 equals 1020, det. Letter 1d434 equals 1, 0 minus 2, 0, equals 0. Property 5 states that the determinant of an inverse matrix, letter 1d434 minus 1, is the reciprocal of the determinant letter 1d434. Thus, letter 1d434 equals 1324. Det letter 1d434 equals 1, 4 minus 3. 2 equals minus 2. Letter 1d434 minus 1 equals minus 2321 minus 12. Det letter 1d434 minus 1 equals minus 2, minus 12 minus 32. 1 equals minus 12. Property 6 states that if any row or column of a matrix is multiplied by a constant, the determinant is multiplied by the same factor. Thus, letter 1d434 equals 1324. Det. Letter 1d434 equals 1 4 minus 2, 3, equals minus 2. Letter 1d435 equals 2, 1 32 2 4. Det letter 1d435 equals 2, 4 minus 3, 4 equals minus 4. Example 8. Using Cramer's rule and determinant properties to solve a system, find the solution to the given 3 times 3 system. 2 letter 1d465 plus 4 letter 1d466 plus 4 letter 1d467 equals 23 letter 1d465 plus 7 letter 1d466 plus 7 letter 1d467 equals minus 5 letter 1d465 plus 2 letter 1d466 plus 2 letter 1d467 equals 4, 1, 2, 3. Solution. Using Cramer's rule, we have letter 1d437 equals 230, 1,472,472. Notice that the second and third columns are identical. According to property 3, the determinant will be 0, so there is either no solution or an infinite number of solutions. We have to perform elimination to find out. Multiply equation 3 by 2 and add the result to equation 1. Minus 2 letter 1d465, minus 4 letter 1d466, minus 4 letter 1d465 equals minus 8 2 letter 1d465, plus 4 letter 1d466, plus 4 letter 1d467 equals 20 equals minus 6. Obtaining a statement that is a contradiction means that the system has no solution. Media. Access these online resources for additional instruction and practice with Cramer's rule. Solve a system of 2 equations using Cramer's rule. Solve a system of 3 equations using Cramer's rule. 7-8 section exercises. Verbal. 1. Explain why we can always evaluate the determinant of a square matrix. 2. Examining Cramer's rule. Explain why there is no unique solution to the system when the determinant of your matrix is 0. For simplicity, use a 2 times 2. Matrix. 3. Explain what it means in terms of an inverse for a matrix to have a 0 determinant. For the determinant of 2 times 2, matrix letter 1d434 is 3. If you switch the rows and multiply the first row by 6 and the second row by 2, explain how to find the determinant and provide the answer. Algebraic. For the following exercises, find the determinant. 5. 1324. 6 minus 132 minus 4. 7 2 minus 1 minus 56. 8 minus 8 minus 145. 9 130 minus 4. 10 10,020 minus 10. 11 1050. 20 1. 12 68 minus 34. 13 minus 23. 1 minus 34 0 0 0. 14 minus 1 17 20. 6 minus 0. 5 15 minus 10,001,000 minus 3. 16 minus 10,042,003 minus 3. 17 101,010,100. 18 23 minus 5 minus 3 minus 46,111. 19 minus 2 minus 4,212 minus 80. 4 minus 8 minus 3. 20 6 minus 41 minus 1 minus 3,925 minus 1. 21 52,313 minus 6 minus 11 minus 3. 22 1 1 minus 44. 120 minus 0. 4 minus 102. 5 23 21. 1 minus 9. 3 minus 1. 6303. 1 minus 82. 24 minus 1,215,013 minus 160,140. 1,718. For the following exercises, solve the system of linear equations using Cramer's rule. 25. 2 letter 1d465 minus 3 letter 1d466 equals minus 14 letter 1d465 plus 5 letter 1d466 equals 9. 26. 5 letter 1d465 minus 4 letter 1d466 equals 2 minus 4 letter 1d465 plus 7 letter 1d466 equals 6. 27. 6 letter 1d465 minus 3 letter 1d466 equals 2 minus 8 letter 1d465 plus 9 letter 1d466 equals minus 1. 28. 2 letter 1d465 plus 6 letter 1d466 equals 125 letter 1d465 minus 2 letter 1d466 equals 13. 29. 4 letter 1d465 plus 3 letter 1d466 equals 232 letter 1d465 minus letter 1d466 equals minus 1. 30. 10 letter 1d465 minus 6 letter 1d466 equals 2 minus 5 letter 1d465 plus 8 letter 1d466 equals minus 1. 31. 4 letter 1d465 minus 3 letter 1d466 equals minus 32 letter 1d465 plus 6 letter 1d466 equals minus 4. 32. 4 letter 1d465 minus 5 letter 1d466 equals 7 minus 3 letter 1d465 plus 9 letter 1d466 equals 0. 33. 4 letter 1d465 plus 10 letter 1d466 equals 180 minus 3 letter 1d465 minus 5 letter 1d466 equals minus 105. 34. 8 letter 1d465 minus 2 letter 1d466 equals minus 3 minus 4 letter 1d465 plus 6 letter 1d466 equals 4. For the following exercises, solve the system of linear equations using Cramer's rule. 35. Letter 1d465 plus 2 letter 1d466 minus 4 letter 1d467 equals minus 17 letter 1d465 plus 3 letter 1d466 plus 5 letter 1d467 equals 26 minus 2 letter 1d465 minus 6 letter 1d466 plus 7 letter 1d467 equals minus 6. 36. Minus 5 letter 1d465 plus 2 letter 1d466 minus 4 letter 1d467 equals minus 474 letter 1d465 minus 3 letter 1d466 minus letter 1d467 equals minus 943 letter 1d465 minus 3 letter 1d466 plus 2 letter 1d467 equals 94. 37. 4 letter 1d465 plus 5 letter 1d466 minus letter 1d467 equals minus 7 minus 2 letter 1d465 minus 9 letter 1d466 plus 2 letter 1d467 equals 85 letter 1d466 plus 7 letter 1d467 equals 21. 38. 4 letter 1d465 minus 3 letter 1d466 plus 4 letter 1d467 equals 105 letter 1d465 minus 2 letter 1d467 equals minus 23 letter 1d465 plus 2 letter 1d466 minus 5 letter 1d467 equals minus 9. 39. 4 letter 1d465 minus 2 letter 1d466 plus 3 letter 1d467 equals 6 minus 6 letter 1d465 plus letter 1d466 equals minus 22 letter 1d465 plus 7 letter 1d466 plus 8 letter 1d467 equals 24. 40. 5 letter 1d465 plus 2 letter 1d466 minus letter 1d467 equals 1 minus 7 letter 1d465 minus 8 letter 1d466 plus 3 letter 1d467 equals 1. 56 letter 1d465 minus 12 letter 1d466 plus letter 1d467 equals 7. 41. 13 letter 1d465 minus 17 letter 1d466 plus 16 letter 1d467 equals 73 minus 11 letter 1d465 plus 15 letter 1d466 plus 17 letter 1d467 equals 6,146 letter 1d465 plus 10 letter 1d466 minus 30 letter 1d467 equals minus 18. 42. Minus 4 letter 1d465 minus 3 letter 1d466 minus 8 letter 1d467 equals minus 72 letter 1d465 minus 9 letter 1d466 plus 5 letter 1d467 equals 0. 55 letter 1d465 minus 6 letter 1d466 minus 5 letter 1d467 equals minus 2. 43. 4 letter 1d465 minus 6 letter 1d466 plus 8 letter 1d467 equals 10 minus 2 letter 1d465 plus 3 letter 1d466 minus 4 letter 1d467 equals minus 5 letter 1d465 plus letter 1d466 plus letter 1d467 equals 1. 44. 4 letter 1d465 minus 6 letter 1d466 plus 8 letter 1d467 equals 10 minus 2 letter 1d465 plus 3 letter 1d466 minus 4 letter 1d467 equals minus 512 letter 1d465 plus 18 letter 1d466 minus 24 letter 1d467 equals minus 30. Technology. For the following exercises, use the determinant function on a graphing utility. 45. 1 quadrillion 10 trillion 20 billion 280 1,349,003. 46. 10,300 minus 90,121 minus 2,113 minus 1 minus 2. 47. 1 quintillion 200 quadrillion 11 trillion 200 billion 700 10,020,452. 0002. 48. 1 quadrillion 247 trillion 30 5,800,690,000. Real-world applications. For the following exercises, create a system of linear equations to describe the behavior. Then calculate the determinant. Will there be a unique solution? If so, find the unique solution. 49. Two numbers add up to 56. One number is 20 less than the other. 50. Two numbers add up to 104. If you add 2 times the first number plus 2 times the second number, your total is 208. 51. Three numbers add up to 106. The first number is 3 less than the second number. The third number is 4 more than the first number. 52. Three numbers add to 216. The sum of the first two numbers is 112. The third number is 8 less than the first two numbers combined. For the following exercises, create a system of linear equations to describe the behavior. Then, solve the system for all solutions using Cramer's rule. 53. You invest $10,000 into 2 accounts, which receive 8% interest and 5% interest. At the end of a year, you had $10,710 in your combined accounts. How much was invested in each account? 54. You invest $80,000 into 2 accounts, $22,000 in one account, and $58,000 in the other account. At the end of 1 year, assuming simple interest, you have earned $2,470 in interest. The second account receives 0.5% less than twice the interest on the first account. What are the interest rates for your accounts? 55. A theater needs to know how many adult tickets and children tickets were sold out of the 1,200 total tickets. If children's tickets are $5. 95. Adult tickets are $11.15, and the total amount of revenue was $12,756. How many children's tickets and adult tickets were sold? 56. A concert venue sells single tickets for $40 each and couples tickets for $65. If the total revenue was $18,090 and the 321 tickets were sold, how many single tickets and how many couples tickets were sold? 57. You decide to paint your kitchen green. You create the color of paint by mixing yellow and blue paints. You cannot remember how many gallons of each color went into your mix, but you know there were 10 gal total. Additionally, you kept your receipt and know the total amount spent was $29. $50. If each gallon of yellow costs $2, $59, and each gallon of blue costs $3. 19. How many gallons of each color go into your green mix? 58. You sold 2 types of scarves at a farmer's market and would like to know which one was more popular. The total number of scarves sold was 56. The yellow scarf cost $10, and the purple scarf cost $11. If you had total revenue of $583, how many yellow scarves and how many purple scarves were sold? 59. Your garden produced 2 types of tomatoes, one green and one red. The red weigh 10 Oz and the green weigh 4 Oz. You have 30 tomatoes and a total weight of 13 lb, 14 Oz. How many of each type of tomato do you have? 60. At a market, the 3 most popular vegetables make up 53% of vegetable sales. Corn has 4% higher sales than broccoli, which has 5% more sales than onions. What percentage does each vegetable have in the market share? 61. At the same market, the 3 most popular fruits make up 37% of the total fruit sold. Strawberries sell twice as much as oranges, and kiwis sell 1 more percentage point than oranges. For each fruit, find the percentage of total fruit sold. 62. Three artists performed at a concert venue. The first one charged $15 per ticket, the second artist charged $45 per ticket, and the final one charged $22 per ticket. There were 510 tickets sold, for a total of $12,700. If the first band had 40 more audience members than the second band, how many tickets were sold for each band? 63. A movie theater sold tickets to 3 movies. The tickets to the first movie were $5, the tickets to the second movie were $11, and the third movie was $12. $100 tickets were sold to the first movie. The total number of tickets sold was 642, for a total revenue of $6,774. How many tickets for each movie were sold? For the following exercises, use this scenario. A health-conscious company decides to make a trail mix out of almonds, dried cranberries, and chocolate-covered cashews. The nutritional information for these items is shown in Table 1. Fat G, protein G, carbohydrates G. Almonds 10, 623. Cranberries 10, 0, 0, 208. Cashews 10, 7, 3, 5, 5, 5. Table 1. 64. For the special low-carb trail mix, there are 1,000 pieces of mix. The total number of carbohydrates is 425 g, and the total amount of fat is 572 g. If there are 200 more pieces of cashews than cranberries, how many of each item is in the trail mix? 65. For the hiking mix, there are 1,000 pieces in the mix, containing 390. 8 g of fat and 165 g of protein. If there is the same amount of almonds as cashews, how many of each item is in the trail mix? 66. For the energy booster mix, there are 1,000 pieces in the mix, containing 145 g of protein and 625 g of carbohydrates. If the number of almonds and cashews summed together is equivalent to the amount of cranberries, how many of each item is in the trail mix?